Did you know that machine learning is one of the most powerful technologies shaping the future today? From Netflix recommendations and fraud detection to face recognition, medical diagnosis, self-driving cars and AI-powered applications, machine learning is transforming the way businesses and industries work. But before you can build powerful machine learning models, you need to understand the core concepts behind them. That's why we have created this complete machine learning course for beginners. This isn't just another theory-based tutorial. It's a structured, beginner-friendly course designed to help you understand how machines learn from data and use that knowledge to solve real-world problems. In this course, you'll start with the fundamentals of machine learning, explore its real-world applications, and understand why machine learning is important in today's data-driven world. You will then learn about different machine learning approaches, including supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. We'll also explore important concepts such as classification, regression, the machine learning pipeline, model training, validation, testing, and deployment. And after building a strong foundation, you'll begin learning one of the most important machine learning algorithms, linear regression, from its mathematical concepts to practical implementation in Python. And here's the best part. After completing the course and successfully passing the assessment test, you will receive a course completion certificate. You will find the link to apply for the certificate in the video description and the pinned comment. This course is designed specially for beginners, so you don't need any prior machine learning experience to get started. So if you are ready to begin your journey into machine learning and build a strong foundation for advanced AI and data-driven applications, this course is the perfect place to start. So let's get started.
So we'll start off with an introduction to machine learning. Okay. My name is Sudarshanan and I'll be taking up this session for you tonight. Generally, some guidelines are here that you can read, but let me see if I can pick out the ones that are relevant for today. So in terms of prerequisites, there's not much. It's just, as long as you understand data analysis and what we do in data analysis and things like that, right? That is sufficient prerequisite for this session. Mostly there will not be any exercise in terms of Python or calculations or anything. That's going to come up from the next session onwards, right? Today's is an introductory session where we want to develop that frame of mind and get into that frame of mind to do machine learning. So that's more or less what today's session is going to be about. Okay, so the agenda for today is, as you can see on the screen, we'll start with an introduction to machine learning. Then we'll try to understand what are the motivations behind machine learning, that is, why do we want to do it. We'll discuss very briefly what the current landscape looks like, the academic and the industrial landscape. Then we'll get into the various types of machine learning, the paradigms. And finally, we will look at linear regression as a machine learning model in an introductory way, right? We'll do an introduction to linear regression, and then in the next session we can deep dive into linear regression. So this is the agenda for this session. So first of all, let's recall data analysis a little bit. So what did we do in data analysis? As you can see, generally we had some kind of data that we were working with. So here we seem to have observations, rows of people. Okay, each entry seems to be a person, and we have features associated with each entry. We have gender, male, female, whether they are married or not, income, so on and so forth. Okay, so what exactly happened in data analysis then? Right, we had data. This was what we started with, the data. What did we analyze? So we saw two, very broadly speaking, we saw two kinds of analysis. One is descriptive analysis, one is inferential. In descriptive statistics, you essentially try to summarize the data and make sense of it, right? You use things like mean, median, mode, standard deviation, variance, and all these kinds of metrics. You get some sense of the data, right? And this is done for the full data. In inferential statistics, what did we learn? We learned that it's not possible to collect data when you're dealing with you know, huge volumes of data and population, right? You cannot go around and get data so much in any domain. So you have to rely on certain assumptions and certain theorems, the central limit theorem, sampling, those kinds of things, right? So then you drew conclusions about the population by working with those samples. Okay, a very specific way of doing that would be hypothesis tests. So basically, this is what we did with data. We took the data and we kind of, you know, uh, churned it around, tried to get metrics from it, understood the metrics, interpreted the different metrics, so on and so forth. Okay, so reason now why should we go beyond data analysis? Now whatever I explained is data analysis, be it descriptive or inferential or whatever, right? Why should we go beyond? Now there are many reasons why one might want to go beyond this. A very important one is that in data analysis generally it requires human intervention. So if you remember, in all the tasks that you did as you were doing EDA, descriptive stats, inferential stats, all of those things, there were many places where your intervention was necessary, right? In fact, for example, if you are dealing with correlation values, right, if you are doing a correlation analysis of your data set, then the correlation values, you have to make judgment calls, right? You might see values of 0.8, 0.9. Now in one person's analysis, you might say 0.8, 0.9 correlation is high value. In some other person's analysis, because of their data, they might say this is not even high, right? It's kind of subjective. So human intervention is required, right? And another example is p-value, right? The p-value in the hypothesis test, although universally we have agreed on a threshold of 5%, right? Still, it's a subjective value. So there are many of these, interventions required, right? There are many places where we intervene. So the data automatically does not provide you insight, right? That's how we get the insights from the data in data analysis. So clearly this is not an automated process. Okay, clearly. Question is, can we automate this insight generation process? Now, we'll get more into this, right? But the answer lies in enabling machines to learn. So the interesting thing is that what we are doing when we do data analysis, see, we are learning how to do data analysis, then we are implementing it. Then we are learning something about the data, something about the metrics, then we are concluding things. Can we automate this? Can machines actually learn some of these things? Can machines learn, how to draw insight out of raw data? Yes, generally the answer is yes, which is why we have machine learning. Now that doesn't mean that I'm trying to say machines are equal to human brain, obviously not, but there are many cases where it really helps, right? So this is what we'll be seeing soon. So let's talk about learning for a second here. Generally speaking, like think about this example. I don't know how many of you last time saw a rat or a mouse, maybe on the road somewhere. But even if you haven't seen a rat for over 10 years, you will look at a rat and you will immediately say that's a rat. Okay, very interesting. So basically, you don't go through some, very complicated set of processes to look at a rat and say that's a rat. What am I trying to say? You don't take the data, okay, 2 ears, 2 eyes, tail, black color, whatever, right? And then you don't do mean, median, mode. You don't do any of that, right? You look at the rat and then you're saying, hey, that's a rat immediately. So this is what we mean by learning. Something has happened. Okay. So we have learned how to recognize the rat. This how part. See this how part, right? In data analysis, the how part is what? You're only saying how to do. You're only saying, okay, calculate the mean. You're only saying, okay, do the histogram analysis or correlation analysis. The how part is provided by the user or the data analyst in multiple stages. But if you see a rat and say it's a rat, you actually learned how to recognize the rat, right? So learning is basically a process by which an intelligent entity, there are two words here, gains and sustains the ability to perform tasks and solve problems. So learning doesn't mean doing it one day and then not being able to do it after that. You should be able to do it the first time, second time, third time, and forever, right? Gain and sustain the ability to perform tasks and solve problems. So now the question may be, okay, I understand what learning is, I understand all this, I understand, okay, why I need to go beyond data analysis. Fine, to some extent I get it, right? How do you do that? Where does this learning really occur? What we know is that at least in us or mammals, or even any animals, learning happens in the neurons, right? So it happens in these nerve cells, and technically we know that nerve cells, this we know from biology, they are electrical switching mechanisms, right? Very rudimentary way of putting it, I know, but that's what they are. They are tiny units, right? These new nerve cells or neurons, they are tiny units which go on and off, and they keep pulsing, electric voltage signals and whatnot, right? My point is that there is some kind of mechanism, right? So there is some kind of physical numeric mechanism to how learning works. Okay, so many experiments have been done over the years, right? The processor, the middle part, as you can see in the screen here, I want the processor. So as I said, we want, so this is the data. Okay, if you remember, this is the data that we are all playing with. Of course, the rat here is just symbolic, right? I hope everyone understands. A rat is just a symbol. It is, what is it replacing? It's replacing all the data that we were analyzing and doing hypothesis test and all of that before, right? I'm just replacing all of that with a rat. Okay, so this is the data that we are interested in. Okay, the idea is, can we come up with a set of units, and we don't know what kind of structure these units should have, but it should be a set of units which is numerical mechanism. Okay, some kind of numerical mechanism which we can claim that, okay, it has learned how to recognize a rat. Okay, now you might say, okay, is this even what are we talking about here? Does this work? My answer to that would be, look, more than 1 billion people are driving right now around the world. If you check the stats, at any point in time, there are 1 billion people who are driving. So long ago, people used to say that, okay, there's no chance of self-driving cars. There's no chance of automatic cars. Right? Long ago, it was some kind of fantasy. Now we have companies who are investing in that, and a lot of experiments are going on many places. I think it's being considered to be run publicly, right? All these things are going on. Okay, so yes, it is possible to make machines learn exactly what we know, and we know that driving is not easy, right? Whoever is driving, like whoever from the audience, maybe it's a car or a jeep or a bike, it's not easy. Okay, driving, you go into the roads, the traffic and all the other drivers, we know how it is, right? The point is that it's possible for machines to learn exactly what we can learn. It's very interesting, I know, but it's possible. So see, the human brain is quite powerful. Okay, this whole data to action flow diagram, if you see here, right? Input data and output action. So you see a rat and then you say it's a rat. This happens in a fraction of a second in the human brain. Of course, doing that with a machine, at least in this day and age, it's not easy. Okay, the human brain is quite complex. So it's complex, but what is the goal of machine learning? What is the aim? The aim is exactly what I just told you. We want to essentially offload a lot of tasks to machines. Now you might say, we've been doing that for such a long time. What is this industrial production line and all of those things? Yes, we have been doing for a long time. Those are very simplistic rules. If you see all those industrial production lines and other such things, they follow simplistic rules, and we define the rules, and then you just continuously run the machine or whatever, right? In machine learning, I am not talking about me telling the machine the rule. I'm telling the machine itself going to learn the rule. There's a large difference. So if you see the bottom diagram, I mean, look at the diagram, right? This chip is essentially symbolizing what? A bunch of numbers and units. That thing has to learn how to recognize a rat. This is the aim of machine learning, but it has to find a way to learn. Okay, that is the aim of machine learning. So why machine learning? Of course, we know all this is happening. We spoke about it a bit, but exactly why? Let's see a few more examples. So I was playing around with 3.5, ChatGPT 3.5. Okay, of course, ChatGPT 4 has come out. It is way more powerful and all that. In fact, before 3.5, if you see the version before 3.5, right, ChatGPT, before that, its outputs were not good. right? Those of you who may know this and others who don't know, you can Google it, right? ChatGPT 3 or something, it was way before. So the outputs were very erratic, like if you use very erratic. The reason that generative AI got so much fame and so much popularity is because of this ChatGPT 3.5. It was able to give at least somewhat meaningful results, basically. And those who don't know what ChatGPT is, it's a chat bot essentially, but it is powered by artificial intelligence on the back end, right? It's essentially a very complex machine learning model on the back end. My point is that it made a few mistakes, right? ChatGPT 3.5 made a few mistakes. So I won't go into the details of all this. I was discussing some mathematical stuff with it, but it made some mistakes. Okay, here it made a mistake. And by the way, you can see the slides later. Okay, so then there was a discussion with prime numbers. It made a few mistakes, right? So clearly it makes a mistake. Now, if I go to a professor of math or an expert in math, they will not make this mistake, right? Now again, if another example we may take, there is something called the Google Brain Simulator. Okay, it uses neural networks, which is a kind of machine learning model. Interestingly enough, it took around 16,000 computers to start thinking like a human. 16,000 computers. Okay, and it started recognizing cats after, what's that, 1 crore images of cats. Now, I mean, we all can agree, right? A little baby can start recognizing a cat after seeing it like 2, 3, 4 times, right? That's how complex the human brain is. Then why 16,000 computers? Why should we do machine learning at all? Right? You might be thinking, why? If it is so, so like difficult to make it learn, then why? There are certain motivations which push us to continue in that direction, right? There are many motivations. So I'll not go into the academic motivations. That is something I can just sort of tell right now. People are interested to know the answers to very interesting questions, such as, can a machine uh, recognize everyone in my company? Can a machine speak with me like a human being? All these very curious type of questions, right? Academicians are always interested in that. Great. What about some practical motivations? Can you please check the columns and see? Om says no. Person with maximum income, who is it? I believe row number 2. Oldest is 53. Okay, no. So now if you think about it, how much time did we take on average? How much time do humans take to answer such questions? 2, 3 seconds, 4 seconds, 5 seconds, some of us 10 seconds. Do we agree? It's in at least more than 1, 2 seconds, 3 seconds. Yeah. Computers generally are better at number crunching. Okay. We, on the other hand, humans, we are really good with visuals. Okay. Like there are some uh, papers in biological and psychological fields which say that most of our human learning happens visually, like 70% or 60%, something. I'm just remembering whatever I remember. Don't quote me on biology and things like that. But yeah, a lot of our learning happens visually. So if I look at these images, definitely we will say, okay, this is elephant, this is giraffe, this is a sloth. In seconds, right? Most of us will look at this and immediately recognize animal in seconds. The same thing if you give to a machine or to a machine learning model with moderate power, it will still take more time than you. Okay, you need very, very, very powerful machine learning model to be able to match a human for this task. So what I'm trying to say here is that humans are not good at number crunching. We are good at visual tasks, but humans are not really good at number crunching. And day by day, the amount of data, the amount of numbers in the world is just increasing, right? We are getting more and more data every day. The next point, data volume. So the same question, if I say this data set, same question, is the person with the maximum income also the oldest in the data set? So there are 10 points in this data set. Okay, what if there were 1000, 10,000, a million points? Then what? Right, just multiply the amount of time you took for that operation, just extend that and see how much time would a human take for that. So then you ask the question, is this task supposed to be done by humans or not? If we are not good at all this, right, if we around million data points and I need to sit and crunch those numbers and try to come up with some insight or whatever. Should I really be doing that? Right? If it's inefficient. I'm not saying anything about human beings, I'm also human. But if computers can do like this, then why not? Right? So computers generally can handle all these large numbers. In fact, there's a small article here for those who are interested. I found this very interesting. It's a small note on human short-term memory and things like that. So the claim is that you go through first 100 data points, next 100 you will forget previous 100. Right? It's a very interesting article. So that brings us to automation. Okay, now we know machines can learn, handle all these numbers, right? Okay, it's great. So if I tell the machine a rule, then even if there are million data points, it can get the answer faster than me if I tell the rule. Okay, so great, automation is easily possible. So suppose consider a factory production line. So maybe there is a rule in the factory. Maybe there's a simple rule. If the volume of juice in a bottle is less than 500 milliliters, then you reject the product. Okay, this is a rule. So think about when there weren't so many machines and automation available, right? Generally factories, what do? Depending on the size, you're producing many thousands of such bottles per day, right? So then comes the question, is it profitable or even reasonable to assign this rule execution to a human being? Okay, think about it. What should the human being do? Just sit there and check the bottles, take the bottle and check 500 ml, 500 ml, 500 ml. Long back, I mean, surely humans used to do this, right? When we didn't have automation and things like that. Yes, humans were doing many of these tasks. But the main question is this reasonable? Is this profitable? And the answer to both these questions is no. If you are able to automate certain tasks, you can free up the bandwidth of humans who can then contribute in more valuable ways. So neither is it reasonable nor is it profitable to install a human for such tasks. Wherever automation is possible safely, we should do it. Okay. So if a machine is trained well enough to execute this rule satisfactorily, this will save a lot of human resources, which is very valuable. Okay. There are a few more things which we can get from machines, right? So it can provide additional insights, okay, through number crunching, of course, because it is able to view. So try to think of it metaphorically, right? Because the machine learning model is able to view the full data set, it is able to view. A human has to read through. Machine learning models, in a sense, are able to view the whole thing. So they can generate certain additional insights which we might find difficult. I won't say impossible, but it might be difficult for us to search and come up with those insights, right? So suppose there are two rules which I'm sort of suspecting after going through this data set. So there's one rule which I say, okay, people with more income spend more money. This is a rule that I think the data is telling me. Okay. And there's another rule which is younger people spend more, right? Spend more money. This is also a rule I think that the data is telling me this rule after studying. Okay, we also came up with this understanding by looking at the data and doing some things. What to say if which rule is stronger or more believable? Now we could use something like correlation, right? We could say, okay, what is the correlation between, let's say, what is the first one? Income and expenditure. So maybe I take these two columns, right? I'll take the income and expenditure columns and I will take the correlation. Then similarly, I will take the age and expenditure column, this one and the expenditure, and I'll find the correlation. Then I will see whether my rule is correct or not, right? So I'm getting negative 0.54 and negative 0.36. Yes, there is an inverse relationship. Two, it is somewhat moderate. The strength is moderate. The rule strength, I mean A and B rule, which is stronger rule. The income expenditure correlation seems to be stronger. I can do this, machine can do this, but machine can also automate these things, right? There's no need for my intervention here. I can automate many of these things. And of course, it can handle way more data. Okay, so that's through number crunching. Now, there are certain things that the machine can do, which is very difficult for us. And when I say difficult, way more difficult than doing correlation. In the previous case, I showed you 10 points, right? What if you had 10,000 points and all? You, in the end, you have to do the correlation. You have to look at the matrix. You have to check all those values, right? You have to do all that. But still, you could do that. But now, if I ask the question, is it better to divide these 10 people into 2 groups or 3 groups for my business? Now, this is where things get very complicated. How are you going to justify? What is the method you're going to use? So look, I have 10 people in this data set. Okay, suppose they are customers or something like that. Then say my team comes to me, or my manager comes to me and says, look, we need to do some intervention measure. Our product is not going well in this city. Maybe these 10 data points are from a certain city. And then the manager says, look, we need to do some kind of targeted marketing, productization, that kind of thing. So then what am I supposed to do? What do I do? Should I do this in 2 groups, 3 groups? How do I even analyze this? You see, it gets so complex when you try to handle some of these questions from data through pure data analysis. It becomes very complex. You will get, so what will happen is you will get deeper and deeper into rules and rules and rules and rules, metrics. You will get deeper and deeper into that. It becomes very complicated. At the end of it, you may have an answer, but when you go present it to your team, they will say, what is going on? Okay. Machine learning algorithms can actually answer this question like this, right? Very interesting. And although they do it mathematically, there is some kind of meaning to it. So in this case, of course, most of you would have realized I am talking about clustering. Okay, it's an unsupervised algorithm, clustering. Later in the course, we will be studying clustering also, right? So interestingly, the machine learning algorithm can do these kinds of things automatically also. It can tell me, right? The machine can tell me, should I split into 2 groups for my business, or should I split into 3 groups? Which is more profitable, which is more reasonable, and why? Who are these 2 groups? Who are these 3 groups? All these answers will come from the machine learning model. So you see, there are many of these motivations. Now, there are a couple of others. I've given you some of the major ones. These are some of the obvious ones, right? Precision is a very important one. We humans obviously have a lot of bias when it comes to reading data, looking at data, studying data, making comments about data, right? We have our biases, right? Measurement bias also is a problem. Somebody might write a 3 as an 8 or something, all sorts of things. Surely the computational machines do not suffer from this. So in fact, if you see the screen, this is a very age-old, I think, visual psychology problem, right? Which line segment is longer? To me, it looks like the bottom line segment is longer. And I think to most people also in the audience, just by looking at it, our eyes are playing tricks on us, right? However hard you try, your eyes are playing tricks on you, right? The bottom one looks longer. But if I remove these arrow things, as you can see, they are the same length, right? So for a machine, there's no question of measurement bias. Okay, it's going to read 3 as 3. It's going to read 2.5 as 2.5. Right? There's no mistake or bias going on there. So computing machines are generally less prone to these kinds of measurement biases and measurement errors. Okay. And finally, exhaustion, which is what I'm feeling right now after speaking a lot about this. But anyway, right? Computers need power, hardware, software. Humans need food, sleep, and many other things. So the question is not, okay, computers don't get exhausted, right? That's not true. Okay, and that's not a claim that I would make or anyone else would make. You have to maintain the computing systems. You have to, quality check them all the time. They need power. They need a certain, certain environment to be stored in. You need server connections. You need all these things, right? At some point, we have to, accept that, okay, either all this data goes to waste, or we need to train some machine to do our job, okay, of analyzing these data. Anyways, so what is the current landscape like? I see the third column is okay because of my camera. Okay, so what is the current landscape looking like? So first, let's, let me just do one thing. I'll keep my camera on and I'll just write AI here. Great. So first, a few words on what are these things, okay, so that there's no confusion. DS, data science, okay, it's science or scientific methods applied to data. And scientific methods primarily means what? It means using metrics to understand the data, rule, logic, metric, these kinds of things. So this is where your mean, variance, all those other things come from, right? And you can also conduct tests like hypothesis tests and various other tests, ANOVA tests, things like that on the data. And then you derive some kind of insight from the data. Okay, this data is telling me this data is telling me that. Deriving insights from data. That's what data science means. What is machine learning? We have seen till now. Machine learning is training machines to do these tasks, these and other tasks, by the way. So you're training the machine to actually automatically do these tasks. Once you train it, you're not required, so to speak. What is artificial intelligence? Artificial intelligence is much more complex. It is the attempt to impart intelligence to machines. You can say some kind of general intelligence. Okay, so that will take a while. That will take a while. As all of you know, generative AI has reached some kind of position in the course of technological development, right? But true, true, let's say proper AI, people are still trying to get to that, right? So that's that. So what about some examples of these? An example of data science activity would be, looking at historical sales data. You're just looking at some historical sales data of your company, and you're studying relationships between the different variables. You're doing correlation analysis, you're doing all sorts of tests and things like that, and you're seeing, okay, this variable is stronger, this variable is weaker, because of this happened. This is data science or data analysis. And in the same context, what's machine learning? So you might train a machine to predict the amount of sales in the next year. That's a machine learning example. Okay, you take the historical sales data, somehow train a machine using that data to predict the next year's sales. Okay, so that's example of ML. The same context example of AI would be, you might build a system that can apparently think independently and engage in decision making discussions with you, with the team, with the board of director of sales, so on and so forth. Surely we are very not yet there. Okay, we are not yet in this this state. Okay, we are getting there, everybody's working towards it, but we are not there yet. So data science, of course, is very well understood, right? It's mathematical methods proven and everything is established. Machine learning is also well understood to some extent, right? We know what's going on to some extent when we train machines, what they're doing, why they're doing. We know that, right? To some extent. AI is still being understood. We are still day to day, we are seeing, trying to understand what AI is. Okay. So data science, where is it used? Honestly, in this day and age, most domains and businesses have started using data science techniques, right? Most domains and businesses are using machine learning. Many domains, I will say, right? Long back I might have said few, but today I will say many domains and businesses are regularly using machine learning models. Okay. AI, as you know, slowly there is some kind of acceptance into the industry. Even now there are roadblocks. Is it okay to use this? Is it always going to be good for us? Whatever. So of course roadblocks are there. So slowly there is some pickup. Okay. Now on the academic side, data science has humongous amount of literature. Just paper after paper you will get, right? Machine learning, there's a lot of literature, and even now we are getting many papers in the machine learning domain, right? So there's really good amount of literature. There's more literature coming up in artificial intelligence domain right now. There are very few strong literature out there. One example would be, I think, the Google paper, attention is all you need, and transformers, things like that, right? There are very few well established papers, you can say, and of course more and more papers are coming up every day. Okay, this is kind of the landscape right now. So some applications of machine learning, training machines to learn, and I'm sure all of us can think of various tasks that machines, if I could train a machine in my job, then what is the first task I will allow it to automate, right? So all of you can answer this question in your own fields, right? So there's sales forecasting, as I told you before. Customer segmentation is so popular, right? It's almost bread and butter these days. Image recognition is very important. Face recognition, thumbprint recognition, all these kinds of things. Even voice recognition, right? These are all ML models, right? Sentiment classification. So automatic flagging of comments. Is this a rude comment or hate speech comment? Automatically you can classify it. You don't need humans to check. Automatically you can classify those kinds of things. Weather forecasts are mostly done by machine learning models these days. If you open your phone, you can check all the forecasts, and all of that is mainly coming through a lot of well-trained machine learning models. The field of medical diagnosis also is seeing some amount of automation. So obviously, I think all of us will agree, medical field is the field where you might find a lot of resistance to the acceptance of use of machine learning, and for good reason, right? We are dealing with human lives, right, directly. So surely there will be resistance from there. But even in the medical field, there is a lot of pickup in machine learning models. Okay, so diagnosis, automation, and all sorts of things. Of course, not replacing the doctor, not those kinds of things. I don't think we are there yet. Aided surgery, things like that are happening in certain places in the world, I believe. But diagnosis and things like that, a lot of automation, that is ML model, people are using. Then let's continue with machine learning paradigms. Okay, we till now we got a general understanding of what machine learning is, what we want to do, why we want to do. So let's see in the industry what are the technical things that we need to do. Okay, so there's a very, very common flow chart that you may see everywhere. It's called the industrial machine learning pipeline. Okay, so the machine learning pipeline, of course, there may be slight differences. If you Google this, you will get slightly different diagram, but more or less they are the same. Everyone's talking about the same thing. So, generally you start out by defining your problem statement, you gather your data, you clean, you pre-process, you explore. This is all data analysis, right? The whole left part of it is data collection, data analysis. Then what you do is you enter this pipeline wherein your first task is to define the machine learning task. Okay, what do you want your machine to do with this data? What do you want it to learn and to be able to do later, right? That's point number one. Then you choose suitable ML methods. Okay, and you will be able to choose suitable ML methods only after you have good experience with various ML methods, right? So currently we'll be getting into linear regression, then you will see logistic regression, you'll see decision trees, so on and so forth, right? So once you have an understanding of all that, then in this pipeline you will be able to choose which is suitable method, which is not useful method for that problem statement. Then, and by the way, there may be more than one suitable method. Of course, there are many methods available. You may pick 3, 4, 5 methods, whatever. So then you go and you build these models. Okay, and of course each model is going to have various things, various metrics that you may want to change, and you try to make that model learn in a certain way. Okay, what is it learning? It is learning the solution to the original problem statement. That's what it is learning, at least in part. So you build and you train these ML models. Finally, you need to evaluate these models. Okay, once you train it, we can't just be happy with the training. Okay, we have to test it. So that's called model evaluation. You test it on testing data, and there are many ways to test this. Once you are happy with the model that you have, then you are free to deploy, right? You can share it with the larger audience, you can host it, you can publish it, you can deploy the final model for use. Okay, so in this course the focus is more or less around these blocks, right? And we will go chronologically, right? That means, so model evaluation and choosing ML methods, of course we will not get into that right now. First we have to study various ML models, right? Then when you understand these various ML models, then it's easier. Okay, which model to choose, how to evaluate these models, right? So this is the focus area. So ML paradigms, machine learning paradigms, paradigms in the sense way of thinking, how to make machines learn. And that's exactly the question I've written here, right? So we are trying to answer this question: how to make machines learn. We know the goal of machine learning. We know, right? We want the machine to do certain tasks, identifying a rat, whatever it is. And if you want to think more reasonably about it, I want it to detect fraud transactions automatically. I want it to predict customer behavior for me, right? So we know what we want the model to do. How to do, okay, how to do and what we want to learn. So this part based on the problem statement, and this part how to make machines learn. There are different ways to think about it, essentially, and I have given on the slide four popular ways. One is supervised learning, one more is unsupervised learning, then we have semi supervised learning, and we also have reinforcement learning. Okay, I will touch a little bit on semi-supervised and reinforcement in this session, but the course will more or less be around these two paradigms, the most common paradigms, supervised and unsupervised. Okay. Okay. So what is supervised machine learning pipeline and why do we call it supervised? Okay. Essentially, what you're doing is you take your training data. Okay. So you suppose you have your data. So it's the same historical sales data or whatever, right? Suppose I take last year's sales data and I have 1000 data points from last year. This is my data. Suppose what I'm going to do is I'm going to break it into three parts. Okay, listen carefully here. I'm going to break these 1000 data points into three parts. Okay, maybe 800 data points here, maybe around 100 data points here, and 100 data points here. Three divisions. I will use 800 of these data points to make the model learn. Okay, how it is learning, the details we'll get into that later. But right now, assume that we are trying to predict sales. So I'm using last year's sales data, and of course, I have all the features. I have number of sales that day. I have the location, where was the product bought, what time it was bought, and various other data or information is associated with that particular sales. So like that, I have 1000 sales, right? So I'm predicting the sales using the other factors. Okay. So let me use 800 examples in my 1000 data points. Let me use 800 examples to train my model. How am I training? Some training algorithm. Okay, algorithm will change for different models. We'll study in detail later. But with some algorithm, I'm using these 800 training data to train the model. That's what's happening here. Then I want to see, is the model doing well? So if you see, I have split the other 200 into two parts, 100 and another 100. And if you notice carefully, I have not used these 200 data points to train the model. So essentially, model has not seen these 200 data points. Okay, the model has not seen. It has only been trained on the 800. So now I can use one of those 100, let's call it validation data, to see, is the model performing well or not. Now, if it is not performing well, then I can go back and improve my model. Okay, I will train on 800 in a different way. And then again, I will see, is it doing well on the 100. Then again, I'll go back and train it again in a different way on the same 800 data points. Again, I will check, is it doing well on this 100. Go on and on and on till you are happy. Okay. Once you're happy, remember there's another 100 data points which the machine learning model has not seen up till now. Okay. Finally, we can use that as the testing data. And once you test it, you are ready to deploy it. And deploy means what? You are actually going to use the model on new data, unseen data, okay, to predict, on the data points. the way I like to sometimes remember this is, board exam, school exam, that kind of thing, So we go through classes and then we do pre-board exam and then finally there's board exam. Okay. So the classes and the subjects that I'm learning in school or whatever, uh, these are my training data. Okay. They are training me. Okay. So this is my training data. Then the pre-board preliminary exam, it's a validation. Okay. So I'm writing my pre-board exam and I'm saying, am I doing well in this or not? It's a validation. If I didn't do well, I go study again, then I give my next pre-board, right? And on I do till I'm happy. Right? And then finally I go and I give the board exam. That is final test. After that, I am deployed into the world. Correct? So this is a very, I like to use this analogy because it kind of just fits perfectly, the whole supervised learning pipeline is exactly this. Okay. So notice that the validation data, you did not see the validation data, but it helps you to improve. But final board exam, which is testing data, there's no chance of going back. Okay. So I think this is understood. Even as a data analyst, data scientist, or ML engineer, if you want to deploy a model, essentially, the client is trusting you with the model, right? So just because it worked on your validation data, the client need not trust. It has to work on completely unseen data. Okay, which is exactly why we keep the testing data aside. So then I'll tell my client, look, I don't know what this data is. My machine learning model does not know what this data is. It performed well. So even in your case, if you are going to use on new data, it should perform well. Okay, that's the whole logic here. This is called supervised learning. Now, why is it called supervised? Because we are giving it 800 data points, and in that we are saying these are my inputs and this is my output, sales. So the model has the idea, for this data point how much was the sales, for this data point how much was the sales. So 800 such examples you have provided to the model. This is why it is called supervised. Same way, just think about it as a classroom. The teacher is giving you examples and showing you the answer. Supervised. All right. So just a quick snapshot example of the same here. So this is the same data set, I think, which has, every row seems to be a customer of some sort, right? We have variables like gender, married, unmarried, income, age, so on. And finally, there is this target column called expenditure. Now, maybe my problem statement is to predict how much is a new customer going to spend. So suppose these are like quarterly spendings or annual spendings of a customer in my on my product or in my shop or something like that. So you can see in the bottom, I have an unmarried female. In the bottom row, if you see, I have an unmarried female with a certain income of certain age. Question is, can I predict how much this lady is going to spend on my product? Can I predict? It's a new customer. Okay. So how would I build a machine learning model to do that task? Then if you see the top part, this much, if you see 1 2 3 4 5 6 data points on the top, I have singled it out as training data. So in this case, I'm going to show the machine, look, these are my inputs, gender, married, income, age, and in each case this was the expenditure. This is a historical past data. Okay, historical truth. So I'm showing this data to my model, and the model is learning that connection, that connection between this input features and the output feature. Okay, so for example, if you see here the fourth row, that's a higher expenditure, $100.7, and if you see the second row, that's a lower expenditure, around $60. Why is there this difference, and can you predict what is the difference? Okay, so we give these examples to the machine learning model, it learns some connection. Does it learn well or not? We have to see. Now, how to see whether it learned well or not? That is exactly why I have the validation data. Okay, so if you can see these two, I can then test my model on this validation data. Are you performing well or not? I can test it. Okay, if it's not performing well, we will go back and we will see what went wrong with my training method. things like that. I can change some things and maybe try to make it learn better. Then again I can check on the validation data. How to check? Well, we have the truth values here. We know the expenditure of these two data points, $74 and $69.56. So we know the truth. So we will use the inputs in the machine learning model and allow it to predict the number. If it predicts closely to my actual truth, then I will say it's doing well. Correct? If its prediction is far away from the truth, then it is not doing well. Okay. And finally, of course, you can just test it on one data point and be doubly sure that it is doing well, final board exam. Now, going ahead, when we start learning about linear regression and things like that, we will treat validation and testing data as the same. Don't get too confused at this point. The only reason to split test and validation is if you have a way to change your model. If you don't have a way to change your model, then each time you're going to get the same model. And if you're getting the same model, then there is no use of validation data. Okay. So when we first study, we will be studying very, very simple models where we don't have so much scope to change or tweak the model, but immediately we will get into those things, right? After 2 sessions or something, we will get into those things. What are the things we can change in the model? Then this validation data will be more useful. Okay, just wanted to put that out there. And again, I'm not expecting that we all understand this perfectly at this stage. Just keep it in your mind, and as you go through the series of lectures and all the demonstrations and everything, you will automatically start understanding what's happening where. Okay, so don't worry too much if you're not getting it fully in this session. You will get it soon. You will understand it very soon. Okay, so a quick summary of supervised learning. Supervised learning is generally intended to be used on new data, and soon we will see what is this classification regression, but essentially prediction. Okay, it's intended to be used on new data points for purpose of prediction, predicting the next sales, predicting the next temperature, so on and so forth. Okay, it has well-defined input and output variables. Okay, in supervised learning, this is my input, this is my output or target. This is what I am trying to predict. Generally, you split data into 2 or 3 parts. And in the future, when we cover more lectures, you will see there are ways to split in 2 parts and do, there are ways to split in 3 parts and do, so on and so forth. Not to worry about all those details at this point, but you will usually split it into training and testing. Okay. Then some applications. Customer lifetime value, right? This is the amount of revenue you are expecting from a customer and through the course of their association with your product or company. That's called customer lifetime value. Churn rate prediction, right? Whether a customer is going to cancel your subscription, right? Or whether they are going to not buy products from you in the future, right? That's called churn rate. You can use it for classifying sentiment of comments. I told you that before. You can flag whether it's a bad comment, good comment, happy, sad, satisfied, not satisfied, hate speech, so on and so forth. Yeah. Of course, this is in itself, it's a large field. This one, language processing, natural language processing, and text analytics. A lot of applications. Yeah. So posts, articles, comments, you can actually quickly sort through and flag, is it positive or negative review, so on and so forth. You also have recommendation systems, right? So which movies to recommend to which person automatically, right? Which series to recommend to which person, even in Amazon and all those things, which product to recommend to you. There are many applications of supervised learning. Some popular implementations of supervised learning is one, linear regression, logistic regression, decision trees, random forest, gradient booster trees, k nearest neighbors, support vector machines, neural networks, convolutional networks, recurrent networks, transformers, and so on. There are ample implementations, many different models. Okay, that's supervised learning. Now let's move to unsupervised learning. This is also a machine learning paradigm. Okay, this is also a way to make machines learn, but this is slightly different way. In unsupervised learning, if you saw the previous table of supervised learning, there were many things, training data, testing data, input, output, all those things were there. In unsupervised learning, there's no output and there is no testing, validation data, nothing like that. Everything in your data is input and everything in your data is training. So, okay, so what are we getting out of this? Well, actually, unsupervised learning is meant to uncover patterns from the data. Okay, natural patterns. So it's primarily intended to uncover patterns from the data. It's not intended for prediction of new data and things like that. There are ways to integrate new data in the process, but that's not the main intention. There's no target variable, there's no split of data, things like that. Now you might think, how is this machine learning? Now the example I use to understand this is, suppose that, just very hypothetically, suppose I'm thrown in a forest or something. Okay, I don't know how to survive in a forest. Did nobody told me, that this is the output, this is the input, this is how you should survive in the forest. Nobody told anything. I have to learn by myself, right? So that's kind of, I would say, a kind of unsupervised learning. I have to learn patterns in the forest. I have to learn, okay, many things. When do the insects come this way? When do, I don't know, tigers go that way? Whatever. Like, there are many things I need to learn myself to survive in the forest. So that's kind of how unsupervised learning is. You can think of it that way. Applications, well, there are many applications. So customer segmentation is one of the primary applications of unsupervised learning. This is done generally through clustering. You can also identify very strong relationships in data. Generally, this is done using association rule mining, which is also an unsupervised learning method. You also do anomaly detections, right? So some popular implementations are clustering, in that you have k-means, you have hierarchical clustering, so on, and association rules, things like that. Of course, supervised learning, there are way more types of models, right? In unsupervised, there are fewer models. That doesn't mean it is less important. It is used wherever the problem statement demands it. Okay, so that's more or less how unsupervised learning is. And just to go back to the diagram, as you can see, there's no target feature, there's no prediction, nothing like that. So what it learns from the data depends on the algorithm. For example, clustering tries to group the data. If you remember, we had the question, should I group it into 2 parts, 3 parts, 4 parts? How should the group be? Which customer should go in which group? You can do this automatically using k-means clustering. And you can also say that, okay, I can also do that automatically. Why I need machine learning model? I can just take some people and put in group, take some people, put in another group, done. Well, the machine learning model actually does it statistically so that all the groups are contiguous and tight. In a sense, a person from one group will be very similar to another person in that same group. So they'll be very similar. Then you can take proper interventions for different groups. Okay, this is exactly customer segmentation, how it works. So that you can have different interventions for different customer segments, which products to sell, how to sell, many of those kinds of things. So I am going to very quickly go over semi-supervised and reinforcement. I'm not going to go very deep into these, kind of out of scope for the course, but just quickly to touch upon. So in semi-supervised learning, essentially what's happening is, see, in supervised learning, we had all the training data, okay, and 800 data points or whatever it is. If you remember, we had so much training data, all the truth, we have all the truth values from the past. Okay, 800 sales value we have from the past. So we have enough confidence, when we train the model using 800, and I say 800, generally it's 8,000, 80,000, whatever. But yeah, so 800 data points, I'm confident. Okay, I'm very confident that my machine learning model is doing well. Suppose I don't have so many data points. Suppose it's very hard to get data points. So you can think of some examples like in the bottom right, certain areas of satellite images. I don't know, the near south pole of the moon. Recently, Chandrayaan and all we've sent there, right? Or backside of the moon. There are a lot of cases where getting data is not easy. And even if you think of very specific text data, just because you Google something doesn't mean you will get the exact kind of text you're looking for. So there are a lot of domains where the kind of data you're looking for is very difficult to get. Okay, so some of examples I've given you. In those cases, whatever you have, you first train the model. Okay, whatever you have, you train the model. Then you allow the model to predict for some unknown data. Then you use the prediction as truth. After doing the prediction, combine it with your original data and use that bigger data set as the truth, and then train your model again. So it goes in like these iterations. Okay, that is semi-supervised learning. Reinforcement learning is a different way of making machines learn. Essentially, it's based on reward and punishment. Okay, so some domains where these kinds of techniques are used. So we were essentially discussing ML paradigms, right? We were mainly focusing on supervised learning and unsupervised learning. Supervised learning being where we show examples to the ML model and train it to think and find out the connection between the input and the output. Okay, that is supervised. And unsupervised where there is no input output and we just want the ML model to uncover patterns from the data. So now we'll go a little deeper into supervised learning, which is primarily what we'll be focusing on for a while in this course, and we'll go a little deeper into that. So let's look at the types of supervised learning methods based on the task at hand. Now, if you see on the top half, there is something called classification, and if you see on the bottom half, there is something called regression. Classification and regression both are kinds of prediction. Okay, both of them are predictions only. In classification, you are predicting a categorical variable. So you are predicting some kind of label. If you see the kind of task, maybe something like look at the picture and identify the animal. Okay, whether it is elephant, giraffe, or sloth. So this is called classification. Another example will be identifying the sentiment of a comment. So if you see here, I have a data point which says, what an amazing movie. I have another data point which says, what a waste of time. And I have another data point which says, I don't really care. So by taking in these data points, can we identify the sentiment? That is it good comment or bad comment? Okay. So you are producing categorical labels. Okay. You're producing categorical labels, producing or predicting. In the regression case, you are predicting numerical values. So one example is, for example, forecasting temperature or sales, whatever, right? So if you see, these are all future data points and we don't know the value, but these are forecasts. You are forecasting or predicting the future temperature. Similarly, you have expenditure prediction, say how much your potential new customer, how much they are going to spend on your products, right? So this 38-year-old lady, we have 36-year-old man, how much will they be spending on your products in the future? So that is a numerical prediction, correct? You are predicting a value amount. So that is a kind of regression, right? That is what we call regression. So primarily supervised learning is broken down into these two kinds of tasks. Okay, so a few more examples on classification. As you can see, take this case where you have a comment, you have some kind of comment, that was such a nice movie. So then that goes into the ML model and the ML model says positive. This is the predicted label, right? So this comment was input to the ML model and the output was the label called positive. Okay, so the ML model is saying this is a positive comment. Another example is, suppose I take this image and this whole image I just give it to the ML model and the output of the ML model is park. So this is called image captioning, by the way, right? So you give an image to an ML model and it produces labels or captions for you. That is also a kind of classification. So out of a list of labels, it is choosing one. So maybe I have park, in the labels. Maybe I have road, those kinds of things. So it rejected other labels and it selected park as the label, which is also classification. Okay. And another example, if you see here, I have a customer, it seems, unmarried lady with certain income of certain age. I passed it through an ML model. This observation, this data point, I passed it through ML model, and the machine learning model predicts that this person will opt for credit card. So the output in this case is either yes, the person will opt for the credit card, or no, they will not opt for credit card. Notice that all of these outputs are categorical levels. These are not numbers. Okay, the outputs are not in numerical scale. These are all categories: park, road, yes credit card, no credit card, positive, negative sentiment. These are all categories. So this is called classification, when the machine learning model is predicting categorical labels or levels. That is called classification. Now, generally in classification, we break it into two kinds. One is binary classification, which is the simpler or the simplest version of classification, where the target variable has two levels. So for example, you have, say, male and female, that is two levels, right? Positive, negative sentiment, that is two levels. Fraudulent or legit transaction, that is two levels. This is binary classification. Multi-class classification is the case where you have more than two levels. Okay, so maybe you want to predict whether tomorrow is sunny, rainy, cloudy. That has three levels. Maybe you want to predict whether a certain customer segment will prefer tea, coffee, milkshake, or something else, right? So 4 or 5 categorical levels. So you can have multiple levels also when you're predicting. That is called multi-class classification. Okay. A quick use case of classification, just to set some context. So suppose I have my data set here. Okay, and this is the historical data set of customers of my bank, and whether they opted for credit card or not. Okay, so these are my existing customers. So for example, the first row is an unmarried man of certain income and age, and that person has opted for credit card. I know that because that person is my customer. Same way, I have so many customers and I know which customer has opted for card, which customer did not opt for card. So then as the bank, what I can do, I can build an ML model that classifies a new customer based on their details, whether they will be open for getting the credit card or not, right? And once I have the answer, then I can make interventions. So for example, you take these last two data points, which are new customers. Suppose my ML model says no here and yes here. Okay, so it says no for the man and yes for the lady. So if it was a no, just see the second point in the bullet point here. If the ML model predicted no, then I will go and take feedback from this customer. Why did you say no? It's a good bank, you've been with us for like 3-6 months, you're using our services. Let me explain the credit card more to you, right? So you can make a specific intervention for the person who the ML model said no, that they won't be open for credit card. Now suppose the ML model predicts yes. So if you see the second unknown or unseen new entry, the lady whose historical data we don't have, right? Suppose the ML model predicts yes, then I can have another kind of interpretation. I can just directly go to that person and say, hey, look, we have very good credit card option. Do you want to have a look at it? So you see, it is allowing me to optimize my time and resources. And this is exactly why ML models are being used in all the kinds of businesses everywhere. It's for optimizing efficiency, right? So this is a good use case of classification. Let's look at regression next, right? So again, some examples. If you see the data point on the top, this is a data point about a certain property. So it is a certain property in a certain area, certain flat or apartment. It's a 2 BHK. It has certain area, 1200 square feet, some ceiling height, age of the building, whatever, right? So you have all these kinds of data, and you're using the ML model to predict the selling price of that flat. Okay, so you have some kind of historical data in which you know, okay, this area this much square feet, this is the price, this area this much square feet, this much age, this is the price. So you have all these historical data. Then if you have a new flat that you're looking at and you want to predict the price, you can train your ML model on the historical data and allow it to predict the price. Okay, and in another example you can see there is a lady with certain income and age. Now suppose this is a customer of your bank or company or whatever, right? So you use an ML model and you are predicting the lifespan of that customer in your company. Now lifespan means how long they will be associated with your company as a customer, how long will they enjoy your products, right? That's called lifespan, customer lifespan in business language. So your ML model can also be used to predict that. Note that in both these cases you are predicting numbers. Okay, you are not predicting categories, you are predicting numbers. So you're predicting numerical values. Right? This is called regression. Now generally speaking, I told you that classification and regression both are called prediction, but in many international circles classification is called classification and sometimes regression is called prediction. But I hope it is not going to cause any confusion to anyone. It is very clear. Classification is predicting categorical levels, or you can say qualitative variables, right? Regression is predicting numerical or quantitative variables. So a quick use case, again you take the same bank data set, okay, and instead of whether the customer opted for credit card or not, right, instead of that feature you now have different feature which is lifespan, customer lifespan. So for example, here you have this unmarried male of certain income age and they were with your bank for 12 years. If you see the second entry, there was a married male with certain income and age and they were with your company for 7 years, so on and so forth. You have the customer lifespan of all these different historical customers. Now suppose you get two new customers, okay, and in the bottom row as you can see there are two new customers. So you can now use this historical data to predict how long these new customers may be associated with your bank. And then again, after understanding the kind of predicted lifespan of such a customer with your bank, you can have specific intervention measures. For example, suppose the married male, it says 5 years. Okay, the prediction from the ML model is 5 years. And suppose the unmarried lady, the prediction is 15 years, suppose. So think about it yourself. If you are a bank manager, okay, or you're managing the various services like loans, credit cards, things like that, your ML model is telling you this man is going to most likely be associated with you for 5 years and the woman is most likely going to be associated with you for 15 years as a customer. Let's try to participate in this. Yeah, wow. Am I reading correctly or is all these answers are the same? All the answers are the same. Okay, let me do one thing. A, using the fingerprint to identify them, everybody is saying classification. Okay. B, predicting temperature for tomorrow, everybody is saying regression. Okay. C, predicting the number of votes that somebody will get is regression. Okay. Using DNA sequence to determine what type of genetic disease one might have, everybody is saying Q. Okay. Attempting to identify is also Q. I think this is right. Yep. ADEQ, BCR. Wonderful. I think we are getting the hang of what this is, right? Which is classification, which is regression. Great. So a quick summary of everything that we learned, at least in the introduction to machine learning part. So ML is basically an engineering domain, okay, where you enable machines to learn and then you train the machines to perform tasks and solve problems for you, right? So it's a very technical and engineering domain. You can broadly classify into supervised, unsupervised, semi-supervised reinforcement. These are the most popular ways of looking at it. And supervised, we saw it's broadly classified into classification. Regression, we understood what is classification, what is regression. And I would like to say one statement in the summary before we move to linear regression. The ML pipeline is very well defined and can and should be followed for almost every project. Okay, and when I say ML pipeline, I'm talking about that flow chart, right? You can Google it yourself, you'll find many variations of the flow chart, but this whole pipeline is very well established, well defined, and you can and should follow it for every ML project. Great. So we'll move to the final phase of today's session, which is a very what do you say, soft introduction to linear regression. In the next session, we will get into the details and all of that. We'll do a lot of things in the next session. We'll softly look at it. Okay, we'll try to get a sense for it today, and then we'll pick it up in the next session. So quick introduction. Why consider linear regression and what is linear regression? See, generally speaking, many real world quantities are related proportionally, okay, directly or inversely. So basically, in other words, there is a positive correlation between age and expenditure, or there is a negative correlation between age and expenditure. Generally speaking, there is some kind of proportion. If this is less, this will be more. If this is more, this will be less. Okay, generally speaking, we see this pattern. So for example, sales as a function of money invested in resources, inventory, infrastructure. So you invest more money in resources, does your sales go up or down? Either it goes up or it goes down. More money in the inventory and infrastructure, does your sales go up or down? It may go up, it may go down. But generally, these are proportionally related. Depending on your domain and your problem statement, it may be inverse, it may be direct proportion. Similarly, sales as a function of product pricing, this is very straightforward, right? How you price your product and how much it actually sells, right? So either it's a good relationship or it's a bad relationship, so on. So there are many real world examples where such simple relations do exist, and linear models are very simple and easy to interpret. Okay, and they are often representative enough of certain real processes. When I say representative enough, I mean it's good for a start. You can say it's good for a start, right? The biggest plus point is that linear models are very simple and very easy to interpret. So let's quickly revise a familiar equation from school. Maybe many of us want to forget this kind of equation, but it's in the front of your screen. But I suppose we all remember this equation, v equal to u plus at. Okay, so suppose your initial velocity is u is 5 meter per second, acceleration is 10, whatever. So this is the formula that you get, v equal to 5 plus 10t. Now my question is very simple. If you want to predict the future velocity of this vehicle, can we use this equation assuming there are no other variables, right? So if you see here, I have put a small cap on the v. You can see there is a small cap. Cap means prediction. Okay, so cap on v means predicted v. So can I use this equation? 100% I can use this equation, right? Full confidence. We all will use this equation. My car has this much acceleration. This is the initial velocity. What's going to be my final velocity in 10 seconds and whatever it is, right? So it's a very, very well established equation and we don't question it and whatever. So essentially, you can say that learning or knowledge has been encoded into this equation, right? The equation itself carries knowledge. The equation itself carries knowledge. Where is that knowledge? So if you look closely, you will see there are two things. I have written here one thing. I have written what the information or knowledge is stored in the coefficients 5 and 10. Okay. So the knowledge is obviously stored in the coefficient. If the coefficient was wrong, then your prediction will be wrong, and whatever is going to happen to your car, I don't know, right? So the coefficient better be right? Better be the right value, correct? So 5 and 10 is where the learning happened. But there is another aspect to this equation which has captured the learning, which is the structure of the equation, which is the linear relationship. So we are not using v equal to u into at. We are not using v equal to u power at. We are using v equal to u plus at. There is a linear relationship between the variables here. Okay, so there are two things happening. One is the structure of the formula or the computation, the structure, and the other is the numbers or fixed numbers in the structure. These two put together is what you call a machine learning model. Very simply put. Okay, great. Now that's a very familiar equation. This equation is probably not familiar to most of us, right? If you see, I put the equation here. Here y cap, that is the predicted y value, is the quality of some wine. Okay, so in fact, in 1990 there was this economics professor at Princeton, Ashenfelter. You can Google this also. Okay, there are a lot of articles around this. So this professor announced that he can accurately predict wine quality without tasting the wine, even without the wine existing, basically. So if some of you are aware, there are, wine is a big domain in itself, and there is huge amount of business, in wine. Is it good wine, bad wine, whatever? And there are specific specialized roles called wine tasting, right? People taste the wine to then judge it's it good or bad wine, and then you price the wine. Okay, so you create the wine, you then test the wine, you taste the wine using tasters, then you price the wine. It's a large process, right? It's very large process, and this professor came out with an equation saying I can predict the quality of wine without tasting the wine. Right, and the equation he came up with was like this: y cap equal to, and I'm not going to read out all these numbers, but what you are maybe interested in right now are these x values. Okay, what are these x? Coefficient carries the information, but x1, x2, x3, these are the structure part, the variable part of the model. So x1 was the amount of winter rainfall. So this is basically when they grow the crops for the wine, right? So x1 is the amount of rainfall that the crops get in winter. X2 is the average growing season temperature. Growing season, okay, what's the temperature? X3 is the amount of rainfall in the harvest season, and x4 is the age of the vintage. So the professor found out these four variables, right? Put them in this linear model, gave these coefficients, and these predictions were more accurate than experts. Okay, these predictions were more accurate than experts. So this equation is less familiar, but it's more or less the same concept. A linear relationship between input variables and the target variable, the prediction, the required prediction. Okay, and this was so accurate. So if it is so accurate, so what? This means what? This means that what the large process I told you about, testing, tasting, and all those things, if you are confident enough in the equation, in fact, you don't need those wine taster, you don't need all that. Directly use this equation, right? So I would urge people to go read more what this professor has done and what happened and all that. Okay, so this is a classical case of linear regression. So now the main question is, where are these coefficients coming from? Because in the previous case, this 5, this 10, we knew initial velocity, acceleration, whatever. Either it comes from physics or it comes from me, whatever. But where did these coefficients come from? How do I know how much winter rainfall is going to affect the quality of the wine? I don't know, right? So is there a way to train a machine learning model to learn these coefficients? Yes, that is called linear regression. Okay, so going ahead, in this session, next session, and some of the other linear regression sessions, right? I will be using a very small data set for discussing concepts. So if you see here, this is my sample coffee expenditure data set, and the features are blocked. Let me turn my video off. Yeah. So here I have, like, I think 10 people. These are customers, and I have the gender, I have the job, I have income, I have age, and I have the amount of money that they spent on coffee in the previous year. Okay, and like this I have 10 data points. So this small data set is something that we will use to discuss concepts, and for demonstration and coding we will use a larger, more complex data set. Okay. Now in this data set, as you can see, I have the index, which is the name. I have features on the left side. You can see the table which describes the features. I have a binary gender. I have a multi-class or multi-category job feature. I have a numerical integer, which is income. I have numerical integer age, and I have amount spent on coffee, which is also numerical integer. You can see the units here and all that. And since this is a very small data set and very just for discussion, I am using this data set. So I'm using integers. Okay, I'm not using float numbers and all. When we work with the complex, more realistic data set in the demo, we'll be using real data. Okay. Now let's get back to this small data set and start forming our ideas about linear regression. Okay. So there are 10 data points. As I mentioned, there are 10 data points here. You can see the names of the people and all. And there are 5 features. Okay, gender, job, income, age, amount. Note that amount is also feature. Okay, just because your output is called output or target or whatever does not mean it is not a feature. It is still a feature of your data set. Okay, so that is your output feature, which is what is here, output feature. And the other things you will treat as input feature. Now, which one you are treating as output depends on you. Okay, in my problem statement here, I am interested in predicting the spending of new customers on my coffee, right? So for me, amount is the target feature. So that depends on the problem statement. Now these 10 data points, if you remember, we will be using these to train the model, and the expectation is that the model learns the relationship between the inputs and the output. So the model should learn the relationship between gender and amount, job and amount, income and amount, age and amount, right? So input to output, that's what the model has to learn. And you may ask a question, why not use correlation or something like that? You can use, if the question is what is the relationship between gender and amount, or age and amount, spent on coffee, whatever, you can use correlation. You can even use bar graphs, right? If you're using categorical variable, you can use bar chart, no problem. The problem is that it's an analytical metric. Correlation is analytical, not predictive. Your correlation is not going to tell you how much your new customer is going to spend on coffee, right? Correlation will not give you that. So correlation can give you useful insights. It is analytical metric. It can help you build the ML model, but it is in itself not a machine learning task. Okay, using correlation. So what exactly is a linear regression model then, right? As we said before, you treat y as a linear combination of all your x variables. So the general equation looks like this. Okay, this one here. Y equal to some constant beta naught plus coefficient 1 into variable 1 value plus coefficient 2 into variable 2 value, and so on. This is how your linear model looks. So here y is the target variable. In my case, it is the amount spent on coffee. And you have x1, x2, x3. These are the predictor variables. You can say input variables also. These are my gender, job, income, and age. And these beta naught, beta 1, beta 2, beta 3, and so on. These are the coefficients which store the information, that is the relationship between the input and the output features. Okay. What is simple linear regression? Now in linear regression there are two kinds. One is simple, one is multiple. In simple linear regression, you are using only one predictor to predict the target. So in that case, you will call it a SLR, simple linear regression. So in this data, you can see I am using the income as my input to predict the output amount. So the equation is going to be very simple. Y equal to beta naught plus beta 1 x. So in this case, it will be amount equal to beta naught plus beta 1 times income. And my job is essentially to find these two values, beta naught, beta 1. Okay. If I put random values, I will get bad prediction. So obviously we need to find good values. Similarly, you can also have simple linear regression for other input variables also, like gender. Okay, now gender is categorical. What to do about it, we will see that later. Okay, but yes, there are ways to encode categorical variables into linear models also. What about multiple linear regression? So in MLR, that is multiple linear regression, you are using more than one predictor to predict your output. So in this case, if you can see, I'm using income and age both to predict my amount. So general equation is here, y equal to beta naught plus beta 1 x1 and so on. So in this case, for the income and age, this is your equation. Amount is equal to beta naught plus beta 1 times income plus beta 2 times age. And of course, you can add more variables. And again, the job is the same. You have to find good values for these coefficients. Okay. So when we talk about linear regression, we are primarily talking about fitting lines. Okay, we are primarily talking about fitting linear shape to the data. So suppose I start with the numerical predictors in my data set. So I have income here, I have age here. My target is amount. Okay, so if you see here, I have a scatter plot of age versus amount. Okay, this is the age of the customer and this is the amount they spent on coffee. Now you can quickly do a correlation of these two features, right? You just take these two columns and you find the correlation. Turns out the correlation is about 0.32. This is not a weak correlation, but by no means is it a strong correlation. You can say it's not so strong correlation. Okay, and you can see the scatter plot here. Yeah, age is on the x-axis, amount, the target is on the y-axis. Okay, so if I want to start fitting a line, I can fit a horizontal line. Now the horizontal line where I should fit, maybe I just take the average. So look at the data set on the right side. Suppose I just take the mean of all these things. Aarti spent $2264, Darshan spent $1976, Isha spent $1702, whatever. I add all of these things and I take the mean. Okay, and the mean of this comes out to be around $2000 or whatever. Okay, so let me just predict the mean for the new data. So what I'm trying to say is, in these 10 historical data points, the mean expenditure was $2000. So if a new data point comes, I will predict that they will spend $2000. Okay, because my past 10 data points averaged around $2000. Therefore, my new person also will be spending $2000. This is not wrong, right? This is not wrong prediction at all. It is a weak prediction, but it's not a wrong prediction. It's a reasonable way to think about it. Last year, my average sales was so and so dollars. This year also, it's going to be so and so dollars. What is so wrong about it? It's not wrong, but it is weak. Okay, it is very simplistic, weak prediction. So you can fit a straight line at the mean value. Okay, any new data point you can predict mean. So suppose here I have age 56, 35, 42, 32. Suppose I have somebody who is 45. Okay, see the graph. New person whose age is 45. So I just go directly from the point in the y-axis, and wherever the line meets the model, I will take the y value, which is 2000. This is going to be same for everyone. Any new customer who comes, I'm going to say, okay, you're going to spend $2000 on my coffee. I hope it's clear. This is not wrong. Okay, it's just a very weak way of predicting. What's a better way? So were we satisfied with that horizontal line? I don't think so. Okay, what's a better way? Now suppose I find a better line. So the horizontal line is also a linear relationship. Okay, in terms of equation, what does the horizontal line look like? In terms of equation, if you see this y equal to beta naught plus beta 1 x, the horizontal line refers to just constant. Okay, the beta 1 x term is not there, just constant. That's the horizontal line. But can we do better? Question is, can we do better? Yes, little bit. If you try to fit the line, so that the it's somewhat following the pattern in the data points, maybe your prediction is better, maybe. Okay, so question is, are we happy with this line? So how are you going to find how whether you're happy? You have to find the predictions and you have to see, are we doing well or not? Okay, why should I stop at linear equation? Why can't I go for a quadratic curve? So as you can see in the graph now, I have a quadratic curve. There are many reasons in this case why you should not go for quadratic curve, because outside this age the quadratic curve will be exponentially increasing and it will give meaningless predictions. Below this age also it will exponentially increase, it will give meaningless predictions, right? So it will give meaningful predictions for very short range in your data, it won't give meaningful predictions for full data range. That's one problem. Another problem is, why do you need more complex equations if you can model it more simply, right? So maybe after making your equation more complex, still your predictions are still okay, then what is the point of making it more complex? And you can even ask the question, okay, I'll make it even more complex, right? Now I'll fit a cubic curve. If you see the scatter plot now between age and the amount, the same data, cubic curve seems to be doing pretty well, okay? But are you sure that this is good enough? And usually, and it's not visible here, we will discuss this later in regularization and certain topics. You are overfitting your data, okay? You are fitting your model so closely to the data that any new data point you're going to get bad prediction. This is called overfitting. We will learn about that later, okay? Point is that you're making the model unnecessarily complex at this stage, okay? So there are many of these questions that you have to deal with, okay? Now in this case, okay, I put a summary table here which is better, so you can see the arguments for both sides. I have lines on this side, curves on this side. Lines are very simple model, curves are complex equations. Computations in lines are faster, curves will have slower computations. Lines may be too simple to model some kind of data. Of course, definitely linear relationships are simple. Maybe there are data whose relationships are more complex, right? But curves, what will happen? Maybe the curves are so complex that it's fitting your data so perfectly, right? New data, it's not even able to predict properly, right? This is something called generalization. We will see that later. But I think I can simplify it by saying I have 10 data points. If I overfit my model to 10 data points, what happens to my 1000 unknown data points, right? It's like saying, if I study for my board exam from only one book and I will not look at any other book, I will only study one book, I will score 100 on 100 from that book. Is that a good way to handle your board exam? No, right? You need to generalize. So these are the kinds of uh, questions you will have when you have to choose which kind of model, okay? Lines, generally the range is somewhat more under control. As I told you, it will not go outside the graph and things like that. So in quadratic case, very easily it will go outside the graph. In cubic case, in fact, this is going to go down to negative. On the left side it will go negative, on the right side it's going out. So there are many problems with complicated models. So I would like to say that, see, honestly, it depends on the problem statement that you're trying to solve. But generally, trying out a linear model first is not a bad thing. Generally, trying out a linear model is almost always a good way to analyze your data and try to see, is it a decent model or not. Okay. So previously, we saw age versus amount spent on coffee. Here we are seeing income on the x-axis versus amount spent on coffee on the y-axis. It's quite clear that there's a linear relationship. It's very clear. You can see in the screen. And in fact, the correlation value also tells you 0.87. It's a very high correlation, right? So again, you can start by saying, I will take the average of the amount. I will take 2264 plus 1976 plus 1702. I'll find the average. And then I'll say, okay, last year my customers average spending was $2,000. So whoever new customer comes, average spending is $2,000. I can say that. Question is, are you satisfied with this model? And most of us should not be, right? We should not be satisfied with this model when there is such a clear linear relationship. So then the next best thing to do is, okay, let's try to fit a line to this data. What do you mean by fitting a line? Where there is no real value you can predict. So using the, I think we have income here on the one of the columns. Yes. So RT has income of 64563 and amount spent on coffee was 2264. So that is probably somewhere here. I guess this data point is RT, right? Now suppose I get somebody in the future who is whose income is $67,000, right? So they on the x-axis they will be here. Then I can use the formula, right? I can use the formula to get the predicted amount of money they will spend on coffee. Okay. All right. So that's kind of what the linear regression model looks like. It is a machine learning model. We know the structure of the model. We know what coefficients are there and what are our variables, right? And as I told you before, the cap on the y means it's a predicted value. Yeah. So where is the learning happening? It's happening in the coefficients, right? Beta naught, beta 1, beta 2, and so on. These coefficients, this is where the learning is happening. These are called the parameters of the model. Okay, this is a technical term. As we go into other models also, each model is going to have parameters. Models are also going to have hyperparameters. Many of you may have heard of these terms. We will see in detail what is the difference between parameter, hyperparameter, and all those things. And finally, if you have a new data point, once you have your good equation, right, once you have the correct coefficient values for your model, you can use it to predict any new data point. Okay, so then that raises the question, what do you mean by good coefficient? That's the only question left that we have to answer. What do you mean by good beta naught, good beta 1, good beta 2? Where do we get that from? So we know that the target variable is a linear combination of the predicted variable. This much we know. It should be the best fit for the data. Best fit means what, right? Where is the good coefficients coming from? What does best fit mean?
In today's rapidly evolving business landscape, machine learning and AI are no longer buzzwords. They are essential tools for staying competitive. Are you ready to lead the AI revolution in your industry? Upgrad, in collaboration with IIIT Bangalore, brings you the Executive Diploma in Machine Learning and AI. This program is designed for ambitious professionals like you, seeking to leverage AI for strategic decision-making and innovation. Gain hands-on experience with cutting-edge technologies, learn from renowned faculty, and network with industry peers. Elevate your career, drive business transformation, and position yourself as an expert in AI. Enroll today and future-proof your career.
So the agenda for today. So first, what we are going to do, see, we are going to study simple linear regression using numerical predictors. And then we are going to get into model evaluation. So as we have mentioned before, linear regression is a machine learning model, right? So we saw in the previous session that there are many machine learning models and each model has to learn, right? In the previous session, which is a very fit comparison, which is doing the tests, weekly tests, assignments in school, and then the pre-board examination and then the board examination, right? So through that we know, are we doing well in a subject or are we not doing well in a subject? So model evaluation is a very central theme and an important part of machine learning. We need to evaluate how well the model has learned. Now for linear regression, we will see two ways of evaluating the model, right? One is goodness of fit and other is predictive power. We will get into this in more detail. And of course, finally, we'll spend some time doing the Python demo. So first, let's refresh the simple data set that we saw last time, right? So here, these are my data points. I have 10 entries: Arti, Darshan, Isha, Gayatri, and so on. I have their features, that is gender, job, their income, their age, and the amount spent on coffee. Basically, it's telling me the so the data is basically the amount of money spent on coffee in the previous year in dollars. Okay, that's what this data is. So in this session, we will focus on these input variables. Okay, income and age. Now, as we mentioned before, If you're using only one predictor, it's called SLR. If you're using more than one predictor, it's called MLR. So here, if you see what could be, the equations, right? So it should be of the form y equal to b naught plus beta 1x. We remember that beta naught and beta 1, this is where the learning has to occur, right? Good beta values will give you good predictions. Bad beta values will get bad predictions, right? So what could be sample models? So this is one example model. So if you can predict the amount spent on coffee using the income of the person, then the question is, what should be these beta values? Similarly, if you're trying to predict the amount spent on coffee based on the gender, then the question is, what are these beta values? Similarly, you have the same kind of thing happening in MLR as well, multiple linear regression. Okay. If we remember correctly, we also saw best fit line, right? If you remember this, we had the scatter plot of the data, right? And then we said, let's go with a very naive or very simple prediction, that is, just take the average of the past data set and predict that average value for any future data point, right? And if you remember, we said that's not wrong, but it's not good enough, right? That's not wrong at all. The what you say, the thought process or the motivation behind that is pretty correct, right? This happened in my last year, I will say average will happen this year, right? Nothing wrong about that. But it was a simplistic model, very simple model. So we could just change the slope of the line and try to fit it to the data better, right? So instead of, if your data is like this, right, if your data is having a slope like this, why should you go for a horizontal line? You can get better prediction with a line which follows the slope, right? So that is called a simple linear regression model. So suppose we are dealing with the same data set, right? And suppose my target variable is the amount of coffee that is spent by the customer, right? And suppose we have two linear combination equations. You can see here I have one in green and I have one in red. Okay, now let's not worry where the numbers came from. First, let's try to compare these two. After that, it will be easy to understand where the numbers came from. Okay. So if you see the green one, it says predicted coffee amount is equal to 50.13 plus 0.032 times x. What is this x? Now, as I said, you can have different input variables, right? Now, we are selecting income to start. Okay, we can start with income. So that's only one variable. In the data set, let me just close the camera. Here is income, right? So I am using income to predict amount. Okay, x is predicting y. And what is the other equation? The other equation is 399.77 plus 0.026x will be equal to predicted coffee value, right? So if somebody new comes, if some new person comes and I know their income or something, right, then I can use that to predict the amount they will spend on coffee. I can predict using both these equations. I can predict using infinite equations. The point is how to find out which is the best equation, right? So this is actually so this green equation, right? This 50.13 plus 0.032x. Okay, the equation is here. So this is the line, right? This is the line fit with x-axis income and y-axis amount, right? So this is my predicted amount on coffee, and this is my income. Now, if you just use this equation to build a straight line on the same scatter plot. So what is the scatter plot? It is showing income versus amount. Okay. The whole idea is I want to use income to predict amount. So for example, if somebody's income is 67500, right in between 65,000 and 70,000, how will you use this to predict? So you'll just go up here, meet the green line, and then go to the left. So this looks like around $2150 or something like that. Same thing, you can put the value in the equation, right? So you put that x value in the equation, you will get the prediction. One thing you should note is that the green line, or any line for that matter, it's never going to go through all your data points. Okay, sometimes I've come across certain questions that why the prediction model is not predicting 100% accurately for all my training data. That's not possible, right? The model is simplistic, it's a straight line. So if your data points do not lie on a straight line. Now you see the blue points, see all the blue points. Do you think they are on a complete straight line? No, right? We are trying to find the best straight line. There may be many straight lines. We are trying to find the best straight line, not the perfect straight line. There's a big difference. Yeah, best straight line, not the perfect straight line. So that is why, of course, when you try to repredict, then also there will be error. Okay. So for example, if you take this x-axis point, right in the middle of 55 and 60,000, maybe not Darshan, maybe Lokesh. That value looks like it is the entry Lokesh, right? 57398. Okay, that is here. So if I go up here, it is actually falling short of the prediction, right? You are getting 1810, something like that. But what is the actual amount spent on coffee by Lokesh? Look at the data. It says $1886. So we fell short by $70. Okay, so I hope that makes sense. You're not going to ever get a perfect straight line that goes through all the training data, because naturally real data is not going to sit on a straight line like that. Okay, now here is the red model. I showed you the green model before, and here is the red equation and the red model. And as you can see, so for the red model, again, see, this is the truth value. Okay, so if you go to the previous slide, green model, these two are historical truths, right? These two, income and amount, this is the actual data from last year. So that is obviously the same. Even in the red model, it's the same. These are the actual data points, like RT with an income of $64,563 has spent $2,264 on coffee last year. Same way, Lokesh with an income of $57,398 has spent $2,001 last year on coffee. Now this red model, what is it predicting for Lokesh? So all you have to do is take this number 57398, correct? That's the income. You put it in X, and then you just calculate the predicted Y. Visually, what does that look like? As we saw last time, it goes like this, right? And then you can find the value here. Again, it is falling short. As you can see, it is falling short from the actual value. Okay? And for some other values, you may be over predicting also. For example, you check this data point. Okay, so this is around 64 something income, looks like Hemant or RT, might be one of them. Okay, so these guys, right, actually you can find out who's Hemant, who's RT, because RT and Hemant have almost the same income, 64,563 and 64,465. But if you see the actual amounts, that will help you, right? RT spent 2264, so obviously the point on the top, this is RT, and Hemant spent 1754, so this is Hemant. So interesting, right? In the case of Hemant, you have over predicted. In the case of RT, you have under predicted. So if you use 64, around 64,500 as your input value for a new person, right? It is an error from both sides. Anyway, so the major point that I wanted to drive was that many lines and no line is perfect. These are the two major points I wanted to drive. You can fit many kinds of lines with different intercept and slope, and not a single line is going to be perfect. But the question is, can we ask the question which model is better? Clearly one model is better. Like, of course, green and red, these two models look really the same. But if I just showed you, a line like this, you would say, okay, this line is very bad, right? For the same data, if I showed, let me just draw that line on the left side. Suppose I had a straight line which was like this, right? So suppose this is my linear model with a different equation, of course, right? So suppose this is gray or blue color, whatever it is, right? So suppose there was a third model with this kind of equation. You would say it's a bad model. Rather than this, I can just use the green model or the red model, right? So obviously, there is a finite number of models or a single linear equation which gives you the best results. Intuitively, we know. Now, the problem is if you try to do it manually, visually, intuitively, it's kind of impractical, right? You're not going to find a universally correct answer which you can discuss with other data scientists, other mathematicians. There's no such like if you say, okay, for me green is better, for me red is better, what is the algorithm that we are using, right? So this is where we need to start thinking in terms of errors. Okay, so if you see in the two graphs, So this is the green model and this is the red model along with the predictions. So by now I hope we understand that the predictions of each of these models is the colored line. So in this case, the green color line, this is giving you the predictions. In this case, the red color line, that is giving you the predictions. Okay. And what you can see is for each of the 10 data points, so you have 10 data points, right? Each of these blue color points are your data points. This is your data point, this is your data point, this is your data point, right? For each of these data points, both models are off, right? The predictions are off. For each data point, you can calculate this error. Okay, so if you see on the bottom of the screen, all you need to do is find y minus y cap, which is true value. So this is the true value, historical truth, minus predicted value. Okay, this is the predicted value. So obviously, the larger the difference, the worse the model. Pretty simple. If your prediction was close to the truth, then y minus y cap should be small. And we want this to be small for all the data points, which is why we are doing summation. If you see in the end, there is sigma. Okay, summation. And generally, we do not care whether you over predict or under predict, right? Both are considered equally bad error. Correct. So if your model is saying less than what it is or more than what it is, both of these things are considered equally bad. So to remove that negative sign, usually we do the squaring, right? So you calculate the error, do the squaring, and then you add. Generally, in general machine learning language, these errors are also known as residuals. The reason they are known as residuals is because it's the residue that is left after explaining whatever is possible to explain using the machine learning model, basically. So you use the machine learning model to explain the values of the target. If you are not able to explain a remaining amount, that is called residual. Okay, that is why the name is residual. The same thing is called errors. So, don't worry about these technical terms so much. It's the same thing. It's just how far you are from the prediction. Okay. So now, if I apply this to both models, then I can find out who is having more error and who's having less error. Very simple logic, right? This thing is called sum of squared errors. So whenever you get into linear regression, this is the first thing that you will see, SSE. There are other things, SST, we will come to that. Okay. So this is the sum of squared errors. It is the sum of all the errors and we square it to remove the negative sign. Okay. What is the error? Difference between prediction and truth. So yi minus y cap I square, and you summation it 1 to n, all the n data points. Okay, that's called SSE. So this is the overall error of the model. Okay, like if you fit this line to this data, this is the overall error. Okay, and obviously you can also see, these are also terms that people use. It's also called residual sum of squares, RSS. Okay, same thing. It's the sum of square errors, or you can call it RSS, residual sum of squares. Okay, this is basically the objective function that needs to be optimized. Now, this is the secret, so to speak, of machine learning, of the learning in machine learning. So if you remember, we said that we have to somehow, in the previous session, I used the word somehow we have to make the machines learn somehow. This is that somehow. Okay. For each machine learning model, there will be a certain objective function and an algorithm, how to train that machine learning model. In the linear regression case, it is called sum of square errors. This is the thing that is going to be optimized. So mathematically, we will try to find that linear model which minimizes this error. So if you see the last bullet point, the linear model that minimizes this prediction error will be called the linear regression model for the data. So this is another technical term that I want to talk about. Any line is not called a linear regression line. So the best fit line is called the linear regression line. Okay. So when it's kind of a very informal language when we say we want to fit a linear regression model to the data, that is informal language, because regression already means that it is fit. Okay, I hope that is understood. Everything else is just a linear model. There can be many linear models for the data. The best fit line is called the linear regression model. But generally everybody says we will fit the linear regression model to the data. Actually we are fitting a linear model to the data, and that fit model is called the linear regression model for that data. Okay, it's very small technical jargon point. Don't worry too much, but if we all understand what's going on here, that is enough. Okay, we are trying to minimize this error. Okay, so how does this look? Let's look at the green model and red model calculations. Okay, so obviously all of this is done automatically in the backend when you try to implement, but here is just a sample. So these, as you can see, these are the data points, right? These are my training data points. I have Aarti, Darshan, Isha, Gayatri, Hemant. I have all the 10 training data points, and I have the actual value and I have the predicted value. Okay, from the green line and the red line. So you can see here, this is actual value, predicted value, actual, predicted, actual, predicted. So first you find the differences. Those are called the errors, and then you okay, these are the errors, right? These are all the errors here. So these are the green model errors, these are the red model errors, and then you square these errors, right? So you take this 147.85, you square it, you take this minus 11.71, square it. So you square all the errors, and same thing you do for the red model. Okay, and finally you add them up, because we want to find out which model is having the minimum sum of square errors. So the green SSE is this number here, 304501, and the red SSE is this number here, 255199. We are not trying to, give special attention to any one data point. That should be very clear from this. It's not as if, Aarti as a data point is more important to me and Isha as a data point is less important to me. No, right? All the data points should be treated fairly, and the machine learning model should learn the nature of the relationship between the features and the output. Okay, so that should be apparent from this. That otherwise I could say model did better for Isha. Actually you can check it right now. The error for this person, if you see see this one, right? Error for Trevor. Check the error for Trevor. Trevor's error in the green model is 10, right? And the red model is 128. Based on that, I could have said green is better. No, that's not the case. For all the training data points, you must treat it fairly. That is the way, that is why you call it learning. Okay, otherwise it's not learning, otherwise it's memorizing. Okay, so I did one, one test in my class, I aced. All other tests, I don't care. So I will pass the board exam. No, that is not the case. You should be able to generalize well. Okay, so it's very important to understand this point. It will become clearer when we go on. Now, see, there are a few optimization methods, and see, the goal is essentially to find the set of coefficients that minimizes the SSE. Okay, so what's written here is just SSE, sum of square errors. You have to find the coefficients. So in both the models you saw, there was intercept, there was slope. So the goal is to find the right numbers. There are mathematical methods that do this quite simply. Okay, there are many methods. The most common method used is ordinary least squares. Okay, it's a derivative matrix based method. It's pretty fast. Okay, there are many other methods. Even this is a popular method. Gradient descent is also popular. We'll not go too much into the math of these. That requires way more time, and that's another session. I would urge everyone to have a look at it. It's not that you need to be able to do it pen and paper. Not really. If you just read through some of the math, it's you'll get an idea. Okay, matrix inverses, things like that. So don't worry if you don't understand the math of it. Right, that is something you can even spend time once you understand implementation and how to work with these models. Right. Anyway, so if you see in Python. Stats models, I think we are using the OLS function. I'll show you that today. Fine. Now, now that, okay, we understood that there is something called the best fit line, and that best fit line is called the linear regression model for the data. And there are methods to optimize, such as ordinary least square, gradient descent, and so on. Okay. And there are ready-made implementable functions which do this for you. Okay, based on any one of these methods, ordinary, least square, gradient descent, whatever. Now, if I have my model, so what? Okay. Obviously, one point is you can predict, right? You can use the model to predict new data. Before we go to predict, there is one stage we should study, then we can go to prediction. Okay. The stage that we want to study right now is how to interpret the coefficients correctly. So see, it's easy to understand that, okay, take Jasmine, take her income and just put it in the X value, and you will be able to find the prediction, right? 0.026 into 49980 plus 399.77, it will give you some number. Okay, we know how to use the coefficients. Wonderful. Can we interpret the coefficients before we go for prediction? Okay, instead of just looking at it as a formula, can we understand what do the coefficients mean? What are they telling us? Okay, so this is what the coefficients are telling us. And don't worry about the table. By now, I think we know that the first column is the income, the second column is the true amount spent on coffee, and the third column is the prediction from the red model. Okay, so in the data set, it is income, true amount spent on coffee, predicted amount from the red model. And here is your equation. So first, let's look at the slope. Okay, that's kind of the most interesting one here. It is a measure of strength of influence of the input variable on the output. Okay, so the way to interpret this number, on an average, if x is moved by 1, then the amount spent on coffee increases by 0.026. So there are two things here. Increases because there's a plus sign. Okay, increase because there is a plus sign. And why 0.026 units on average? So as I said, the model is going to have errors everywhere. Okay, if you go back to the diagram, you can see the model has errors everywhere. Okay, but if you gather sufficient amount of data, then you can see that if you take a group of data whose income is almost the same. So suppose you take income around Isha, which is $52,000. Okay, suppose you gather 5-10 such data points, right? Find the average amount spent on coffee of those people. Who people? Income around $52,000. Find the average amount spent on coffee. Then you take another 10 data points. Suppose you take someone around Monisha, 70K, 69, 71K, and then you find their average amount spent on coffee, right? This rule will more or less match the difference. So if you find the difference in the amount spent on coffee of those two groups, right, that will directly be proportional to the difference in the income times 0.026. And I have a simple example here. So if you see here, if you take actually Gayatri's income minus Isha's income. So here I'm taking Gayatri and Isha. So 72 minus 51, right? That's about $20820, right? This is the difference between their income. The predicted difference in their coffee spendings is nothing but the coefficient times the income. So 0.026, that's the coefficient, times 20820. This is giving you what? $541. Okay, and you can obviously use the predictions also. That's the same thing, right? If you go back to the data set, you can first use the equation to predict the outputs 2292.7 and 1751. Here you can see the predictions, and you can subtract that. That will also give you the same value. Okay, now what is the actual difference in the coffee spendings? The actual difference in the coffee spendings is 2063 minus 1702. Again, go check the data. Okay, so use the truth values, find the difference. How much is the difference? $361. Now, what is the point I'm trying to drive here? See, we are using one variable to predict coffee spending. In the real world, we use multiple variables to predict any target variable. This is point number one. We are using only one variable, simple linear regression. Point number two, we have only 10 data points. Real here in this example, we have 10 data points. Real data will be having 1,000, 10,000 data points, millions. Okay. I am saying even with 10 data points, even with a simple linear regression equation. And by the way, this red model is the linear regression model. The coefficients come from fitting it in Python. Okay, so this is the best coefficients. So this simple linear regression model from 10 data points is still matching the average value correctly, almost. Okay, so the predicted difference is $540. The actual difference is $360. Not bad. Not bad at all. For 10 data points and one input variable, this is not bad at all. And if you use more data points, and if you use, in the future we'll be doing multiple linear regression, these two numbers will be more or less the same. Okay, so this is the reason why linear regression is used a lot in analysis also, not just in prediction, but analysis also. These coefficients can tell you a lot about your data. Okay, so what is the difference between these two groups in terms of spending? What is special about these two groups? There are many ways to interpret these coefficients. Okay, and it all boils down to this very simple statement here. A unit increase in X leads to a 0.026 increase in Y, predicted Y, on average. Okay, on average. So it will not be exactly the same for 1 or 2 data points, but when you do it for a lot of data points, it will average out. Okay, so this is how you interpret the slope coefficient. What about this intercept, this constant value 399.77? Now this thing, this constant has two personalities, you can say. If the X value being equal to 0 makes sense, then interpreting this constant makes sense. Basically, the constant is the expected value of the amount. Expected value, let us remember, nothing but the average. Correct? Expected value just means average, right? So this 399.77, it is the expected value of amount if income equal to 0. But the interpretability is a bit shaky, correct? Because income equal to 0 doesn't make sense. So if you have a linear regression equation where the input X equal to 0 makes sense, then the constant will be interpretable. Otherwise, it is an imaginary interpretation. Okay, so if the predictor can meaningfully have a value of 0, maybe you're talking about temperature as a predictor. Maybe you're talking, if it's temperature, like ambient temperature 0 degrees, okay, that makes sense. If it is blood pressure, I don't think 0 blood pressure makes sense, right? So it depends on whether 0 makes sense in the input. Okay, if the predictor can meaningfully have value of 0, then it is the expected or average value for those data entries in my data set whose X value is 0. Okay, so otherwise the intercept is meaningless. Now we have discussed the coefficient and the mean interpretation. Sorry, not mean, the constant interpretation. And you would have noticed I am talking in terms of average, mean, average, mean. Okay, so linear regression more or less does that only. It works on averages. Okay, on an average, how much change is there, to evaluation of model. Okay, goodness of fit. Now before we get into model evaluation, I think we should explain one thing. You may be asking the question that, look, we just took the what is that, the sum of square errors, right? We just took the sum of square errors, right? And we fit a linear model to the data set to minimize this SSE, and then we called it the linear regression model. Correct? So out of all the infinite possible lines that you can draw between income and age, right? So right now we are talking about not income and age, income and amount. Income and amount. So out of all the infinite lines that you can draw between income and amount for the data, we already found out which is the having the lowest SSE. Red model, right? The red model had the lowest SSE. So then you may be asking the question, why should I evaluate the model? Done, na? Red model is best. Why should I evaluate it? So there's a difference between best fit line and good model. your best fit line may be a bad model. Okay, let's try to understand that. Your best fit line may be a bad model. Right now, we are discussing only about linear regression. Over the course of the next few lectures and weeks, you will learn multiple machine learning models. What if linear regression is a bad model for your data? And what if some other model is good for your data? How do we analyze that? So for that reason, we need to do model evaluation. Just because your straight line is the best fit in your data set does not mean it is a good fit. It is the best out of all the possible lines. So all the possible lines may be bad. Out of those infinite bad lines, you found the best bad line. Think of it that way. Is it good or is it bad? It's the best out of all the bad. How good is it? So that is why we need to do model evaluation. Okay. Now let's understand how model evaluation is done first for linear regression. See, in the context of linear regression, generally what we do is we compare it to a base reference model. So supposing you have other linear regression models, right? We will generally use the base model as a comparison. So the base model is what? If you remember, the base model or the simplest model is average of output, right? So you have the mean value of all the coffee spending. Previous year coffee spending, you have the mean value, right? So what does the model look like? For any x value, for all the x values, you are predicting the exact same value. That is the mean value. Okay. Now the linear regression line, which is the best fit line, how did we obtain this line? We obtained it by minimizing SSE, right? We minimized the SSE to obtain this. So we found a coefficient and we found a intercept. All right. So that line looks like this. Now the question is, which has more error? This may sound like a very obvious question, right? I mean, the answer might be very obvious. Of course, the one with the less SSE is going to be having less error, right? Therefore, this model should have more error. If your straight line has the lowest SSE, if when it is horizontal, then that horizontal line is your linear regression model. I hope it's making sense. Okay. There are infinite such straight lines. All of these are having different SSE. Why they are having different SSE? Because the predictions will be different. So the errors will be different. So the SSE will be different. Some of these are having less total error. Some of these are having more total error. Now, out of all these lines, if your linear model with the lowest error turns out to be horizontal, then that horizontal line is your linear regression model. Now, having said that, generally that is not the case. Obviously, that is generally not the case. Data are all scattered. They have certain linear patterns. Real data doesn't behave the way I just explained. So generally, you will get some intercept and some slope. That line will be your linear regression line. And of course, that is going to have less error than your basic model. What is your basic model? The mean model. Okay. Great. This much is clear. Now, let's put all of that into algebraic terms. The base error is called the SST. So essentially, it is just nothing but sum of error. Okay. It is the sum of square errors for the base model. So if you see here, these are your truth values, yi. These are your truth values, actual historical, what you say, true value of spending on coffee. Okay. And these are your predictions. Why the prediction is y bar? Why have I written y bar for the prediction? We know that in statistics language, y bar means the average. It is the mean. And in the baseline model, all the predictions are equal to the mean. So you are finding the difference between the mean, that is the predicted value, which is the mean, and all the data points. That's all, right? You are essentially doing this. Sorry, you are essentially doing this. You are finding the differences between the mean of the coffee spendings and the actual data. And then you are finding the SSE. Very simple. You are squaring the errors and you are adding them. Same thing you're doing here also. For the red model also, for the linear regression also, you're doing exact same thing. You're finding the prediction errors and you're squaring. Okay. And that's exactly what is written here. Now generally when you do the SSE for the mean model, it is called SST. Okay, it's just a terminology. Okay, when you find the total error for the average model, it's called SST. When you find the total for the linear regression model, it is called SSE. That's all. And generally, what did I say? SSE will generally be less than SST. In very, very rare scenario, your linear regression model may be horizontal, but that is near to impossible, right? Most of the times you will get some coefficient and some intercept and some linear regression model, which is better than the horizontal model, better than the mean model. Okay. So safe assumption. What is the safe assumption? SSE should be less than SST. Okay. SSE is what? Error for the linear regression. SST is what? Error for the horizontal model. So obviously the linear regression should have less error. So we can consider this thing SST minus SSE, okay, as the improvement from the mean model. Okay, so SST is the mean model total, that is higher value. SSE is the error for the linear regression, which is lower value. So SST minus SSE will be positive number. Correct? It will be positive number. And this value is called sum of squared residuals. Okay, SSR. And you can see the formula here. SSR equal to SST minus SSE. Now I'll just take a step back and I'll reiterate. Why are we doing all this? Again, let's ask the same question. If I already minimized my SSE to get my linear regression line, why should I do all this? Well, because you want to compare different linear regression models. See, in your data, you're going to have multiple input features. You're going to have income, age, gender, this, that, whatever. You're going to have so many input features. And you're predicting one target, amount spent on coffee. How do you find out which is a better predictor? How do you find out which is a better model between two input features? For the same input feature, you can minimize SSE. Fine. But for different input features, you're going to get different regression lines. You're going to get different best fit lines. How do you compare the different best fit lines? That's the problem, which is why you take common reference. Okay, which is why you take the common reference, and the common reference is generally considered as the mean model. Okay, and mean model is agnostic, independent of the input variable, obviously, because you are only taking mean of the output variable and using it as prediction. That output variable truth is not going to change if you change your input. The true outputs are going to remain the same for any of these models or inputs. Okay, so that is a common baseline. Okay, so I hope we are well motivated to understand why we are using a baseline as a reference and then using the SSE of the linear regression model to compare with this. Otherwise, if I did not have the baseline, how will you compare one SSE with another SSE? Not possible. If you found the SSE for income versus amount, that is one value. If you found the SSE between age versus amount, that is another value. Okay. Even in that, you might say this is less, that is less, whatever it is. But you compare it with the mean, that allows you a common ground to compare. Okay, this is much better than this, or this is slightly better than this, right? So it's a universal way of comparison. Now, we understood that the SSR, which is nothing but the mean value, the mean model error minus your linear regression error, right? SST minus SSE is a positive value. Now you can compare this to you can convert this to a percentage. So if you see the formula here, it says R square. This is the name given, okay, to this metric R square. It is nothing but SSR divided by SST. And remember what is SSR? SSR is just difference between the mean model error minus the linear regression error. So SST minus SSE. And if you boil down this formula, you are getting 1 minus SSE by SST. And note that generally speaking, SSE will always be less than SST. So whatever value you get here is going to be between 0 to 1. So now you can interpret this as a quantity between 0 and 1. If it is closer to 1, it's a good value. If it is closer to 0, it's a bad value. Okay, and the way to interpret is it is a % improvement, you can say, from the baseline model. How better than the baseline model is your linear regression model. Okay, this is called R square. And I just have a simple visual example here just to motivate. Okay, so here you are going to have a very high R square. By the way, what is the R square for the first model? Okay, just so we can understand this more, intuitively. What is the R square value for the first model? Let me just put the formula here. R square is equal to 1 minus SSE by SST. Okay, the baseline model, if you treat the baseline model, yes, exactly, 0. Wonderful, exactly, great. So if you treat the first model as your linear regression model, then SSE equal to SST, because it's nothing but the sum of square errors, right? So the numerator is going to be equal to SST for the first model. So your R square value is 0. No improvement from mean model, obviously, because it is the mean model. Okay, then if you try to change the slope a little bit, you might get a slightly better R square, maybe 0.3, 0.4, whatever. This last graph, this is the linear regression line. This will give you the best R square for that input variable, X versus Y. Okay, so the R square value will increase like this. Okay, on the left you have the worst model, which is the baseline model. On the right most you have the linear regression model, which is the best fit line. Okay, great. And this might be having higher values, 0.6, 0.7, whatever. Need not be 1, nah? Never going to be 1, by the way. I hope that's also clear. You're always going to have some error. Okay, it will never be 1. Now we will see some of these things today. This is the result from a library called stats models. We will see that. Okay, now I'm not going to go over all of the different values in this result. I will speak about R square today in detail. Okay, in the upcoming session you will be doing a little bit more deep dive into everything else. For now I will be focusing on few things. I believe we'll be talking about R square, intercept, things like that. Okay, so okay, I'm blocking the R square value. So this, if you see here, this is where your focus should immediately go. Your focus should immediately go into this coefficient column, and then you have this thing called R square. Okay, so if you see this model, can we try to build this model? Can we write an equation? How do we write the equation? What are we predicting? You can see here what we are predicting. Even that is there in the results. Dependent variable is amount. So amount equal to, now let me use these coefficients to build the equation. Intercept is 399.7. I'll just write 78 plus y plus, because you can see that the coefficient of income is positive. So plus 0.026, I'll just round it. What is the input variable that is written here? You can see it here, income. Okay, so amount equal to 399.78 plus 0.026 times income. Does this equation look familiar? Does this equation look familiar? It is the exact equation for the red. Here it is. Right? It is the exact equation for the red model. Okay, so that's how you can build the equation if you want from the results. Okay, so we'll see this result, how to produce this. Don't worry about all that, we will see that. Okay, and interestingly, look at the R square value here, 75%. Not at all bad, I would say. 75% is pretty good. I told you, right? 10 data points, only one variable, still I'm getting 75%. In other words, my machine learning model has learned something. Definitely it has learned something. And that learning is here, guys. 0.0259. That's what it has learned. It has learned that on average, if my customer who comes next, if their income changes by plus 1 unit, then they will spend plus $0.026 more on my coffee. Okay, so this is telling you both. It's telling you the direction, that is, is like are older this is what income versus amount. Okay, are people with more income likely to spend more money on coffee in my shop, right? So plus minus will tell you that, right? Plus means yes, more income, they will spend more on coffee. Minus means less, more income, they will spend less on coffee. Okay, here the model is telling me it's plus 0.0259. Okay, it's also telling me how much. It's not just telling me, you know, the proportionality. It's also telling me how much. Okay, so 1 unit increase in the income of my customer, 0.026 units or dollars increase in the amount spent on coffee. And this model is doing pretty well, 75%. Sorry. Yeah, so this model is doing pretty well, 75%. Now all the other things, as I said, adjusted R square, you know, some of these p values and things like that, you will learn in more detail in the upcoming session. I believe it's on Saturday. You will do a deep dive into that library called stats models. Okay, what we are trying to achieve in this session is we are trying to understand, okay, the analytical part of it, which we just saw. What we just saw was the analytical part of it, how to use linear regression for analysis. Of course, you can use the same equation for prediction, no problem. But how do you evaluate that model in terms of prediction? Now, before going to that, I hope it is clear that now if I change my input variable, the R square value will change. Okay, that's the whole point of this this thing. So this has 75% R square. Now that is income versus amount. If I next try age versus amount, then I might be getting a different R square. Okay, so looking at those two, I can think, who is a better predictor for my coffee amount, right? And who's stronger? Which model is better at fitting? Okay, so that's the importance of R square. Now, generally speaking, analytical indicators, okay, they are good analytical indicators as long as certain assumptions are satisfied. There are many assumptions such as your data is not non-linear and things like that, right? So these kinds of assumptions you will see little by little. Sometime in the next week also we'll speak a little bit about the. Now let's forget about validation data for a bit. Okay, let's forget about validation. As I said, validation is something we will use when we have the ability to improve our model. Right now we don't have the ability to improve. Okay, can you guys tell me, is there any way to improve the best fit line? No. You have income, you have amount, you have 10 data points, you have a very strict mathematical algorithm which gives you two numbers, intercept and coefficient. Do this 1000 times, you will get the same intercept and income. It is the best fit line. There is no notion of changing or modifying or improving this model. Okay, that model improvement thing we will get to in the next week. We'll see what do we mean by improving model next week. Okay, but first let's understand good bad model and all that. So validation data we will not worry about right now. We will only think in terms of train and test. So training data, it's my 10 data points. Okay, whatever 10 data points that we see. Where's the data set? I hope it's okay, lot of slides. Yeah, this is my training data. Okay, Aarti, Darshan, Isha, Gayatri, Hemant. So we have 10 data points here. We have their actual income values and we have their actual spending on coffee of last year. 10 data points. Okay, so we will be using those 10 data points to train the model, which we already did. The model training is over. We have the best fit line, we have the linear regression. Okay, we have the equation, we have the coefficients. Now, how do we evaluate then the predictive power of this model? Is it doing well on new data? How do we understand that? So what we need to do, we need to generally follow this ML workflow. As I said, we will focus on train and test for now. We will train the model only on the training data set and then validate the results or test the results using the validation or test data set. As I said, this validation business, we'll take it up next week, but we will declare the model's predictive power on a test data set. So as you can see, we have the best fit line. Where did this best fit line come from? It came from these 10 data points. Now suppose you have intentionally left aside 3 data points which you did not use when training this model. So this coefficient 399.77 and 0.026 interceptant coefficient, they came only from these 10 data points. Okay, so the model has not seen or been exposed to these 3 data points. Intentionally we have left it aside. Okay, so Bhavna, Irfan and Oliver were not used to arrive at the red model equation, but I have the data of Bhavna and Irfan and Oliver. I have the data, so I have their incomes and I also have the amount of money they spent on coffee last year. Okay, these true values I have, both of these truth values I have, but I intentionally did not use it, okay, to train my model. Now we can use these to check whether the predictions are good or bad. Very simple. Okay, so since we did not use these data points for training the model, we can use it for testing. Again, just think, right, if all your pre-board questions were exactly the same, pre-board 1, pre-board 2, pre-board 3, or even your class questions, whatever questions you got tested, assignments you got tested in your classroom, like imagine a school classroom, all the questions are the same, pre-board also same questions. Do you think you have a good idea of how you will be performing in the board exam if all the questions were same? Absolutely not. Absolutely not. You will question the teacher, you will question the school saying, what are you doing? Why are you not giving us good practice questions? That's exactly the concept here. Okay, we want to test the model on data that it has not seen. How to do the testing? First step is to get the predictions. You already have the model, you have the true income values of Bhavna, Irfan and Oliver. You put these x values in the equation, you get the predictions, and then you have to just compare the truth and the prediction for the testing data and summarize it. There are many ways to summarize. As you can see, we have mean square error, RMSE. These are terms that we may have heard of before. We'll see the formula. We have mean absolute error, we have mean absolute percentage error, so on. Okay, these are predictive performance metrics when you are doing regression. For classification it will be different. Okay, for prediction, generally in predictive performance we use these kinds of metrics: RMSE, MAPE, so on. RMSE, what does it look like? So all you need to do is you have to compare these two columns, right? You use the red model to get the prediction. You already have the truth values for the testing data. So what is RMSE? Root of mean of square of errors. Okay, it's obviously not a very creative name. Root of mean of square of errors. So error 1632 minus 1492. Okay, next error 1987 minus 2076. Next error 2124 minus 1899, as you can see here. Get the errors, square the errors, take the mean, take the root of mean of square of errors. Okay, so that comes out to be something like 153.48. What is the actual value? The actual value is the amount of money in dollars spent on coffee. That is what we are trying to predict. So you have the values like 1492, 2076, 1899, so on and so on, around $2,000. Okay, $1,500, $2,000, something like that. So the error of your model in this scale is about $150. Okay, that's what RMSE is kind of telling you. All right, so this is one way to compare two models. Okay, another way, mean absolute error. So this is nothing but instead of doing the squaring and rooting and all that, right? So why did we do the squaring and rooting and all that? Because we want to remove the negative sign. There is another way to remove the negative sign. Okay, that is the absolute value function. So this time you take the error, you just take the absolute value, and then you find the average. So here it's about $151, right? Another interesting error metric is the mean absolute percentage error. So here what you do is you take the error, and you treat it as a proportion of the truth. So the question is, what proportion of 1632 was my error, what proportion of 1987 was my error, what proportion of 2124 was my error. Okay, so these proportions you take average and it will give you a percentage, right? So here you have 1632 minus 1492 divided by 1632, so that is a ratio. Same way you have the ratio for the next data point, same way you have the ratio for this data point, take the average. Here we are getting 0.07, which is about 8% error in prediction. Okay, so again, just to reiterate, we have computed these metrics on the testing data. To compute these metrics, you need to first predict on the testing data. To be able to predict on the testing data, what you need to do, you need to first of all split your data into training testing so that you keep testing separately. Secondly, you need to have a model. Where did the model come from? You trained it from the training data. Okay, so I hope this whole process is clear. Original data split into training testing. Training is for training the model, and then you check the predictions on the testing. You arrive at a metric. Do that for different models and then see which model is working better. This is a way of analyzing the predicting power. Okay, of course in linear regression you can always analyze using the r square values also. All right. Right, so in the first part of the Python code, what we'll do is we'll import all the packages for the demonstration. I generally have the habit of loading all the required methods, packages, libraries at the beginning itself. You can do it whatever is suitable for you, right? So I generally just load everything. We'll also load the data, and we'll do some basic data processing, such as changing strings to category data type, so on and so forth. Okay, you'll get into more details of the category data type in the upcoming session, which is on Saturday, I believe, which deals with categorical variables and things like that. You will of course encounter this more and more when we do multiple linear regression also. So first, I'm just using a couple of statements to filter warnings, because as far as I'm concerned, an error is good, but getting warnings all the time is something that I usually don't like. We want NumPy and pandas by default because we might end up using them when we do data analysis, machine learning, right? Seaborn is for data visualization, so we look at some plots to understand the data. This is one library that we will be using, which is stats models. So if you see here, stats models.formula.api. Okay, so there is a method for linear regression from this library. We'll use that, right? And we'll also use the very popular machine learning Python library, which is Scikit-learn or sklearn. So from sklearn.linear model, we will import the linear regression method. As you can see, we are also importing the train test split method from sklearn again. So here you have sklearn.model selection, right? And notice how the train test split method comes under the model selection module of sklearn, right? So we spoke about this before. Why should we do this train test split and all that? It's so that we can compare different models fairly, right? So under model selection, you have this method, and for as we saw before, we have different metrics by which we can evaluate the performance of these regression models. And if you see in sklearn.metrics, there's a ready-made method for mean square error, MSE. Okay, now if you want the actual data source, I've given the link here. Okay, so it's from a university website. It's actually about some cars. So let me just run these cells. Yeah, so the data is stored in this CSV file, car prices, and I'm setting the index column to car ID. Let's see what the data looks like. So here you can see car ID 1, 2, 3, 4, 5. Since the car IDs are 1, 2, 3, 4, 5, I'm using it as the index column. That's why I'm putting index column equal to car ID. There are many features, as you can see: symboling, car name, door number, that's number of doors, I'm guessing, car body, engine location, wheelbase, car length. So you have many features, right? You have many features, and at the end you have this interesting feature called price. Okay, so the objective of this exercise is to analyze price. Okay, larger question is, can we predict price using these input features? Okay, using city MPG, highway MPG, whatever, bore ratio, engine size, can we predict price using these input features? And you also have a description file here. So car prices data description. So this will help you understand each of the features. So here there are the features, car ID, symboling, car company, and here is the description. So unique ID of each observation is car ID. Symboling is some sort of categorical risk rating. Car company's name of the car company, door number is the number of doors, and so on. Right? You have all these features and their descriptions. Let's also look at, and I hope here we were using the pd.read_csv function to read the CSV files. Now we are using df.info. So if at any moment if you feel that you want me to pause or study some command in detail, let me know. Okay. Right. So you can just raise a hand. I think I will hear the beep. Right. When somebody raises the hand, I will hear a sound. So that will allow me to check the chat. So I'm using .info, and .info is very useful because it tells me everything, at least in the sense of the shape and structure, right, of the data. It tells me a lot. So it has an integer index. There are 205 entries named 1 to 205. Okay. And you can see non-null count. So you have 205, 205, 205. Everywhere you have 205. And the total number of entries is 205. This means there are no missing values, basically. So from .info, you can easily infer that there are no missing values in this data set. It has 20 columns. Each column name is here, and the type of the columns is here. Okay, for example, car body is object, generally means string, by the way. Bore ratio is a float value, engine size is an integer value, so on. So most features in this data set are numeric, either integer or float, but some features are of object. Okay, these are actually strings. So if you see, for example, engine, location, car body, it says object, right? These are strings. Typically, when you do categorical analysis, right, it's better to convert these into category data type. Okay. So just to explain that a little further, if I just say, for example, I am interested in, suppose I take car body. Let's just say car body. So I want to know what are the entries here. So if you see convertible, convertible, hatchback, sedan, sedan, sedan. Now I can use .unique to see what are the unique values that this feature can take. So convertible, hatchback, sedan, wagon, hardtop. Okay. So clearly it's a categorical variable. Okay. So in Python, you can convert this from string to category. Since it's a categorical variable, converting to category makes our analysis easier and faster. Okay. Having said that, for example, if you take car name or something, then mostly I will be dropping it, right? If I just say df car name, right? If I just take the car name, as you can see, these are all the names: Alfa Romeo, something, and so on and so forth, right? Volvo. Now, I would not waste my time converting this to the category data type. I would just drop this because I don't need it for my analysis, right? Okay. So what we are doing is first convert all the qualitative predictors to category. So here you have df select d type. So the select d types method allows you to select all the columns of a certain type in your data frame. Notice that it is a pandas command. That is why df dot. Okay. So select object type columns. Okay. So categorical columns equal to select object type columns, and then convert that to category. So you use the dot as type method to convert those to category. Now if you check df info again, wherever you saw object, now it is category. So if you see here, these are objects, right? Now you have all these things as categories. So all the object data entries are now category. Now when you do your pivot tables and histograms and all those other things, not histograms, sorry, bar graphs and all those other things, it's much more efficient. Okay, and in fact linear regression also becomes more efficient when you do this. One thing to notice is that just because you converted all these objects to categories, does that mean you did the conversion for all the categorical data types? That is something you need to check. For example, if you see the symboling feature, it is recorded as integer. Like if you see here symboling, okay, it says int 64. Where is the symboling? Here. So you see the values 3, 3, 1, 2. It is recorded as an integer. But if you go back to the data description, the data description is telling you that symboling is a categorical risk rating. It's not a numerical feature. In other words, you cannot have a symboling of value 2.5. Okay, this is some kind of categorical rating value 3, 4, 2, something like that. So in fact, you can even check the unique symboling values, right? Let's just quickly check that. DF symboling unique, clearly categorical. Otherwise, I would be having values like 0.95, 1.3, 3.5, not there. It is recorded as integer, but it is categorical. So be careful and study your data. Okay. So here I am converting symboling also to category. Okay. Then car name is useless, so I'm going to drop it. So df.drop, drop car name. Axis 1 means what? It means column. In place means change the existing variable called df. Update the data frame. Okay. So things like names, identifiers, these are not considered as valid predictor variables. So car name is not generally not considered as a valid predictor for linear regression. Okay. Finally, let's look at the data we have and check its shape, right? So now we have 205 entries, which is same as before, and 19 columns. Now note that in the sense of real data sets, this is still a small data set, albeit a real data set, right? The reason we are taking a small data set is we want to explore simple, start simple, and then the same can be used for larger data sets, right? So this is actually a very nice data set. It's not easy actually to build models on this data set. It has a lot of variation, a lot of things going on. So it's a good data set to understand stuff. And again, for this demonstration, we will not use these 19 features, right? So the expectation from the learners is that through the course of these, right, I will be sort of treating this with maybe 10 features, 8 features or something like that, right? And I'll show you, okay, this is good model, this is bad model, what's happening here. Then you can do the analysis and the modeling from scratch. That is the intention, right? So you can learn what you're learning from these demonstrations and the theory and apply it to the full data set. Okay, I will be using a subset. So the subset I'm using has these features: symboling, car body, engine location, car length, car width, car height, curb weight, which means weight of the car, horsepower, CT MPG, highway MPG, and price. Let's even check what is this. CT MPG, mileage in city, highway MPG is mileage on highway. Okay, great. So you can actually go back and check the data description and understand these features. Note that I am not a car expert. Okay. All right. So now I have this simple data which we can use for demonstration purpose. Okay, I'm just showing the head, that is 5 data points, top 5. So you can see symboling 33122. It is now category data type. Okay, you can confirm that by doing type. What is that? DF symboling and just choose any one value. Type symboling. I can use .loc. What is the car ID? Car ID is 1. So you can see it says int. Maybe I need to rerun that. Give me a second. Let's just rerun this category. Yeah. All right. So the feature, sorry, car name is not found in Access. Why is the car name not found in Access? Because we deleted it. Let's just redo this once. We have to read the data because we deleted deleted the car name. Okay, great. So okay, so now if you see the shape and if you see the DF info, right, you will see there are 11 features that we are using: symboling, car body, engine location, all these, right? So those 11 features are here, right? And each of their data types is given here: category, category, float, 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 int. Okay. So generally, when you do linear regression, ensure that all your input variables are of any of these data types. Okay, the correct data type. So categorical in this case are symboling, car body, and engine location. You can see the unique values to understand that, right? So symboling we already saw, car body also we saw. So let us see what is this engine location. Car body was sedan, hatchback, that kind of thing, I think. And symboling had -3 to 2, some kind of value. And engine location has 2 categories. As you can see, now when you do unique, you're getting this extra information. Okay, categories, right? So since it's a categorical variable, now you're getting 2 categories. Each category is type object. So same way, if I do for symboling, now I'm going to get 6 categories, but each category is an integer value. Okay, initially what was the case? The feature itself was integer. Okay, now it's of category type. All right. So let's just store the categorical column names here. Okay, so if I just print this, it's just the name of my categorical columns: symboling, car body, engine location. Okay, this is in a list, obviously, right? It's actually an index, so it's a pandas object, but it's a list. Essentially, it's a list. Okay, now comes the machine learning part of the exercise. You need to split the data into input and output. Okay, now out of these 11 variables you see, the price variable, that is the last column, is the output. That is what we want to predict, right? And the other 10 variables which we have retained, these are the inputs. So x is equal to df dot drop price. You drop the price column and retain the data frame, that is x. You retain the price column only in a new variable, that is y. Okay, now if you just quickly check what is x, as you can see, it does not have the price column. Okay, it has 1 2 3 4 5 6 7 8 9 10 input variables. And if you check y is essentially the price. Note that the values are associated with the car id. This is your original index from the original data frame, right? So if you see the type of this y variable, it is a panda series, right? Which is why you have the same index of the original data frame. Same way, x is obviously a pandas data frame with the exact same index. All you've done is you have separated the one column. Okay, this is the target variable, is the price. Secondly, if you remember, we need to split the data into training and testing. All right. Note that there is no validation splitting going on here. We are directly doing train and test because, as I mentioned, we are not fine tuning any model yet. That we will do in the next week. So now we just need training and testing. So this train test split method, it gives you a tuple output. Okay, the output is a 4 tuple. Okay, it has 4 values: x train, x test, y train, y test. Of course, you can give whatever name you want to give here. Okay, but this is generally the name that is used for these variables because this is exactly the order in which the output comes. You get the x train data, x test data, you get y train data, y test data. Okay, so if you Google any code with train test split, the left side is almost always going to look like this. Okay, now you look at the parameters here. So x, this is my input data. Y, this is my output data. Test size is essentially percentage. Okay, proportion. What percentage of the original do you want to separate as test? So here I'm giving 0.2, which means 20%. What is 20% of 205? Right, 20% of 205 is 41. Correct. So 1 by 5 times 205 is 41. And the random state, because when you do the data splitting, generally there is a shuffling that happens. As I mentioned before in this session also, we want to avoid giving special attention to specific data points. We want to generalize the model's ability to see the data points. We want to generalize. It has to be random and shuffled. Okay. So there is of course some shuffling going on, but you can set something called a random state. If you set the random state to any number, by the way, you can put it as 0, you can put it as 1, 2, 3, whatever. Okay. I'll just keep it as 0. You can put any number. Point is that it will reproduce the same split if you use the same random state. Okay. This is good for purpose of analysis. Right. So I run this cell and my data is now split, and you can actually check what is this X train, X test, what is all this. So X train is still a data frame, but if you see now, as you can see, the car IDs are all shuffled. Can you see here in the index, everything is shuffled, 5, 72, 135, and I have only 164 of these. What happened to 205? I have only 164. So 80% came to X train. And if you see here, the completely different IDs. Okay, so it's showing all the 41 results, which is why I'm not able to see the shape. So you can just quickly do dot shape if you want to see. So I have 41 entries here. Okay, and that's what I have printed here also. So training data set size is 164, testing data set is 41. In the slides, what did we do? 10 data points for training, 3 for testing. Okay. Now generally, 60, 40, 70, 30, 80, 20, these are all acceptable proportion of split. What is not acceptable is if you're using 20% for training and 80% for testing. That doesn't make sense. Okay, again, think in terms of board exam and all. If I just allow you to practice first 3 months of your school, and the rest of the time I say no more teaching, no more anything, no more training, you just have to attempt the exam. So why should I spend 80% of my time testing myself when I have not learned anything, right? Think in the same way how much you should split it. Generally, as I said, 70, 30, 80, 20, 60, 40, these are acceptable. All right. Okay, so this kind of we are at a stage where we have our data. Do we have any questions at this stage? Miles per gallon. Okay. And in fact, you'll be spending a little bit more time on the EDA when you do the stats model analysis in the upcoming session. So for now, I just want to quickly walk through the EDA, right? So here I have count plots for the categorical variables. Notice I'm using for loop and I'm using subplots from matplotlib, right? And if you remember, categorical columns is the name of the columns which we saved somewhere here. So it's saving these 3 names, symboling, car, body, engine, location, right? So you just go through all that and you build count plots, right? As you can see, symboling, you can see that this is kind of how it is. 0, I'm guessing, is neutral risk. -2, maybe it's bad risk. 3, maybe it's very good risk. I don't know. As I said, not really a car expert. You'll have to read the data a bit more clearly. Okay, but this is kind of the distribution, right? 65 cars are neutral, around 50 cars are having risk rating of 1, so on. Car body also you can see here, hatchback, 65 cars are hatchback. We have around 90 something cars in sedan and so on and so forth. And engine location, you can see almost 99% of the data set is made of cars with front engine location, and maybe 1 or 2 cars are having rear. In fact, it would be interesting to see who these cars are, right? What is the feature name? Engine location, right? Location, rear. 3 cars. There are 3 cars in 205 which are rear. I deleted car name, so when you do your analysis, you can keep the car name column if you're interested. Okay. Anyway, 3 out of 205 is not a good indicator. Okay, so anyway, we can see that the engine location feature is extremely imbalanced. Okay, 205 minus 3, That's what 202. So 202 cars with front and 3 with rear. So then from this data you have to ask the question, is engine location a useful feature for me? If 99% of my data set has front engine, then will the difference in the two groups mean anything to me? Right? One group has 3 cars, one group has 202 cars, right? This is the front, this is rear. Is it fair to make a comparison with 3 data points in rear and 202 data points with front engine? Is it fair to make a comparison? More often than not, it is not fair to make the comparison, which is why we will drop this engine location feature here. Okay. Anyway, you can also create bar plots instead of count plots. Bar plot with average price as the y-axis. Okay, so for example, you can see what can you infer from this. I will look at car body, for example. This is telling me that hard top cars have the highest average price, followed by convertible, and hatchback cars seem to have the lowest price. Okay, that's what you can infer from this. Now, as I said before, engine location doesn't look like a useful feature to me in this data set, so I'm going to drop it. Now we can also make scatter plots, right? So this is the beginning of linear regression analysis, right? You have to start making scatter plots and things like that. So here I'm making a scatter plot of car length versus price. So you can see car length on the x-axis, price on the y-axis. There is some kind of increasing trend. Looks non-linear to me, but we can always fit a linear regression. Nobody is stopping us. In fact, we should always start with some linear analysis to understand how good or how bad it is, right? So of course there is some kind of positive trend. Now generally for numerical features, there is this thing called pair plot, right? So cbond dot pair plot. What it's going to do is it's going to make all the possible scatter plots as well as histograms, right? So if for car length versus car length, you're going to get histogram. So here, if you see in the diagonals, you have the histograms, right? It's a very obviously very big plot. With more number of features, it's very difficult to use this, obviously, right? But what you can see here is written car length, here it's written car width, car height, so on and so forth, and you have the same features here. So if you want scatter plot between any two features, then you can just choose the row and choose the column. So for example, if I want to see price versus CTMPG, so then I will search for CTMPG here. I can see it here. Here is the thing, right? And price is here. So the plot that shows me the relation between price and CTMPG, that is here. Interestingly, as CTMPG increases, there seems to be a decrease in price. Okay? So we can even single that out. Whatever looks interesting here, in fact, this looks very, very interesting. Look at this one. This looks very interesting. CTMPG versus highway MPG. Almost perfectly correlated, you can say, right? Anyways, so CTMPG versus price, here is the scatter plot. Again, there's a nice downward trend, definitely there is some kind of linear regression we can try to fit and see, is the prediction good or bad. Now for categorical variables and things like that, you can use pivot tables, right? So I won't go too much into pivot tables. You can use Python, Excel, other things to make pivot tables. It's just, what is it doing? It is essentially just doing if conditions, right? So if car body equal to hatchback and if symboling equal to 1, then how many cars are there? That's all. So in the hatchback column, you go down, and in the symboling equal to 1, you go to the right. Wherever it intersects, it's a count of those conditions, right? If your car is hatchback and the car has symboling of 1, how many such cars are there in my data set? 27. So that's the way you interpret this pivot table, right? And for that, you have to use aggregate function as count. Now you can of course use another aggregate function if you want. And what are we interested in this analysis? We are interested in price. So we will use mean. Okay. So here it's counting the price. And by the way, count is such a trivial thing that it doesn't matter what you put in value. You can put anything in value, still you will get the count. But here when you use mean, make sure that the value you use is the target value. Okay. So it's finding the mean price for these categories. Now you can see nan, not a number everywhere. because there are 0 such entries. So it means how many hard top cars have symboling of -1? 0. There are no hard top cars of symboling -1 in my data set. Okay, so that's why you will get NaN here. And if there is some data, it is showing you the mean price. Now you can look at all of this and do some analysis, like see this for example, right? Hatchback with symboling 3 seems to have a very high price average, $14,000, right? This seems to be very less price. What is this? Sedan with symboling 1 has $9,500 average price. So you can draw conclusions like that. I believe one thing that I missed to mention is, notice that everywhere we are using DF. Okay, here I'm using DF. I am not using XY. If you saw before in part 1, we split things into X train, Y train, and all that, right? When you do EDA analysis and you're not necessarily doing machine learning, that time it's okay to use the full data set that is given to you. Nothing wrong. There's nothing wrong in using the complete data set for analytical purposes. So, which is why everywhere for the analytical purposes, I'm using DF. No problem. Okay, data DF. If you see here, I'm using X equal to DF feature name, Y equal to DF price, which means 205 entries, right? All 205 data points. Okay, so same thing for the pivot tables and all of that. And finally, this is one way of looking at it, pivot tables. You can also do this using bar plot, right? So in the bar plot, you can use X as symboling. So if you see here, -2, -1, 0, 1, 2, 3, these are your symboling categories, right? Y is the price. Okay. So when you do default bar plot, what it gives you in the height, it's the mean price. Okay. So here in the pivot table, I'm using mean price, right? In the bar plot, by default, you get the mean value for the categories. Now, where is this other category coming from? This, what do you call, car body? It is coming from the hue variable. So many of these plots in Seaborn, you can use this thing called hue to separate plots by categories. Okay. So already there is a categorical split on the x-axis, -2, -1, 0, 1, 2, 3. You can also split it by another category, so that you can use hue. Right, and in the previous pivot table, this is exactly what we did. Car body symboling. Okay, here also we are doing car body symboling. Okay, so if you see, everything will correspond. Like for example, if you see this sedan, I'm getting here with -2. I have only one entry. What does this mean? This -2 has only one bar. If you see 0, it has 4 bars. Why? So again, you just need to go back to the count and see. -2 symboling, only sedan cars are there. Look at this row, the count pivot table. -2 symboling only has sedan cars. It doesn't have any other cars, 0, 0, 0. Other type cars not there, which is why you only have the sedan, bar here. -1 has 3 bars. That also you can check here. -1 has 3: hatchback, sedan, and wagon. You can check this using this table also. Wherever it is NaN, it will not show. Okay, so generally we do EDA to develop more familiarity with the data set, right? We try to build familiarity, try to understand what's going on in the data set. From all of this, what I can sense is that there are many types of cars. There are many there are so many features and variables, right, for all the different cars. And it's not really going to be very easy to say this feature affects price or this feature affects price. I hope now we can appreciate that it's not easy. Okay, this data set is small, but it is not very easy to say that okay, this feature is best to predict price. No, we have to go through the whole process of building the models, analyzing the model, and so on and so forth. Okay, we have to do the whole thing. Okay, I may not be expert enough to say why this is like this, but I am closer to the truth about the car prices than the typical individual who did not do the data analysis, right? So this is kind of the power of data science, data analysis, is that you are able to see all these connections, relations. You're able to make claims even if you are not necessarily expert in that domain. Having said that, I hope we all understand this does not mean that I can go diagnosing medical conditions just because I know data science. Okay, so I hope we are all clear on that. But this technique, data science, machine learning, these things, they help you to gain more insights the way we are doing right now. Okay, so one good question is, I don't know if it's a good question, but one question is, why is car price decreasing with an increase in mileage? What this graph is telling me is that higher mileage cars are costing less and lower mileage cars are costing more. In fact, if you want to know the names of the cars also, that is also there. Okay, these are the cars, Audi, Alpha, something. So my guess is that some other features of these cars are making the prices this way. Must be, if there is power of the engine. You mean horsepower? So first, in part 3, simple linear regression models, first we will train and evaluate linear regression models using stats models library. Okay, so if you remember, we loaded the stats models .formula.api. Okay, and we just gave it a name, SMF. I hope we all know we can give any name here. Okay, XXX, whatever. So we have loaded this module, stats model.formula.api, as SMF. Okay, so let's start by building models, as simple as that. So suppose I'm interested in predicting price using car length. Okay, notice that in this case, right, we can use the I am using the complete data set for analytical purpose, because my intention is to build predictive models using Scikit-learn. Now in the industry, it's a choice. You can build a model using stats model or Scikit-learn, whatever. Okay, my interest is to show to the audience through these lessons the analysis part using the full data set, and my intention is to use stats models for analysis. Okay, so if you're using stats models for building a model, then do the splitting of the training and the testing and all that. But generally the popular library is Scikit-learn when you come to machine learning. Anyway, so here I'm using the full data frame. Okay, so I am analyzing the predictive power or the fitting power, you can say, because as you remember, we saw two things: model evaluation, which is goodness of fit, and model evaluation, which is predictive power. Right now we are analyzing the goodness of fit. Okay, so this is the equation that you should be interested in, or not equation, command, smf.ols. Now I'm guessing we all can quickly guess what OLS stands for: ordinary least squares. Okay, so stats models has this method called ordinary least squares, which we saw is one method to do what? To get those best coefficients, right? And the way you write the equation is like this. Right, you this is your target price, and you use the tilde operator. Okay, so on the left side you have the target, on the right side you have the input. So what we are saying is, build me a linear regression model which explains car price using car length from this data. Okay, that's what this command is doing. So if we store this in a variable, what happens is you have a model which is ready to be fit. Okay, then you fit the model using the .fit command. Okay, so you have here LR model 1, linear regression model 1, here LR model 1 .fit. Then you can print out the summary, that is the results of the model. So let me go ahead and run this cell. And everybody, I hope everybody can see the stats models results. Okay, so this is exactly what we saw in the slides. I mean, exactly as in, this is a different model, obviously different data set. As I said, the first thing you can see is this, right, R square, 46%. The dependent variable that we are trying to predict is price. Intercept is very high, must be, the price is always in many thousands of dollars, so there will be some bulk intercept, of course. So it's minus 6,369 or something, and car length coefficient is 442. Now the units of my price is dollars. I think it's in dollars. We should check. Price of car numeric, it doesn't say. Okay, if you go check this, it should probably tell you, that it's in dollars. Generally it should be in dollars, $13,000, $16,000, whatever. So how do we interpret this coefficient here? This means if, and car length units also is something you need to check from the data. I don't know if it is given in the description. Car length, it just says length of car. What is the typical car length? Let's have a look. 173 can the car experts tell me whether this is what centimeter, feet? What is this? Or I don't know, inches. What is the length of car typically? Then if you come here to interpret, what it is saying is, if you increase your car length by 442 units, whatever it is, centimeter or whatever, then your price, if you increase your car length by 1 unit, okay, 1 unit, that's 1 centimeter or whatever, 1 meter, 1 inch, whatever the units are, if you increase by 1 unit, then the car price will go up by $442. Okay, that's what this result is telling me. Okay, but the fit is not good. If you notice here, the fit is okay, 46% R square. Okay. Now there is a specific special plot in Seaborn called regression plot, REG plot. It is essentially a scatter plot with the regression line. So this is the same scatter plot, car length versus price. All these blue dots, these are your actual data points, right? So if we just go up here, car length versus price. Okay, this scatter plot is the same thing here, scatter plot, and then you have the regression line. Okay, this light blue shading is a confidence level thing. Okay, so I won't go too much into that in this session. You will probably have a look at it in the upcoming session. So all that confidence metrics, probabilities, those kinds of things, those values are here. So that will help you to understand this shading. But this is the regression line. Okay, now let's also try to build another model, right? This time let us use the weight of the car to predict the price. Okay, commands are the same, the formula will change. Explain price as a function of weight using linear model. That's how you read this. Okay, now my R square is almost 70%, not bad. So the car length R square was 46%. Okay, and my car weight is giving me 70%. And you can of course interpret the coefficient as usual. 1 unit increase in car weight leads to $13 increase in price. So for this also you can build a linear model. As you can see, the values are all very nicely, almost in a straight line up to $3,000. 3,000 units of weight. Okay, whatever that weight unit is, maybe pounds or I don't know. Okay, you can check the data, but up to 3,000 it's almost like same. Then from 3,000 onwards there's a lot of variation. So there must be something different about cars which have larger weight. Okay, that is another insight you gain from this. Every car less than 3,000 mostly follow some kind of similar model, it seems. As I said, I'm not a car expert, but definitely I would speak to one and I would raise this doubt that less to 3,000 it looks very much cluttered. After 3,000 there's so much variation. Is there like something else going on, right? But as you can see, it's a really nice fit. That is why you have 70% R square. Okay. You can also try other variables, right? You can try horsepower versus price. Okay, I'm getting 65% R square, and 1 unit increase in horsepower leads to $163 increase in price. Again, you can plot the regression plot for this. Okay, so note that when creating and observing these things, we can use the complete data set if you're doing analysis, but when you are getting into the machine learning pipeline for the purpose of deployment, you should only use the training data, okay, for model building. Okay, so now we'll get to Scikit-learn. Okay, there's a slight difference in Scikit-learn. It only it only allows 2D or ND arrays. Okay, so that's why I put the double quotation, not quotation, double bracket here. Okay, so if you, let's just find out the type of this thing, you will understand. Okay, if I do type this, it's a data frame. If I do type, if I just remove one bracket, right, it's a series. Notice that if I do two brackets like this, it is giving me data frame. You can even print and see. If you print this xtrain car length, it's showing me the car length features for my training data points 5, 72, 135, 146. You can confirm this when we did the train test split, wherever we did it. Here, right, xtrain. Okay, the print statement is gone. But if you can actually confirm the same indices, right? Whatever car IDs you are seeing here, exact same, right? These are the indices. And if I do a double bracket of this sort, it will print in a data frame format. Now, if I just remove one set, you are actually extracting the series. It's still a pandas object, but it is now a series. And Scikit-learn does not like series. Okay, generally, Scikit-learn in general does not like single dimensional things like series and all that. So you have to specify it as a data frame. Okay, so here if you notice, I'm only going to use the training data. Now the way that we do in Scikit-learn is, first we initialize a model always, be it linear regression or something else. You initialize a model, then you fit it, right? Same thing we have done in stats models. This will become more pronounced when you deal with logistic regression, decision tree, so on and so forth. Always there's an initial default, then you fit it on the data, right? So I'll say LR model 1 is equal to linear regression bracket. Where is this linear regression coming from? If you go on the top, notice this is the method that I have imported from Scikit-learn. Scikit-learn. Okay, Scikit-learn.linear model import linear regression method. This is the method. Now you can study more about the method if you go see the documentations. Here in Jupyter, you can just shift tab and check. So it's giving you whatever. You can study. Do you want to fit the intercept? Fit intercept, by the way, I didn't mention. Generally, we want to fit the intercept. There may be very few cases where you don't want to fit the intercept. In that case, your line will go through the origin, right? If you don't have the intercept, it will go through origin, but that is very rare case. Generally we want to fit the intercept, which is why the default is true. And of course you can read some other things if you want. Okay, even the fit method also you can read. It's going to have the x, it's going to have the y. Now remember, I'm using x train and y train. I'm fitting the training input feature to y train. Why am I using only one feature? Because we are discussing simple linear regression. Okay, so first you instantiate the linear regression class, right, or object, then you fit it to the required input training data and the output training data. The input training data, I just printed it for you, that is these car length values. Okay, these are the training data points and these are the car lengths. Now same thing, if you want to see the y train is nothing but the car prices, if you remember, right? These are the car prices, 17450 whatever. These are all the car prices. You can see that the IDs are matching, 572, 135. And if you do this, 572, 135, right? Okay, so let's fit. Now you fit the data. You can also, of course, create a regression plot just to check, using these data points. Now, of course, there are less data points, but the plot will look similar to what you saw before. The model has now been fit. Okay, the LR model 1 has been fit. So let's print the intercept and coefficient of this LR model 1. So you can actually access these intercept and coefficient values from LR model 1 object. So if you just do LR model 1 dot and press tab. Okay, if you press tab in Python, you will get all these objects. Okay, from this I'm interested in coef and I'm interested in intercept. If you want to build the model, equation, right? So LR model intercept and LR model coef. So notice the name, there is an underscore after the intercept and things like that. You should be careful when you print that, because that's how objects are generally named, with an underscore at the end. Okay, coef underscore, intercept underscore, right? Values and objects, attributes are named with a underscore. Okay. And the reason I'm doing coef bracket 0, that also I will show you. Here if I just say coef, you will get an array, and inside that array you will get the number. So if you pick out the only element in the array by using indexing, then you will get the number. Okay, if you don't do the indexing, you will get array. All right, because the method is generalized for multiple linear regression, in which you will get array of coefficients. Anyway, so here if you see the numbers -63738 441, I hope we can all see these are very similar values. I remember seeing $442 or something somewhere. Let's check. This is car length versus price. You can see it right here, -6369 442. Okay, and you have here -63738 441. Slight difference because I split training testing data. Okay. What do? Now you have your model, you have your best linear regression model on the training data. What to do next? You have to predict on the testing data. So here is the predict method. So you use the model, LR model 1, you are using the model, use the predict function and predict using X test. Now what is this X test car length? You are using the car length values of the testing data points now. 53, 182, Y6, 619. These are the testing data points. And you have the car length of the testing data points. Same way, you also have the prices of the testing data points. If you put Y test, you remember with the train test split before, right? So 53, 182, 6. These are the prices. Okay. 53, 182, 6. So go ahead and predict. So if you now predict, and I mean, what do you think is the size of the result here? Size has to be 41 because my X test is 41, right? We took 20% of the data as testing. So if I just do len of this array, I will get 41. Right? These are my 41 predictions. And you can in fact check it with the Y test values, right? Y test, and that's what we need to do to compare. See, 6795, 6491, kind of close. 19160, 15750, not that close, right? So basically we want to compare this. And if you remember what we spoke a while ago, how do we compare? We compare using things like RMSE, MAP, right? Root mean square error, mean absolute error, mean absolute percentage error, so on. Before we do that, just giving you a quick comparison for car ID 53, which was in my testing data. This model, which model? The model that you fit, which uses car length to predict price. Okay, the model that we just fit on the data, which uses car length to predict price, that model predicted $6491 for car ID 53. The actual price for that car was 6795. And like this, you can see all the comparisons. As you can see, some predictions are also meaningless. This is going to happen, guys. So look at car ID 19. It is predicting -$1453, right? So definitely you're going to get, some of these will be issues when you come to prediction. That is why in predicting you have to test a lot of models. Okay. Great. One more thing I'd like to mention. I'm showing you this comparison here. Generally when you're doing the ML pipeline in your industry, you do not want to see the testing results at this stage at all. Generally the testing result should be the final result. Okay, I should not look at it and then say, oh, my model is this, my model is that. That we should do using validation data. We'll learn that in the next week. Okay, testing is only for final. I'm doing this here for the purpose of demonstration. Okay, great. That's just the general practice which is followed. Okay. So you shouldn't test the model and then go and improve the model. Don't do that. Okay, which is why you generally we split into 3 parts: training, validation, testing. Then we use the validation to go change my model, whatever. And then finally, when we are happy, we will declare the final results on the testing data. Here I'm directly showing for the purpose of demonstration. Okay, let's then now actually summarize the predictive power of LR model 1. So I will gather the predictions here. As you can see, LR model 1 dot predict X test car length. I'm using the car length feature of the testing data, using my model which was fit on car length versus price to predict the price of the cars in the testing data. Okay, that's what this is. Then RMSE is nothing but what? Root of, mean of, square of, right? But there is already a method in Scikit-learn. We imported it before, if you remember, Scikit-learn dot metrics import mean square error, right? So you can directly use that to do the RMSE. So why am I doing SQRT? Because mean square error gives me mean square error. I need RMSE, so I'm doing numpy dot square root. Okay, so numpy square root mean square error. What are you comparing? So the parameters here are y true and y pred. So in y true, what should I send? I should send the testing y values, the actual car prices of the testing data. That is in y test. Okay, and in y prediction, what I have to send? I have to send the predictions of those cars in my testing data using the car lengths, right? So using the car length of the cars in the testing data, I used my model to predict the prices. Note that the model has not seen this data at all. If you go back and see the fit statement, you are fitting only on X train, Y train. This model has no idea about the testing data. 41 data points it has not seen. So essentially it is fairly being tested. I hope that is clear at this point. Essentially we are fairly testing the model now, right? It has not seen these 41 data points at all, and it is attempting to make the predictions. Okay, so that's how you get the RMSE. And MAP is a very simple formula. I told you it is just the error y test minus predicted y divided by the actual. So you get the proportion, right? You take the absolute value of that proportion to remove negative sign. Now you have some kind of percentage of the original value, which is the error, and then you just average it, okay, across all 41 points. So np dot mean, numpy dot mean. I'm just rounding it so that it looks clean, and I'm storing all my data results, in a data frame. So I'm just going to store it with the model name in the sense, not car model name, my linear regression model name. So SLR using car length, okay, and then I'm going to store RMSE and MAP. So here I have SLR car length model 6593 RMSE. That's a lot of error, right? And you can see that in the MAP also. So in a way you can understand this as $6,500 error. That is very bad, right? Very bad, because you can quickly check that also. DF price, say median, right? The median car price is $10,000. So your model right now is giving $6,000 error with the car price of median car price of $10,000. That's not a good model, obviously, right? So it is failing in terms of predictive power. It is failing, and you can see that in the MAPE also. 33% error is bad. Now you can do similarly for the other models also. Okay, so LR model 2 linear regression, first instantiate the model, right? Declare an instance of the model, then use the input variable that you want to use. So this time I'm using car weight, okay, to predict the prices. So go ahead and fit the model. You can check the plot if you want. You can interpret the coefficients and intercept if you want. So this time you take LR model 2 and take out the intercept and the coefficient. Intercept, as I said, not much interpretation to be done here. Here's the coefficient. You can match this again with the stats models output. Car weight, this one, minus 194800 something, 12.8162, right? So here also I'm having minus 188 something and 12.47. Slight difference again because the stats model output is for the 205 data points. This is for 205 minus 41, whatever that is, 162 data points, right? Training data. Again, we can go ahead and calculate the RMSE MAP, just copy paste the code once you understand it. There is an improvement. As you can see, there is an improvement, 5024 and 23.13. One thing to note is, if you see here in the stats model analysis, this car length model had 46% R square, okay, and the car weight model had 70% R square. So in terms of goodness of fit, the car weight model is better than the car length model in terms of goodness of fit. Generally, typically, better the model fit should lead to better predictions. This is what we will think intuitively also, right? If my model is not at all fitting the training data, then how can it do prediction on the testing data or new data? That is correct. A model has to fit well to the training data. Then it is capable of predicting well on new data. So that is very, very evident here. 46% R square, 70% R square. So clearly the car weight model is stronger fit than car length model and potentially can do better predictions. Potentially. Why am I saying potentially? Point number one, I'm showing you how to do the comparison. As you can see, you're doing this training, testing, splitting, finding the error on the testing set. And obviously, you see the car weight model is better. It has a lower error, right? 23% instead of 33%. That is a better error. But why did I use the word potentially? There is something in machine learning called overfitting. We will get into details of overfitting and all these things in the next week. But after a point, if you fit the model more and more and more, it starts to lose its predictive power. Okay. So we'll see what that means in next week. But in short, I just want to talk about it. It's like if you mug up all the questions in your 3 pre-board exams, then that means that your fit of the pre-board exam questions is 100%, right? R square for the pre-board examination is 100%. You remembered all the questions and all the answers in the pre-boards. Is that a good way to prepare for the final board exam? Think about it, right? Are these two perfectly correlated? Perfectly, right? If you mug up all the questions, not learn the technique or not learn the formula, not explore other books or whatever, not ask your friends and peers, okay, is there any question you heard about, right? All that is what we do for generalization purpose, to make ourselves better prepared for the final exam. Correct? If you just mug up, then who is in a better state to write the final exam? Same way, think about here. Okay, to some point, R square, which is the fitness, goodness of fit, of course you require. If you did not even study anything for pre-board, then of course board exam, what's going to happen? So to some point, yes, goodness of fit should be high. But at what point are you going to say it is too high? The training data fit is so high that any new data it's not able to understand. Okay, so this is something that we will discuss in the next week. Let's get back to this one. Okay, so I hope that is clear. Okay, so here if you see the results, 46% and then you have 70%. So the car weight model is better. In fact, you see this one also. Okay, horsepower. So horsepower is 65% R square. So I'm expecting it should also be doing better than the first model, which is car length, right? So we can go ahead and test that also. Go ahead and instantiate the linear regression, fit the model using the required input and output. Check the plot if you want. Look at the coefficients if you want. You can match these with the coefficients at any time and go ahead and do the computations. Yeah, as you can see, it is doing slightly better than the car length model and little worse than the car weight model. So till now, the R square and the predictive metrics, they are supporting each other. Okay, so we have not come to the point of overfitting because simple linear regression model mostly cannot overfit. Multiple linear regression models have a tendency to overfit. So when we do MLR, we have to think about overfitting. Okay, so for this, I would like to say that the weight of from these three models, at least what I can say is that the weight of the car is generally a good indicator of the price of the car. Okay, if I have to use only these three, out of these three, I will use which one? I will use this one. It has the lowest error, 20%, which is still bad, by the way. 23% is very bad error. Okay, we should try to get it to 10%, 5%. So industry standards will be like 2%, 3%, right? So we have to try to get it till there. But you cannot do that with simple linear regression models. Just not possible, right? Because one variable is insufficient to explain the variation in the car prices, right? As I said, these are of course very simplistic SLR models. MLR models along with some tuning should be able to do better. This will be the major theme for the upcoming week. Okay, let's get into MLR models. Quick introduction. See, in simple linear regression, we saw that there was exactly one predictor. Okay, so the target variable is explained using one predictor. In practice, we know that the real world is obviously way more complex than that, right? One variable is insufficient. And we saw these values also, the car price thing, right? Best R square we saw was 60% or something like that. So yeah, I mean, the real world is quite complex. So we need to include more variables. For example, if you could build an SLR model which predicts sales using investment, right? Investment is one variable. But sales obviously depends on many other factors. It depends on investment. It depends on the pricing of your product, number of resources, and of course there are so many other business related variables, right, which influence the sales. So generally that is why we generalize SLR into MLR, which is multiple linear regression. So suppose we have a data set with n+1 features. Okay, so you have n+1 features, which means columns, in which one is our target feature, which is y. So the remaining n features, so the rest n are predictor variables, which is your input. So then your MLR equation is going to look like this. This y hat, this is your predicted target variable, and this is your constant or intercept beta naught. And then you have these terms for each of the remaining predictor variables: beta 1 x1, beta 2 x2, up to beta n xn. So each term has the value of the variable, that is x1, x2, xn, that is the actual variable value. And you have beta 1, beta 2, so on, which is the coefficient or the strength, you can say, of that variable, right? So x1, x2, xn, these are your n predictor variables. Now for two predictors, we can still visualize. Now see, if you see the equation, y hat equal to beta naught beta 1 x1 plus beta x2, in 3 dimension it's actually a plane, okay, and it's not a line. Okay, essentially only in 2 dimension it's a line. Okay, when you take this to 3D, so if you say y equal to beta naught plus beta 1 say x plus beta 1 beta 2 z, so you have 3 axes x, y, z. This is the equation of a plane. Okay, if you just rearrange, you will get beta 1 x plus b plus y or minus y something, beta 1 x minus y, this is what you will get, beta 1 x minus y plus beta 2 z, right, plus beta naught equal to 0. So this is equation of plane, right? And if you go to 3 dimension, 4 dimension, so on and so forth, essentially you are having new geometric structure. It's not a straight line. Okay, it's a straight structure but not a line. Okay, so you can call these things hyperplanes or hyperlines. Okay, regardless, we can visualize how well it is fitting. See, in 2D you can visualize, okay, line is looking good, line is looking bad. In 3D also you can somewhat see, okay, plane is fitting my points or not, or plane is looking bad, looking good. But beyond that we cannot visualize. So we need to understand the math properly, okay, in this. Now that's understand the math, and and which we have already done, by the way. We've seen how to find the SSE. Same concept here also, exact same concept. You find the sum of square errors, right? And then you find the R square. All the formula, everything remains the same. The only difference is that now you have multiple predictors. Now there's a difference in terms of interpreting the coefficient. What is meaning of coefficient? And there's also differences in which features are more important, which are less important. So we'll get into those kinds of things today. Okay. So coefficient interpretation. Now, if you remember the simple linear regression, we said that one unit change in coefficient results in, sorry, one unit change in input results in beta amount of change in output. This is what we saw in simple linear regression, right? In multiple linear regression, what you're looking at is actually partial contributions. Okay. So think of it like, for example, if we fix the values of n minus 1 of these variables. So suppose I fix x2, x3, x4 up to xn. So all of these values I fix at a certain amount. Then you can interpret beta 1, that is remaining, this one. Okay, the remaining one, beta 1, you can interpret as normal, whatever you interpreted last time. That is the average change in the target variable for unit change in x1. But this is only true for a certain level of x2, x3, x4, x5, xn. So you need to fix those things. Once you fix those things, then for that fixed level, x2, x3, x4, whatever, right? These are all fixed. For that fixed condition, the interpretation is like simple linear regression. Okay, more on this later. So in multiple linear regression, you take our data set. Remember, we have this coffee expenditure data set just to understand the concepts, right? We have gender, job, income, age, and we want to predict the amount. We have 10 people in the training data. So now you can think of, amount spent on coffee can be explained as a linear combination of income and age. It can be linear combination of job and income. It can be linear combination of gender, income, age, so on and so forth. So now there are many different considerations that come into play. In simple linear regression, we just took one variable at a time and we fit the linear regression model. Okay. So x-axis was the input, y was the output. Keep changing the x-axis for each model. That's all. Fit income, fit age, fit job, whatever it is, right? You keep fitting and seeing what is it fitting well? What is the R square? Very simple. Now in this case, multiple linear regression, what are you going to do? Are you going to find out all the combinations? See, here I have 4 columns. Quick combination tells you 4C2, right? 4 into 3, 12 by 2, 6. There are 6 unique models that I can build. If you have, say, 20, columns as predictors, then use the combinations formula, 20 into 19 by 2, 190 models you have to check, right? So there are many considerations when you talk about MLR. Okay. So let's talk about the first MLR, very simple multiple linear regression model. Okay. Let's talk about predicting amount or explaining amount using income and age. Okay, we are taking two numerical predictors here, income and age. So let's fit an MLR to this. Okay, now I've gone ahead and I fit it because the equation and everything is very simple. Okay, we'll look at the equation soon, but I've gone ahead and I fit the model in stats model. Using stats model. Okay, so now you can see dependent variable here is amount, right? Here the dependent variable is amount, and you can look at what are my independent variables here. So of course I have intercept, and then I have income, and then I have age. So intercept is the constant. Okay, so now you have two numerical variables, right? One income, one age, and the R square value is around 78%. Okay, and this kind of tells you that income is significant, maybe age is not significant. Okay, so okay, we fit a model. Now how do I interpret this model? Okay, fitting the model is fine. As I said, it's the same thing. Y equal to beta naught, beta 1x. You have a hyperline or a hyperplane type of geometric object. You're fitting it in an n-dimensional space, and you're essentially minimizing the SSE, sum of square errors. Okay, for doing that, you're using things like gradient descent, or ordinary least squares. There are many methods. So fitting and everything same, okay, more or less the same. Let's build the equation for this, okay, this model. So we are using income and age to predict the amount. Yeah, so here is the coefficients. See, the predicted amount is equal to 184.24 plus 0.025 times income plus 6.8 times age. This is your equation. Okay, this is your linear regression equation. Now, how do you interpret the coefficients? Right, that's the main thing. See, intercept is more or less the same as before. Okay, I'm not going to go too much on the intercept. Let's talk about these slope coefficients. Suppose I fix my age at 50 years. Suppose I fix age at 50. Okay, so then I can say predicted amount, and I'll just write here age equal to 50. Predicted amount for age equal to 50 is equal to, what's the equation going to be? 184.24 and 6.8 times 50, correct? So that's 340, correct? So 340 plus 184, you're going to get 524.24, I believe, plus 0.025 times income. Okay, this is what your equation is going to become. Okay. So you fixed the age at 50. What I'm saying is, for all the people whose age is around this 50 mark, for them, if you increase the income by 1 unit, then the amount spent on coffee increases by 0.025 units or dollars. Now, of course, this is the same for if you fix age at 51, it's the same if you fix age at 60 or even 20, whatever it is. The change, right, the update in the amount spent due to income will be the same, but the predicted value will be different, correct? So because of the constant changing, the predicted value is going to be different. Similarly, if you fix income, suppose you fix income at 10,000 or 100,000, right? I don't know the ranges. Okay, 64. So suppose you fix the income at $50,000. So then you get predicted amount for income fixed at $50,000 equal to, so 50,000 you just substitute in the income, right? So that's 1250, right, plus 184, that's 1309, I believe, right? No, that's 1434, sorry, not 134, 1434.24 plus 6.8 times age. Okay, so if you vary both, then the predicted amount, to calculate how much it varies is difficult. You fix income, then you can say, okay, for all the people around $50,000 income, you increase the age by 1 unit or 1 year, then the amount spent on coffee will increase by $6.8. Okay, same way, you can make a claim for fixing the age and then finding the change in income. If you change both, then the interpretation is little difficult. Okay, so this is how you can think of multiple linear regression in a inferential or analytical setting. All right, let's take a look at another model. Okay, this time let's say we want to build an MLR model using job and income to predict amount. Now notice that job is actually a categorical variable. Okay, it has 3 levels: business, service, government. Okay, so job is categorical and income is numerical. So here is the fit. Okay, this is, as you can see, dependent variable is amount, and you can see the variables here: intercept, job, income. The R square is 81%. That's nice. But more importantly, what I want everybody to see here is this coefficient box. Okay, so let me separate out. Yeah, so intercept is intercept. Let it just be there. Because job has 3 levels, remember, you converted job into the category data type. Because of that, linear regression models immediately understand how many levels there are. In fact, if you remember the demo, when you change to category, when you convert data type from string to category, it gives you a list of the levels. Okay, so this job has 3 levels. It has business, government, and service. Okay, 3 levels. And notice it has taken 2 dummy variables, right? It has taken job government and job service. So basically, alphabetically, which one came first, it took as default. So business starts with B, right? So it has taken B as the reference category, business as the reference category. Now, what are the values that these things take? So basically, on the back end, what's happening? You have job business, you have job government, you have job service. Okay, job service. Now, suppose somebody has a job who is from government. Okay, their data entry on the back end is going to be 0, 1, 0. I hope we all understand this one hot encoding, right? This is called one hot encoding. So if somebody has a job from government, the encoding on the back end is going to be 0, 1, 0. You cannot see it here, but this is the way it is treated. Okay, when you convert to category, this is how it's treated. If you want to see it visually, then you have to use pandas get dummies. Okay, to see these columns visually, which we will do. I think today we'll show all that. Anyway, so if somebody is from government, you have 0, 1, 0. If somebody is from what is that service, then you're going to get 0, 0, 1. And if somebody is from business, you're going to have 1, 0, 0. Now, I hope everyone also understands there is an extra information. If you keep all 3 columns, there is an extra information, because see the third row. Just see the third row. If I know that my original job has only 3 levels, business, government, service, and I know that this data observation or this person is not government and not service, then 100% they are business, right? So the knowledge of not knowing too, that okay, this person is not from government and not from service, means we know they are from business. So that information is encoded into the intercept. That default information is encoded into the intercept. Okay, so when you put government equal to 0, service equal to 0, you are actually getting the answer for businessman, because that information goes into the intercept. Okay, so how to use this equation now, right? Suppose that I am talking about somebody who is from government. So then their variables will be like this, 0, 1, 0 for job, right? So predicted amount for job equal to government, that will be equal to what? 21 basically 217.17 plus 145.53. What's that? 362.7. Yeah, 362.7, right? Because G equal to 1, government equal to 1, service equal to 0. So plus 0.027 times income. Okay. So now this is going to be your analytical equation for somebody from government. Okay. So of course the effect of income is same for everyone, right? But again, the predicted amount is going to change. Now, if you fix income, that's where it gets interesting. Suppose you fix income at $50,000 or something like that, right? Then very interesting thing, what you can see is that you are looking at averages. So suppose I fix income at 50,000. Okay, so I'm going to get 1350. I think 50,000 into 0.027, whatever. So predicted amount with income equal to $50K, right? This is going to be equal to 1350 plus 217. So 1567, I guess, 0.17, plus you have 145 times your government plus 206 times service. So now essentially if you put G equal to 0 and S equal to 0, then you get 1567. Basically how to understand that statement is, all businessmen whose income is around $50,000 at an average spend $1567 on coffee. Okay. So if you go back to your data set, single out all these businessmen who have $50,000 around income and you take the average, you're going to get 1567. Okay. Similarly, if you say G equal to 1, that means service has to be 0, business has to be 0. Okay. Because person is from government. So then you get 1567 plus 145. Which is whatever 1720, something like that, 1750 approximately, right? So then the statement is, but remember, income is fixed at 50K. So all government people with income around 50K spend $1750 on coffee. Okay, so this is how you use the combination of categorical and numerical variables when doing analysis. Okay, using regression models. Okay, so here let's go for another model. We'll go for model 3. In this case, I think we are using all the variables. Yeah, we're using gender, job, income, age. Okay, the only thing significant seems to be income, right? But yeah, I mean that's how you would analyze this, right? By looking at this, I would say okay, 0.046 p-value for income. Sure, income is making a big difference in predicting the amount spent on coffee. Okay, other things are not making so much difference. Is what the model is trying to say. But with 10 data points, you shouldn't take this seriously. Okay, when we do the demo, we'll see. Anyway, so in this case also you can see gender has two values, male, female. F comes in alphabet first, so by default it is taken as the what do you call reference category, right? So then you have only the dummy variable for male. Same way in job, that is business government service, B is alphabetically the first one, so it's taken as the reference category. Null category, you can say 0, right? And then you have government and service dummy variables for job, which is why you're seeing gender male is here, and job job government and job service are here. Again, this is exactly like a pivot table. Okay, this is essentially when you combine categorical and numerical variables and build linear regression models out of it. It's kind of like a dynamic pivot table. Okay, so you fix income and age at certain levels, and then you change the dummy variables or the categorical variables with zeros and ones, and then you are making claims about averages of groups essentially, right? And you can do the same by fixing the categorical also. So the whole point is that when you do pivot tables and all, you're limited, right? You can only have one condition here, one condition here. If you try to use what is that bar graphs and things like that, you're limited to the number of variables that you can encode. Linear regression allows you to encode how many variables? N number of variables, right? You can perform analysis using N number of variables. That's kind of the power of linear regression. So this is kind of what your equation is going to look like. Interpretation is similar and so on. Okay, I have a few answers here, and everyone is saying it's A true. Yes, that is right. Let's break this down before we continue. Okay, this is my linear regression equation on the top. Predicted sales is equal to some intercept plus 4 times number of salespersons plus 3 times budget size. Okay, it says here sales is the amount of money made in thousands of dollars. Let's keep that in mind. So the unit here is thousands of dollars of sales. N salesperson is size of the sales team. Okay, so how many people? Budget size is the amount of money allocated to the sales team in, again, thousands of dollars. Let's keep this also in mind. Now, before we go to the statement which is written here, let us ourselves try to interpret, right? According to this linear regression equation, intercept is already constant, so forget about that. If I fix this n salespersons, if I fix n salespersons at some number, I can fix it at 10, I can fix it at 100, whatever, right? Then the equation essentially boils down to sales equal to some constant. I'll just call it k. Okay, generally nobody calls it k, I'm just calling it k. Some constant k plus 3 times the budget size, right? Because n salesperson is fixed, intercept is constant. So this whole thing, intercept plus 4 times n salesperson, that whole thing becomes constant. So now the equation is what? Sales equal to some constant plus 3 times budget size. Essentially, whatever you do to the budget affects the sales 3 times. That's exactly what this number says. If I increase budget by 1 unit, sales will increase by 1 unit. If I decrease budget by 1 unit, sales will decrease by, sorry, not 1 unit, 3 units. Okay, that's the coefficient. So increase budget by 1 unit, sales increase by 3 unit. Okay, decrease budget by 1 unit, sales decreases by 3 unit on average. Essentially, the linear regression model has gone through your full data and understood that this is the most optimal relationship it can convey to you. Okay, you will find a similar thing if you do analysis of averages of groups, right? This is what I've been saying since day one. Linear regression is a very simplistic model in that sense. Okay, it's giving you holistic information in terms of averages. Okay, so now if you increase your budget by $1,000, that means what? 1 unit, because the units are thousands of dollars. So the sales will increase by what? 3 units. That's the coefficient. And what's the sales unit? Thousands of dollars. Okay, so $3,000. Great. For what? For the same sales team size. This is very important. See, if you're going to compare teams of different sizes, then this doesn't work. But I hope this example shows you how to really, use this to understand. Use linear regression to understand the business problem. Basically, it's saying, supposing you have a situation in your business or in your system where say you have 2 teams. Suppose you have 2, say, sub teams of sales. Okay, and you have the same team size, say 50 salespersons here, 50 salespersons here. Okay, then what is linear regression really telling you? It is telling you that for these 2, if you want to compare why the sales are different, maybe you should look at the budget. Right? So I hope you're all understanding how to use linear regression to analyze our data. Okay, cool. So that's the introduction to multiple linear regression and its coefficients and things like that. Of course, now we have multiple variables. Then the question is which variables to use, which variables, how much to use, what is the influence, all sorts of questions are going to come up. And as I said, there is the question of complexity also, unnecessarily using more computations to get worse results sometimes. There is something called overfitting, which we will see in the next class, in the next lecture, right? So all of these questions are going to come up. Let's start with behavior of R square. Very interesting behavior. So this is, this is basically the coffee data set, the 10 training data points. Okay. And what I want everyone to observe is the model, the number of predictors in the model, and then the R square of the model. Okay. So if you see this column, predictors, it shows the predictors that we used model by model. Okay. So you must have seen model, red model was the basic model that I used, income versus amount. Then you may have seen, when using categorical variable, gender versus amount, job versus amount. These are all one variable. Okay. In this session, you have seen income and age, 2 numerical variables to predict amount or explain amount, and so on and so forth. What I want you to observe here is that as the number of predictors increases, R square typically increases. Okay. Does this mean that you're doing a good job? Right? Generally, what happens is, see, your target variable is a real variable, so it's going to have fluctuations. Your input variable is also a real variable, it's going to have fluctuations. It's very rare that the correlation between an input and a target is 0, exactly 0. Very rare. So if the correlation is not 0 for any random variable, so for example, in this case, I can even take, temperature in the city opposite to the, on the opposite side of the earth. Suppose this coffee shop is in US, right? In USA, then I can take a city in China, record the temperature there as a data, add it to this data, use it as a predictor, and my R square will typically increase. It's weird that way, right? It will use any correlation available to start explaining the variance or the variation in the target. Okay. So R square typically increases as the number of predictors increases, right? Then the question comes, does it actually then imply good predictive model? Are you learning for the future? If you remember the examples that we used last time, are you well prepared for your board exam? Right? That's a good question. If just studying anything gives me R square, good R square, am I prepared? Right? So just having a high R square does not uh, ensure you, at least I will say, it may give you some confidence that you have a good model, okay, but it does not ensure at all that it's going to perform well on unknown data, right? So there are some ways to handle this. So one thing you may have noticed in all of these stats model summary results, beneath R square there is something called adjusted R square. In fact, yeah, if you see here, right, there's something called adjusted R square, and you will notice that it's much less. Look at this, right? The R square in this case is 90% and the adjusted R square is 77%. This is all the variables taken together model, right? So there is this one concept called adjusted R square. So the only thing you need to know here is there's a formula for it. Nobody's expected to remember the formula, but understand the denominator here, n minus p minus 1. So p is basically the number of predictors. So you have minus p. Okay. So the more the number of predictors you have, the smaller this denominator is going to be, because minus p, and smaller the denominator means greater the fraction. Greater the fraction, you are actually subtracting from 1. So finally your adjusted R square is going to be less. Essentially, more predictors if you use, it is adding a penalty. Okay, you are adding a penalty on the linear model. If I'm using more predictors, then I'll not go with the actual R square, I'll adjust my R square. Okay, so there's this formula for adjusted R square. So more predictors, less adjusted R square. It decreases the R square value. So if you apply the same to these models, again, these are the models on the coffee data set. We just saw these, right? These are the yeah, so these are the R square values that we saw. Okay, so as you typically, by the way, I said typically, so I mean, please don't say income model has 75% R square and job has 50, so it decreased. That's not what I'm saying. Typically, when the number of predictors increases, typically it will increase. Okay, here and there you might get higher and lower, but generally speaking, the R square increases. Okay, now look at the adjusted R square value. So if you see, in each case it is negative. In some case it is negative, sorry, not each case. In some cases you will find it negative also. And in most cases what's happening is it is, reducing the R square value. So 78 became 72, 81 became 72. In fact, if you see these two models, it's very interesting, right? Just to show you how to use this adjusted R square for comparison, consider these two models. Okay, income and age, job and income. So if I use income and age to predict coffee amount spent on coffee, sorry, the R square is 0.787 and adjusted R square is 0.726. If I use job and income, the R square is 0.817, but the adjusted R square is 0.725. So essentially what it's saying is your R square may be much larger, but both models seem to be performing similarly. Okay, so if you see the adjusted R square, it says that the models are similar. Just because the R square is more doesn't mean it's a much better model. Okay, but see, in practice what I will say is that even this thing called adjusted R square is, it's an attempt to adjust the behavior of R square, right? As I said, R square will go on increasing if you go on putting predictor variables, right? Here and there you'll get some dip or whatever, but as and when keep adding more variables, your R square will typically increase. And adjusted R square is what? It's nothing but an adjustment to the R square, right? So I will not say that it is an effective indicator of predictive power. Okay, because the model has not seen any predictions, right? The model has not tested itself on any new data. So for that, you really need predictive performance metrics only. Okay. Anyway, now coming to some other issues in multiple linear regression. So you see, if you remember, we started linear regression, simple linear regression, all this we started using scatter plot and correlation. If you remember, right, we said, hey, correlation is a nice metric to understand whether one variable and another variable are influenced or not, right? It's a good way. High correlation means something is happening. Low correlation means something is not happening. Which is what we started the series with, right? Scatter plots and correlations. And then we said correlation cannot be used for prediction. Okay. So if a predictor is correlated with the target, that's usually a good thing. That's a good thing, right? You want to understand target variable variation using an predictor variation. There has to be correlation. Okay, that's usually a good thing. But if a predictor is correlated with another predictor, okay, if two predictors are correlated, then we say there is this situation called multicollinearity. Sounds very fancy, right? But what it means is that one of your predictors may actually be explained as a linear combination of some of the other predictors. Let's take some time to understand this. Okay. So in this case, what happens is that the predictor becomes redundant. See, if you can explain a predictor using some other predictors with, say, a high goodness of fit value, then why are you using that and this to predict the target? Okay. It increases the complexity of the model essentially without offering any additional ability to learn. Okay. And what it does is it ends up inflating the goodness of fit of the model. Why? Because you're using more variables. We just established that using n number of variables will inflate your R square value, make your system more complex, right? And if there is some predictor which is a perfectly linear combination of some other predictors, then we don't even need the predictor. Okay. So how do we identify such things? One way is correlation matrix. So in my coffee data set, you can see there are only two numerical features. So age and income are not correlated. 0.16 is okay, no problem. For categorical predictors, you have to convert to dummy variable, and then you can do all this, and you can see is there a high correlation, low correlation? You can see. So this is almost uncorrelated, gender and income. Okay. Government job and income seem to be correlated, so on and so forth, right? One problem with this is that the correlation matrix gives you only pairwise correlation. Okay. So my question is, what if more than 2-3 predictors are influencing one more predictor, and where can I get a combination of those influences? Correlation matrix will give you some understanding pairwise, right? So if you want to know if more than 2-3 predictors is influencing another predictor, there is something called variance inflation factor, or VIF. Okay, it's very simple. Okay, I'll tell you the general procedure. So what you do is you remove the target from the data set first. So if you remember our coffee data, gender, job, income, age, amount, remove the amount, just remove the amount. So now what do you have? You have gender, job, income, age. These are the predictors, right? What you need to do, take each predictor, explain it as a linear combination of the remaining predictors. What does that mean? Linear regression. Take gender and fit a linear regression using job, income, age. What is the target now? Gender. Same way, take job and then use gender, income, age, fit a linear regression model for job. So if you do this, you'll get 4 regression models. Now I am trying to say, if any of these regression models have very high R square, then what does that mean? For example, if you say the last one, right, age equal to linear regression of gender, job, income, suppose it has 95% R square. What is the meaning of this? It means gender, job, and income explain age almost perfectly. Okay. In other words, if I know the value of gender, job and income, I am 95% accurate in calculating age. Then do I need age in my original linear model? They are giving the same information, right? Age influencing amount and gender, job, income influencing amount are the same. Why? Because age is almost 95% explained using gender, job and income. Okay. So this situation is called multicollinearity. All right. So if any of these linear regressions has a high R square, then that particular target predictor suffers from multicollinearity in the data set. So what do? We create a measure which is inversely proportional to this R square. Okay. So here in any of these models, if the R square is high, I need my metric to be low. So that is what variance inflation factor actually does. So the formula is 1 by 1 minus R square. If R square is high, 1 minus R square will be low and VIF will be high. Now, of course, I need not have taken the what you say reciprocal, but generally, universally, everyone wanted a uh, kind of decent value to look at. If you leave it as 1 minus R square, you'll get 0.0000 something, right? So they took the inverse. Okay. So this is how it looks, right? You find R square for the gender model, you find R square for the job model, and so on. You get the VIFs. And typically now what? Because it's 1 by 1 minus R square, if R square is high, then 1 minus R square is low and VIF will be high. In other words, I don't want high VIF. If my VIF is high, that means that particular model's R square is high. And I hope everyone understands we are not even considering amount. Amount, that is the original target, is completely removed from the data set. Okay, we are only looking at predictors as combinations of predictors. Okay, these are the models that I'm talking about when I talk about VIF. Amount is not in the picture. Okay, great. So typically, okay, so VIF is a measure of multicollinearity. If the VIF is high, that's not a good thing. Basically, the ith predictor might suffer from collinearity. Range is 1 to infinity. That's kind of obvious. If you look at this, I know R square goes from 0 to 1. So if R square is 0, then VIF is 1. If R square is very close to 1, then VIF will be close to infinity. Correct? So VIF 1 means R square is 0, which is a good thing, right? If VIF is 1, that means this R square was 0. Then only 1 by 1 equal to 1, right? So that's a good thing. If typically VIF greater than 5, is considered as a high VIF value. But I would say again, you'll have to do the analysis on the data and understand, right? It's not all the time that you're going to get very nice VIF values. Okay, it depends on the amount of data you use and many other kinds of factors. In fact, categorical variables cause issues in the interpretability of VIF. So if you just take numerical variables, you'll get set of VIF. The moment you introduce categorical, those will change drastically, right? There are a lot of interpretation issues with VIF, I will say. So I'll show you in the demonstration how to understand and use all these things, right? Anyway, so when you're dealing with multicollinearity, what are the things you can do? You can drop some features if you feel that they are highly multicollinear. If you feel something is well explained in terms of some other variables, you may choose to remove it. You can also create interaction features, right? You can do multiplication, things like that between features. We'll not get into that too much, right? You can also do a transformation, like you can change the scale from whatever it is to log scale, things like that. You can try these. We will be focusing on the first method, as we go ahead. All right. Yeah. So before getting into feature selection, now, as I said, right, in multiple linear regression, we can blindly use all the, the predictors and call it a day. I have 20 predictors. My MLR model has 20 predictors. Okay. End of story. That sounds nice and sounds good, but I gave you multiple reasons why it's not good. Why? You think you're doing good, you think you're doing good model building because your R square increases. Why R square is increasing? Because you're using, let's say, 20 predictors, all the predictors in your data, very high R square. But I just told you it's not indicative of the predictive power. Secondly, there are issues called overfitting, okay, which we will see in later next session. But please be informed there is something called overfitting. Okay, you cannot overfit your model onto some limited training data, then it will not perform well on testing data, right? And we saw many other reasons. Complexity, why do you want to waste computational resource? Many reasons why you shouldn't blindly just build an MLR using all the predictors. Okay, having said that, what should we do? We should select features, right? But feature selection in general is not a straightforward process in linear regression. Later when we do some other ML models, we will be talking about feature selection and things like that, and you will think, oh wow, it's so easy, right? In linear regression it's not that easy. Okay, feature selection is not straightforward. Maybe easy is not the right word, but it's not straightforward. Okay, there are techniques that you can explore, right? I'm not going to do these in my demos, right? But you can feel free to explore. Recursive feature elimination is very popular method, right? First I would suggest you implement and play with the notebooks that we are doing, right? Then you may go ahead and, as an additional reading, I would say try RFE and things like that. Okay, so we will try to do this manually, okay, and understand things. Male, female, and so on. Okay, so here I have male, suppose female, and then I have female, and then I have male. Okay, MFFM, suppose. So here convert this to dummy variables, right? So you're going to get gender male, and then you're going to get gender female. So GM and GF, gender male and gender female. So in the first entry your gender is male, so that's 1 0. Second entry gender is female, so 0 1, and so on, right? 0 1 1 0. This is how it's going to look. Now if you choose female, which is alphabetically comes before male, I think, so female will be default. So suppose y equal to some intercept, right? Y equal to some intercept plus you have beta times, what will you get? GM, beta times GM. So you're gonna get no, there's some y equal to intercept plus some issue with the net, I think, plus beta times GM. Okay, gender male. Great. That also didn't come properly. Beta times GM. Yeah. Now for the first entry, value is male. So we are talking about male. Suppose y is amount of coffee. Okay, suppose y is amount of coffee. So for the male, I'm going to put GM equal to 1. So now what is the y predicted value if it is a male? Then that is equal to intercept plus beta, because GM, gender male, equal to 1. For a male person, the male variable will be 1. So now you have intercept plus beta. Okay, INT intercept plus beta, right? Intercept plus beta, that is a constant. You will agree that is a constant, right? Now for the second entry, f, which is female, so your m variable is going to be 0. So your linear regression equation will just be intercept, correct? So f, right? Yf is equal to intercept. Now don't you think this looks like a bar graph? So what I'm asking you is, don't you think this looks like a bar graph? If I just make a graph, right, and I just do categorical using male and female, so I put m here, I put f here, right? I put m here and f here. The average amount of coffee that males spend according to my linear regression model is intercept plus beta, whatever some constant. So you're going to get some bar like this. That's all. And same way for females, because the GM variable will be 0 after one hot encoding, So that's just intercept. So the amount of coffee spent by females is a little less on average. This is exactly what a bar graph does, right? When you do bar graph and you choose what you say, the categorical variable as the x-axis, on your y-axis you get average target values, right? When you don't have any target, it's called a count plot. You're counting the number of entries. When you have a target, you get the different bar sizes, right? That's actually giving you the average target value. And this is the exact same thing you can do using pivot tables also, right? So visually, this is exactly what is happening in the linear regression. Now, suppose you add a numerical variable into the mix, then it's nothing but shifting of the line. So, right, suppose I have graph like this, and suppose I'm also taking age. Now you have asked what if there are two categorical variables, say male and female. That is one variable, gender. What if I take age also? So what you might end up seeing is something like this. Okay, you will see one line here, and just shift it up. You will see one more line here. This difference is essentially this beta. If you put male equal to 0, then you're getting the linear regression for the female. If you put male equal to 1, you're getting the linear regression for the male. So this difference here, if you see this difference, that is exactly equal to this coefficient of the gender variable. Okay, so here if I just show with arrows, yeah, so this will be equal to this gender beta. Okay, this difference is equal to the beta of the gender. So what is the one on the bottom? It's the one without the beta, so that's females. So this is the linear regression for females, which is amount of coffee spending versus age. So here my x-axis that I'm showing you is age actually. Okay, so I just wanted to show what will happen when you mix a numerical variable also, right? On the y-axis, obviously it is the coffee amount. So I hope this is clear, right? For the females, you will get a connection between their age and the amount of coffee. For the males, you will get. Now, supposing that the categorical variable is an influential predictor, then you will see big difference between the two linear regression lines. Okay, and how do you know what is big and small? Just look at the beta value, right? If it's a strong beta, if it's a large beta, that means the two groups are having very different averages. So part 1, setup data prep, we've seen this in detail before. All the libraries and packages like warnings, numpy panda, cborn, stats model .formula.api. This is for smf.ols, ordinary least squares, Scikit-learn linear model. You import linear regression method. From model selection, you're using train test split, and we are using mean square error as a predictive metric. And finally, there's this one new thing that we are going to import. Okay, this method called variance inflation factor from stats model.stats.outliers influence. Okay, so you will use this method to calculate the VIF basically. So I'm going ahead and running that. The data source, as I said, is available in this link. It's the UCI, University Library. Yeah, car prices is the data we are looking at. We remember all this, I hope. Symboling is some kind of risk rating, I think is what we saw. And then you have all these different variables: car body, hatchback, convertible, engine location, front, back. I think we dropped engine location because it was highly imbalanced. And then there are all these things, city mpg. We spoke about some of these mileage and horsepower, things like that last time, right? And if you see here price, this is the target, this is what we want to predict. Okay, so right, and the data description is good but not good enough generally, right? In this case at least it's not good enough. So some domain knowledge, reading, research would be good for those who are not car experts, and for those who are car experts, this should be a breeze, right? Anyway, so just going through quickly, these are all strings. We have to change it to category. So object to category using dot as type category. We saw all this. Also remember that things like symboling may be encoded as integers, but they are actually category. Okay. So symboling ranges from what -2, -0, 1, 2, 3, something like that. There is no 0.5 symboling, 1.5 symboling, right? It's a categorical actually. So you have to convert that also. You have to be careful. You have to be very careful and understand your data. Star name we are dropping. We saw this before. Not really useful, right? And finally, this is kind of the data that we have. 205 entries and 19 features we are using. In that also, as I said, I'm leaving the full analysis of this data set to the learners, to the audience. I'm going to take some random, combination. This is what I've taken: symboling, car body, engine location, car length, so on and so forth, to demonstrate some of these concepts, right? That basically leaves me with 205 entries and 11 features, I think, out of which one is price. Yeah. And finally, as you can see, there are no missing values: 205, 205, 205. So size of data is 205, and you can see how many non-null values are there in each column, and it's all 205. Okay. So as you know, price is the target. So y equal to df price. This is our target variable, and everything else, or at least a subset of everything else, we will consider as the input. So you have to do x equal to df dot drop price. Okay. And last time, if you remember, we did the train test split also. So x train, x test, y train, y test, train test split, input x, output y, 20% or 0.2 we will keep for testing. And of course, random state for reproducibility. 20% means what? Of 205, it is 41. So our testing data, and you can check it here itself, x train. Yeah, so car ID 5, 72, 135, 146. All of these cars have been taken for training, and this 53, 182, 6. All these cars have been taken for testing. Great. So the EDA also is something that we remember, right? So count plots tell you regarding categorical data, right? How many of your data points have zero risk? How many of your data points are hatchback? How many of your car have front engine, rear engine? Then we saw that, look, almost 99% of the data has front engine, and rear engine almost, I think 2 or 3 cars had, we checked last time. So it's kind of pointless. Keeping this feature is pointless, right? So we removed the feature. Pair plot, I'm not running it in this demo. You may run it if you want, right? Gives you understanding of correlation between features. In fact, this is where we start today's discussion in more detail. Okay, we are going to look at correlation matrix and understand things. Okay, because we want to do multiple linear regression. So first thing you want to see is, the price thing, is it correlated with everything else, right? That's what you want to see. These are only numerical features, by the way. We will look at categorical things soon. These are only numerical: car length, car width, car height, car weight, horsepower, city mileage, highway mileage, and price. So 0.68 is good. Okay, car length influences price. Car width 0.76. Car height, interestingly, seems uncorrelated with price. So we should be very suspicious of this feature. Car height, is it useful or not? We don't know. It's almost uncorrelated with price. Okay. And what is the meaning of linear regression? You're basically saying increase in the value of a predictor should lead to either increase or decrease in the value of the target. You want some directional influence. You want to put a number on that, right? So 0.12 is a very bad correlation value. So we should keep in mind this is a questionable feature, right? Curb weight 0.84, 0.81 horsepower. These are good features, obviously. And even these two are good features, right? Minus 0.69, minus 0.7. So first thing you want to do is you want to check the price, that is the target, and its correlation with the numerical features. Okay. Then the second thing you want to do is you want to see these diagonals will always be equal to 1, because we know that one variable is always going to be perfectly correlated with itself. Okay. So x correlated with x Answer is 1. So you should just ignore this. You should ignore the diagonal, just ignore all this and see the other numbers. 0.84 is very high. So you see car length and car width, very high correlation. This should be obvious, right? You don't get cars like pencils or something, right? If the length of the car increases, then the width of the car also should increase, correct? So that the car looks like a car, if you know what I'm saying, right? So this is a high correlation and it's obvious. Again, there's a very high correlation between car weight and both car length and car width. Okay, so what does this mean? Out of car length, car width and car weight, maybe one of these is enough. I don't even need all three. Maybe one of these is enough. Okay, so this is how you look at the correlation matrix and understand it. Okay, so we'll go deeper into this. Now if you want to see for categorical, then you have to get dummies. Okay, so you have to use pandas dot get dummies. I'm storing it in a separate data frame called dfcat, and I have the additional categorical variables are symboling and car body. So let's generate the dummies, and just to make the point clear, I have you look here, I have used drop first equal to false. Okay, which means I am retaining the base level. Now if you see symbol, let's look at symboling, right? Df symboling dot unique, let's say, right? Symboling has values 3, 1, 2, 0, minus 1, minus 2, 6 values. Okay, it's written here 6. Okay, it has 6 categories, and therefore I should get 6 dummy variables. 1, 2, 3, 4, 5, 6. Okay, why did I not drop? I'm not building linear regression model right now. Just for analysis sake, I said drop first equal to false. Okay, and what does drop first mean? It means the base category. Okay, so if I put true here, then I'll not get this minus 2. This column will not be there. Okay, anyways, so that's how that works. Yeah, so let's look at the correlation matrix, right? Now the numerical stuff, that is clear already. Okay, the numerical variables we already understood. You look at these, right? These will give you some idea of correlation with the numerical, right? So if you see symboling minus 2, that's basically symboling value of minus 2. Same way, car body convertible means car body of level or value convertible, right? And then you look at these values here. One thing you will notice is that it's kind of difficult to interpret correlation when you involve categorical variables like this, correct? In fact, if you see symboling 3 minus 0.03 correlation with car length. Now why is it the case? This is problem because numerical variables, right? See, if you take car length, car weight, all the different values of the numerical variable are on the same variable, right? But if you want to understand correlation with categorical variables, unfortunately we have to do one hot encoding. What is this one hot encoding? I just showed you, right? 0 and 0 in business. So 0, 0, 0, 0, 0 and then 1 and then 0, 0, 0, 1, right? So now you have what, 6 variables for one tiny piece of information. Okay, that's the issue with categorical variables. Okay, when you treat them in a numerical way, they tend to cause a lot of interpretation problems, as you can see, right? One thing we can understand is it positively correlated or is it negatively correlated, right? You can interpret that much, but strength of correlation interpretation, it's not really that straightforward. Okay, so how to handle these things, as we continue we'll have a look. Okay, oh, I guess we went through part 1 and part 2. Yeah, okay, we finished part 1 and part 2. Let me pause here. Let me know please in the chat if we can go ahead with the MLR models. Any questions till this point? Mostly everything was the same, but we've essentially started thinking in terms of correlation and things like that. Okay, soon we have to use this understanding to choose our features. So now what we'll do is we'll train MLR models. First we'll go ahead and refit an SLR model. If you remember, we are using stats models here, so I'm using the complete data DF. I'm not using X train and all that. Okay, for analytical purpose I'm using the full data. I don't remember the last time, but I think it was car length or something. We are using correlation matrices. We are looking at numerical variables. Okay, we started with multiple linear regression with all the variables, and one by one you were checking the statistical significance values, the correlation table, and you are assessing it practically also, should I keep this feature, not keep this feature, right? This is what we did. I'm assuming there are no doubts, so I'll go ahead and continue. So if you remember, we spoke about this thing called variance inflation factor. Okay, and by the way, everything before now, I haven't gone into the details of the Python code because it's exactly the same, right? Everything we've seen is the same. The only new thing is, at least in this series of lectures, is correlation, but that's pretty straightforward, right? Pandas dot correlation, right? Data frame dot correlation. This is what you're using, right? Everything else you have seen, right? PD get dummies also you have seen, and I've showed it also here, right? The only thing you need to think about is which columns you want dummy variables for, where you're storing that new variables, new columns, where is your original data, and whether you want to keep the base category or not. Okay, so drop first by default, I don't remember, I think it's true. Yeah, drop first, as you can see here, by default, no, it's false. Yeah, drop first is false, but we can set it to true in case you're generating dummy variables, which we will be doing, by the way, for Scikit-learn, right? For stats models, dot as type category is sufficient. So if you remember, we converted all these object things into category, right? That is enough if you want to do stats models. But if you want to do Scikit-learn, then we need to convert into dummy variables. Okay. Anyway, so moving on with variance inflation factor. Now remember that these are the numerical columns that we are using: car length, car width, height, weight, horsepower, city, mpg, highway mpg. Okay, 1, 2, 3, 4, 5, 6, 7. 7 numerical columns. Now this is a very standard code chunk that you can find anywhere to generate variance inflation factor. You can even create your own code or function, no problem, right? But this method called variance inflation factor, you're seeing it here, right? It only gives you the value for one instance, right? So as you can see, these are the input parameters to that function, variance inflation factor method. This also comes from stats models. Okay, this VIF method comes from stats models. So here, see, here you're actually giving it the data, okay, and then you're giving it the output, right? So not output in the sense the target variable from the predictor. Now if you notice here, where is prices? Prices is not there. That's the whole point. Prices is the target, right? So you don't want to put prices inside this. You might put prices inside this thinking it's numerical. No, it is the target variable. So you do not want to put prices inside this. Okay, only the predictors. And as you can see, it is calculating the VIF for each each of these outputs. So when I say output, I mean each of the temporary target, you can say, right? Temporary as in, first it will create a linear regression model between car length and rest of these variables. Then it will create a linear regression model with car width as the output using the rest of the predictors, and so on, right? And then it will calculate each of these VIF values. Okay, and you can store this in a data frame, which is kind of what I'm doing here. You know, initialize a data frame and give the names of the columns, all of those things, right? So if you just run this is what you will get. Notice the values, right? Now we said that VIF values greater than 5 typically are considered problem of multicollinearity, things like that. Yeah, sure, right. And what does that mean? That means all my VF value should be less than 5. I'm telling you, when you practically work, maybe if you have such a large data that you're getting really nice correlation between the input variable and the target, and you're getting almost no correlation between your predictors, then you might encounter this kind of case, right? But otherwise you should look at VIF in a more relative way. So if you see all of these VIF values, which has the lowest VIF value? That is what I would see. And for me, it's clear, right? Horsepower is the lowest VIF, car weight is the second lowest, 198 I think, and CTMPG 369 is the next one, right? So instead of, basically what I'm saying is, instead of doing this full correlation analysis that we did, right? We did all of this correlation analysis, and what did we end up with, right? We ended up with car weight, horsepower, and CTMPG. Correct? We saw correlation values, we saw significance values, we saw all those things, model by model by model by model, right? And finally we kind of saw that a very conservative but good model is car weight, horsepower, and CTMPG. If you see the VIF values, car weight, horsepower, CTMPG, these are your three lowest VIF. Okay, so instead of doing all of that correlation analysis, you can directly, in most cases at least, you can directly use VIF, as long as you're dealing with numerical features. Okay, categorical features are going to cause problems. We will see that soon. As long as you're dealing with numerical features, you can go ahead with VIF. So I can just look at this and get the top 3 or top 4. That's also fine. Okay, so in fact, I want to go one step further, and I want to say that 369 is such a large VIF value. I don't want it. Suppose I'm only taking top 2. Okay, suppose I'm only predicting using car weight and horsepower. So if you see here, let me just use car weight and horsepower. Now my R square is starting to dip a little bit, is what I would say. So here it was 78 and it's going to 77. So I am starting to lose real information. Okay, so the moment I removed what was that, CTMPG, I think, yeah. The moment I removed CTMPG, I started to lose information in a real sense. Okay, my R square is going down, adjusted R square is going down, so on and so forth. Cool. This is more or less how you analyze multiple linear regression models using stats models. Let's quickly look at sklearn. Okay. If you remember, in Scikit-learn, we have this method called linear regression, which we imported. You initialize the model and then you fit the model to the training data. So this time we will be using the training data. Let's first just take the simple model, that is car length, simple linear regression used to predict the price. Okay, so X train car length and Y train, this will be your training data, right? So let's fit this model, and if you remember, we saw these attributes, right? Each of these sklearn objects, even the stats model object has attributes, right? But if you want to obtain the intercept coefficient, you have to you have to access the value from the object in scikit-learn. In stats models, you can just print and see. So here you get intercept and coef, right? So LR model 1 dot intercept, and if you remember, I said attributes have this underscore at the end just to differentiate that it's an attribute. Okay, so these values will be the same as the stats models one. How to obtain predictions? You essentially use the model LR model 1, right? Dot predict. So the method you're using is dot predict, and you're predicting on what? On the testing set. Basically, because training, I already saw what happened, right? I have R square values, whatever, and I am confident that the linear regression model finds the optimum SSE, right? So training, of course, it's going to optimize. What I really need to check is the testing, right? And if you remember, I also said that um, uh, validation is something you can keep doing in between. Testing you should only do at the end. But I also said, when we are learning all this, let's use the testing data. And In the next session, it will become very clear what is the meaning of validation and testing. Okay. Anyway, so in this session, we only have training and testing. If you remember, there are only 2 data split. So this is how you get the prediction, right? In fact, you can put the prediction along with the actual, price of the car and look at it as a data frame. So these are the model 1 predictions. So if you see here, the price of the actual price of car number 53, whatever that car was $6,795, and this LR model 1 predicted $6,500, right? Car number 182 was around $15,000, and your model predicted 19,000, bit on the higher end, so on and so forth. We also saw in the last session how to calculate the mean square error, the MAP, so on and so forth, and keep adding these values to the data frame so that we can compare the results. So what am I showing this RMSE MAP on? I'm showing it on the testing data. Okay, so look here, X test car length. Okay, these are the predictions, and mean square error between what? Between Y test and Y prediction from this. Okay, so whatever you predicted from the X test, that is here, and then the actual Y test values, that is the actual prices of the cars in the testing set, are here. Same here. Okay, what we are looking at is the testing performance. Testing performance means what? Model did not see the testing data, it was trained on the training data. Okay, so this gives me a fair way of understanding, is my model performing well on new data or not. Okay, so this is the simple linear regression model. Now what do you do in MLR? Okay, so suppose I want to predict price using car length and car width. Okay, you use exact same code, but this time you select 2 features. So if you remember, X train is not one feature. Okay, X train actually has all the features. It has symboling, car body, engine location, car length, car width. X train has all the features. So select 2 features, select car length and car width, and then just do the same thing again. Right, you fit it, you can obtain the coefficients. Now if you do LR model 2.coef, you can clearly see it's a list. Okay, now it has 2 values. So if I just do this, right, LR model coef, it's an array of 2 values. First value is 99, so this is the coefficient for car length, and the second value is 2324, which is the value for what? Car width. Now let's see, do we have a stats model model with car length and car width? Let me see. Car length and car width. We have it. Please see the coefficients here. 97 for car length, 2354 for car width. 97, 2354. So you're getting very similar here, right? 99 and 2324. Why we are getting very slight difference? Because the stats model result was on the training, full data, and this Scikit-learn is only on the training data. Okay, X-train. So anyway, this is how you can get the coefficient. You can interpret the coefficient, build the model, whatever. So again, how do you do prediction? LR model 2 dot predict and use the correct X test data. Okay, so so this model predicts using what? Car length and car width. What do you think is going to happen if I add something else? Car height. Can anyone just guess? So here I have put LR model 2 dot predict X test car length, car width, car height. Can anyone guess what will be the output of this cell right now? If I run this cell, what's going to happen? So if I just write, if I just predict using car length and car width using LR model 2, I am getting these predictions, right? My question is, if I just add car height, I believe that is also a feature. What will happen if I run the cell? No guesses. Right? I don't see any guesses. It should throw an error saying there's a dimensionality issue, I think, or feature unknown. Yeah. So the feature name should match those that were passed during the fit. Okay. So I'm just running this and showing you the error to motivate the fact that everything is stored inside this object LR model 2. So once you do the fitting, so here you see LR model 2 dot fit, X train, Y train. From that moment on, everything you need about the model is in that object. Okay, LR model 2, and let's also inform ourselves what type of object this really is. It's some sklearn object, right? Yeah. So it's an sklearn linear model. It's a class. It's an object of the class linear regression. Okay. It has been trained now. Okay. So now it has knowledge of what are the predictors and all sorts of things, right? Right. So then again, you can just check how well it is predicting. Is it better? Is it worse? All those things you can check. Uh, and the way to really do that is, of course, you have to calculate the errors and things like that, right? So interesting. If you remember, I think the SLR model, which we saw last time, also had 33 point something percent MAP, and this MLR model, the second model, the MAP has reduced. Okay. Now I don't want to go model by model by model, right? I want to quickly go through combinations of variables, right? So it's a simple job. It's a simple job of create a list and get the name. So I'm just creating a list, appending the SLR model one as a separate thing, and then using some text functions, string functions to create this list. Okay. So my model names this thing as all the required names, right? It has the first SLR model whose MAP is 33.78. It has this MLR model, which is car length and car width used to predict the car price, and then all of these different models. Okay. So I have all the names. Now, what about the predictors for each of these models? So corresponding to this list called model names, I will store a list of the predictors. So SLR model 1, the predictor is car length. MLR model 2, the predictors are car length, car width. MLR model 3, I have car length, car width, car height, and so on and so forth. Okay. Now here I'm doing it for a limited number of models. You are of course free to do it for more combinations of the features. Okay. So, and there is this thing called numerical columns here, which is essentially all the numerical variables. It's a list. Okay. So the list is already stored, which is why I'm directly using it. Car length, car width, car height, car weight, horsepower, city MPG, highway MPG, all of it. Okay. So all of these models I want to fit and I want to test on my testing data. So, I'll initialize a data frame. Okay. So the index, what is the index of this performance data frame going to be? It's going to be the name of the models, right? These names. And what are the values? What is the data in this data frame? I need the RMSE on the testing data and I need the MAP, right? So, okay, initialize and then do what? And then just do for loop. That's all, right? Fit linear regression models using each of these various combinations of input predictors, calculate the testing performance in each case, store it and see it. Simple. Okay. So for model input, in model inputs, I think that's the list which contains the different list of predictors. Create a linear regression, fit it on the exact input predictor list, the current one. Okay. So for I mean I is just there to count. I think it's just a counter. Okay. So for the first model, use only car length. So here you'll get X train, car length, comma Y train. For the second model, use both, right? So on and so forth for loops. That's all, right? You get RMSE, you get MAP, and I mean just run this and have a look at it. There. So now our job is to analyze this, right? I mean, off the top of my head, MLR model 7 looks pretty good, right? 21.8%, which is the least MAPE. And if you see in terms of the RMSE also, it is the smallest. So what is this model? Model 7 is the second last in the list, this one. Car weight, horsepower, city MPG. Okay, car weight, horsepower, city MPG. Do we have this model somewhere in stats models? Car weight, horsepower, city MPG. Here, this one. So it's that one model. We went one step further, if you remember, right? So if you remember, in stats model, the previous model was also good model. So see, it had the predictors car width, car weight, horsepower, city MPG. Okay, it had 78.5 R square, and all four of these variables were significant. But we went one step further due to what? Due to domain knowledge. We said, look, car width and car weight, the data shows that it is correlated. Where is it? Where is it? Here. So car weight and car width, if you see, the data shows is correlated. And practically also, we know that the wider a car, it should be heavier. Should be. Typically, I should be able to replace the weight of a car with the volume, right? Interchangeable values. So due to this practical knowledge, we said, okay, let's remove the car width also, and let's only use the weight and the horsepower and city MPG. And we arrived at this model, right? Slightly less R square, but we arrived at this model. That model is currently outperforming all the other models. It just goes to show how important domain knowledge really is, right? So MLR model 7 is doing pretty well with 21%, 22 almost, right? And close contender is MLR model 4 with 22. MLR model 3 is pretty bad with 34%. I don't know which model that is, but it's pretty bad. So this is how you can use Scikit-learn and testing data to see what's going on. And by the way, we should not be using testing data. As I said, it's only for the demonstration up till this point. Okay. So from next session onward, we'll not be using testing data to make comparisons and things like that. So now, till now, what we have seen is how to handle multiple numerical predictors when trying to predict the target. Essentially, that's all we've done. Okay, using linear regression for MLR. When there are multiple numerical predictors, how do we use that to understand which predictors to use, and which are good predictors, which are bad predictors, things like that is what we've seen. I would also reiterate at this point that please remember I am using this data set, which is around 205 observations. It's a real data set, but it is limited, okay, in its scope. It's pretty limited, right? 205 car models, right? And I'm also using a subset of the original 20 features. I think there are 20, 25, I don't remember, around 20 features, I think. I'm using 10 features to even do my analysis. So from those 10 features, I'm seeing, okay, which are the features which look good in a statistical sense and practical sense. Okay, both I'm seeing, and then I'm building the models. So I urge the learners that when you work on this, and as I said, we'll see what's going on. I'll get these notebooks shared with you pretty soon. But yeah, when you do work on these things, please try to use all the features and do the analysis yourself. That is the intention as well, right? So I want to show you for this limited thing. You please take the data and take the the code that I'm using. See if you can do better, right? Are you able to build better analyses on this data? Are you able to build better models on this data? Okay, so that's the intention, as I said. So for me, for 10 models or whatever, I'm getting 20% or something, maybe 21%, which is still not good, by the way. I want this to go to 10 or something, right? So if you see the RMSE, it's 4.5K. So essentially, and I told you, right, how to understand this is just go do this df price dot median. So with median price of $10,000 in your data set, 4.5K difference is not good. At least we should bring it to 2K, right? That could be 10% MAP or something. Okay. Anyway, so now how do you include categorical predictors? So as I said, for stats models, it is pretty easy because you already converted the categorical predictors to category data type. So let's use the same model as before. All the numerical models, predictors. So car length, car width, car height, car weight, horsepower, city mpg, highway mpg, all of this. Plus, let's say we also add car body, and we are doing it in stats models. Okay. So now if you see, okay, the R square value has increased. Okay, good. We should be using categorical predictors also if they are available, right? So R square value has increased 82%. And if you see here, it shows you, it breaks down the categorical variable into levels by default, if you have already converted it to category data type. So I'm seeing here hard top, hatchback, sedan, wagon. What is the base category? I really don't know. So we'll have to check that. BF car body dot unique convertible. Okay. This is alphabetically coming first, right? C convertible. So convertible is the base type. That's why it's missing here. Okay. And I mean, I hope it's immediately clear why categorical variables, make a lot of difficulty in linear regression. See, car body hard top, right? This level of car body is showing a statistical insignificance, 0.465 p value. But if you see hatchback, 0.000, so statistically significant. What does this mean? I mean, it's easy to draw the meaning and put it in English and say, but then when you do the analysis, it's kind of, causes a lot of issues. It's easy to just say that, okay, whether a car has a hatchback or not significantly influences its price. That's what it says. Same way, whether a car is of a sedan or not significantly influences its price. Whether a car has hard top or not does not significantly influence the price. Okay, that's what it's trying to say. But when you're using categoricals for prediction, many a times it doesn't make sense to look at the p-values for categorical, because how can you use a categorical variable for prediction without using all the required levels, right? How can you just remove hard top or hatchback? So it becomes a very weird, awkward conversation when you do things like that. So generally you can look at p-values, sure, but when you retain the features, you either retain all of them, or if you are retaining only hatchback, sedan, wagon, then maybe you should have a reason for that, right? When you present the analysis to somebody, you should say very clearly that, okay, this hard top thing didn't matter, so I did not use it. That's how you should present it. Anyway, so this is how you in stats models, it's very easy, right? Just do plus car body and then you have the summary. Okay. Let's also use the other one, which is the other one, symboling. Okay, so here I have all the numerical features and I've added car body and I'm adding symboling also. So now I have 83, not bad, but initially I had 82. So you should keep a track on the difference between R square and adjusted R square. If it becomes very, very big, then that's a problem. Okay. So it is, as I said, it is a measure to adjust for the overfitting. Okay. So here, if you see, the difference is 0.01, right? So 0.824 minus 0.814, 10%, right? Here again, keep an eye on the difference. 14, 10, yeah, 14%. So here it is 0.0. Sorry, that's not 10%, 1%. Okay, very sorry. The previous case was 1%, 0.01. And in this case, now you have 1.4%. It has started to increase. So you should keep in mind, maybe you are adding too many features. Okay, so this is a starting point to think like that. And of course you can see here, the base value is missing, which is -2. The symboling, by the way, if you remember, it is some sort of risk rating. Okay, so -2 is missing. And yeah, as usual, it has wildly varying statistical significance values. As I said before, guys, nobody is saying that the p-value doesn't make sense. The p-values make full statistical sense. Okay, 100% statistical sense it makes. That is, if you take groups of these data, calculate the mean, do the hypothesis test, and get the p-value and all of that, you do all that, yes, it works. Okay, the problem is in the interpretation, in the modeling, right? In modeling, which are the features should I keep, which I shouldn't keep, that interpretation is where the ambiguity comes. As I said, you are free to keep whichever features you want to keep, right? And you can, for example, here I see 0.052. This is the closest I have to a statistically significant value out of the symboling: 0.15, 0.07, 0.05, 0.23, 0.09, right? So I might just keep symboling 1. If you remember, for categorical features, you will get all these different variables, right? So in gender case, it was gender male, gender female. 2 you have variables. So in this case, I can remove all these variables, symboling -1, 0, 2, 3. Only if I want, I can keep symboling 1, right? Question is whether that's even practically the right way to do it, right? Are you saying symboling -1 doesn't matter? Are you saying symboling rating of 3 doesn't matter? Statistically, because of the data, it's showing something, right? But practically, is it the way to think about? So these are all questions that you will have as data analysts, as when you get into ML analysis, things like that, right? These are the questions that you'll ask, right? So please remember that data analysis is very different from machine learning. We saw this a while ago. Data analysis is what? Understanding what the data has to say. Now the data is telling me a lot of things, right? So it's telling me that car body hard top is insignificant. Okay, so what am I going to do? Either I believe my 200 data points, or I get 200 more data points and then see do the regression analysis, right, and see whether it's becoming significant or not, right? And if it's still not becoming significant, I might ask the question to the car manufacturer or the dealer, like, what's the deal with this hardtop thing? Why do people not care? My question to the dealer will be, people don't care, is it, whether it's hardtop or not? There's absolutely the prices of the two pools are almost the same. So these are the kinds of things that I might discuss with my board or the car manufacturer or whatever, right? If I'm doing this as an analysis task. If I'm doing it as an ML task, that's a different story altogether, right? In the ML task, what I need good predictions. Okay, of course I can use my practical knowledge, but just removing one level of a categorical variable is, I mean, for lack of a better word, very awkward when you do machine learning modeling. Until and unless I have a full approval from an expert that the hard top value can be replaced with NA or something, okay, in my data, till that time I'm going to keep this in my ML model. Okay, so I hope that part is clear. Anyway, so you can of course look at all these p-values, all of that, but ideally what you want is you should do things like VIF and testing it on the testing data, right? Now okay, how do you do it for sklearn? So as I said, we need to get dummies. Okay, so right now this symboling and car body in the original data frame DF, as you can see here, DF, they are the category data type. So you don't need to do get dummy and all that. All that happens in the backend. But for sklearn, it doesn't work that way. You need to create the dummies. Okay. So I am creating the dummies, and this time please notice I am putting drop first equal to true. I do not want additional correlations. Okay, I do not want. I know that if I have 4 levels in car body, I don't know, car body 5. I have 5 levels in car body, so I will retain only 4. The 5th one is going to be perfectly correlated with combination of these 4. Okay, so I don't want that. So drop first is going to be true. And the columns that I'm getting dummies for is car body and symboling. Both for xtrain and xtest I need to do this, and I'm storing it in the variables. Okay. So you can have a look at these. It has, okay, for whatever reason it seems to have engine location. I do not know why that is still here. Anyway, we are not using this, so not to worry. But I have no idea why the engine location. Maybe I dropped it only from DF. Yeah. Engine location I dropped only from DF, I think. Let me check. Yeah, DF drop. So if you notice, X train, X test, XY, all this is happening before I dropped it from DF, the engine location, which is why it is still there. Okay. Interesting side point, but yeah, just an interesting side point. Right. So I have car length, car width, car height, all of these things I have, right? And I also have now my dummy variables. Okay. So please remember, you need to create your dummy variables when you are using Scikit-learn, sklearn. In stats models, you don't necessarily need to do that. Okay. So same is for X test also. You have to create dummies when you are using the categorical. Right. Okay. Then before we go into modeling, let's look at correlations. Right. Same thing. Look at correlations. Now I told you before, interpreting correlations between categorical and numerical variables is a bit, you know, bit iffy, right? You can say it's negative and positive correlation, but think about it. Think about it in a way, right? Think about it. If you take any one, so suppose you take car body convertible, either the value is 0 or the value is 1. That's all. Car body convertible has only two values, 0 or 1. So the column, if you see it is 0 0 0 0 0 1 1 1 0 1 0 1, that's all the values are there. Okay. So now if you try to find correlation with a numerical variable, what exactly are you correlating? Correlation means what? Correlation means when a variable increases, then another variable also increases or decreases. You are analyzing change. Okay, change behavior. What is changing 0 1 0 1? What so much change? Either it is 0 or it is 1. So the maximum information you're going to get from a categorical is, hey, is it positively correlated or negatively correlated? Because it's not going to give you complete information about magnitude. The magnitude of the correlation in this case comes from the numerical variable scale, right? So it's not the best way to interpret it. It gives you some idea, but not the full idea. Okay. So again, you can do analysis like set an arbitrary threshold. And by the way, I set a threshold of 0.6 correlation. Okay, this is arbitrary. You can set any other threshold just to analyze, right? 0.8, 0.9, whatever. Okay, but please be informed that you are never going to have a data completely rid of correlations. That's never going to happen, right? So whatever threshold you set, it needs to be practical. Okay, don't expect all your predictors to have with each other 5% or 10% correlation, right? That's almost never going to happen. You're going to have some correlations practically. All right. So okay, the categorical correlations, what are you going to interpret here? Everything is NaN, right? What are you going to interpret? So this is obviously a problem. What about VIF? What about variance inflation factor, right? So again, for VIF, what you need to do, you need to convert into dummy, right? 0 1 1 0, the one hot encoding, right? So I am doing this for the full data frame, which is why I am doing pd.getDummies again. I know I've already done it for extra and XTest, but here I'm doing a bit of analysis. So I'm using the full data frame. Okay, so get the dummies for car body and symboling and do the whole variance inflation factor thing, right? Please look at the screen, right? All the categorical variables have very less VIF, which means they are the best predictor. Do you think so? Do you think so, right? So if you just see all the numerical ones, much higher variance inflation factor, all the categorical ones very low, right? Car body hardtop 2, car body hatchback 14, CT-MPG, highway MPG 300 400, right? Is this meaningful, right? Is this really meaningful? So would you basically look at this and say, I will not use car length, car width, car height, car weight, horsepower, CT-MPG, none of this. I will use not a single one of my numerical variables. I will only use categorical to predict. Does that make sense? No, right? So this is the limitation of even this metric called VIF. It was doing well when we were doing with numerical variables, but when we came to categorical and numerical combinations, even it started uh, posing issues because of the categorical variables, right? So is there any point, right? Just to drive it home, just suppose I will use all the features with less than 50 VIF. Okay, so let's just see who are these. Horsepower is the only numerical feature with less than 50 VIF. Everything else uh, are essentially just the categorical, right? Suppose I build a linear regression model using this, using what? Using only horsepower, car body, and symboling. Okay, so I'm using Scikit-learn, not stats models. You can of course go back to stats models and see what does this look like. In fact, let's look at that before we look at this, right? Let's build a stats model first. Okay, then we can look at Scikit-learn. So here, what are the ones I need? I need horsepower, car body, symboling. So right, and this is stats model, so I don't need dummy and all that. Let's just call it temp model. I don't want to change the names of the existing models, right? Yeah, great. So 72% R square, not bad, actually not bad. I have to say, actually not bad, right? This might be because of the limited data. Okay, we have 200 data points, so within the data point, these two categorical features are being able to separate the groups into different average prices, right? That's what's going on. So not bad at all, but not good enough. If you remember before, we had models with around 80% R square, which were performing well on the testing. Now we should also check the testing. So this is the stats model telling me 72% R square, and let's also use Scikit-learn, okay, and find the performance on the testing data. So here I am looking at the predictive performance on the testing data. Now, which model is this? Remember, it is the model blindly I have taken whichever feature is less than 50 VIF, variance inflation factor, which should be obvious that it is, weird, right? If I do that, right, I'm going to ignore highway MPG, city MPG, car weight. I'll ignore every numerical feature and I'm only going to go with categorical, right? So this is just to show you that it's not the best model. Okay, so let's calculate the RMSE and everything for this. So you just have to do dot predict, use the correct test data, and this condition here gives you the columns, right? The features whose VIF is less than 50, right? 24% MAP, $5,000 RMSE. This is higher actually than some of the values that we have seen before. So even if you blindly take VIF less than 50, you're still not getting a better model. Typically, if you see, when you're only dealing with numerical features, you can say, look for less VIF, right? Now suppose I do VIF less than 10, then what's going to happen? A lot of these things are going to be ignored and you're going to get a very weird model which only depends on whether it's a hard top or not, whether it's a wagon or not, and you can use it for some interpretability, but in predictability it's going to get worse. Okay, and it has got worse. So here the MAP is 24. What is MAP? It is percentage prediction error on the testing data, right? So this model, even though you're using the variance inflation factor rule, the predictive performance is 24%, which is bad. It should be less, right? And we had a model, if I remember, which went almost close to 21-ish, right? So as you can see here, MLR model 2 is going to 21%. It's better. $4,500 error only, right? This one is 5,000. So I hope it's clear that you can use VIF for numerical features at least to understand, what's a good feature, what's a bad feature. For categoricals, you essentially have to try it out, right? You have to include them and try them out. Okay, so so that's what we're gonna do. So I mean, again, you can you can look at correlation tables, things like that. But we remember, right? We remember that car weight was a good predictor, horsepower is good predictor, and CTMPG was good predictor. We remember these three, right? This is our 79% model, R square model, with what 21 point something percent error. This is the exact model. Okay, model number 7. Model number this one, model number 7, whose predictive performance was the best till now. And what is model number 7 actually? If you see the so here, if you see, it is based on car weight, horsepower, CTMPG. Okay, so you're predicting car price using these three. Okay, great. To this best model of using numerical predictors, now you add categoricals and see what happens. Okay, so car weight, horsepower, CTMPG, and then you have to add car body, right, and symboling. So how do you add these two categorical features to Scikit-learn? You cannot just add one feature. As I said, Scikit-learn, you have to give dummies for categories. So to add car body, hard top, hatchback, sedan, wagon, okay, symboling -1, 0, 1, 2, 3, right? And as you can see, I have missed the base category. So symboling -2 doesn't exist. I didn't even ask for it. So drop first equal to true in PD dummies. Okay. So let's run this model, okay, and see how it is performing. Okay, 21.89, not bad. So yeah, the VIF, if you go by variance inflation factor analysis, you will end up with the wrong model. Okay, as I said, in linear regression, there are a lot of things that we need to see. Okay, this is something I think I should make clear right now. The simpler the model, the more complicated the analysis. Okay, so linear regression is simple. Y equal to mx plus c, right? Slope intercept, straight line, simple model. There will be a lot of complicated analysis. Later, when you do more, let's say, complex machine learning models, the effort spent on such analysis will be less. That is the trade-off. Okay, if you want simple, nice, interpretable model, then complicated analysis and decision making. If you go for a complex model, understand it, wrangle with it, then you will be sort of easier with the decision making and analysis. Okay, anyway, so I'm already getting a better MAP on the testing data. Okay, what was this model? It is our existing best model, that is numerical predictors, car weight, horsepower, CTMPG, plus symboling and car body, both. Okay, symboling and car body. So now you may want to ask, okay, what if I remove car body? So what if we just keep symboling, right? That also you can do. So here I'm fitting another model, car weight, horsepower, and CTMPG, along with symboling. I'm not using car body this time. Okay, the MAP increased 22.39. Okay, not bad, but not good. I want to keep reducing this MAP. And finally, you can try just car weight and horsepower, maybe reduce even one more, right? So as I said, CTMPG, we discussed that horsepower and MPG, they are correlated.
In today's rapidly evolving business landscape, machine learning and AI are no longer buzzwords. They are essential tools for staying competitive. Are you ready to lead the AI revolution in your industry? Upgrade, in collaboration with IIIT Bangalore, brings you the Executive Diploma in Machine Learning and AI. This program is designed for ambitious professionals like you, seeking to leverage AI for strategic decision-making and innovation. Gain hands-on experience with cutting-edge technologies, learn from renowned faculty, and network with industry peers. Elevate your career, drive business transformation, and position yourself as an expert in AI. Enroll today and future-proof your career.
So the agenda for today, so first we'll talk about something called bias and variance in machine learning models. These terms you will come across a lot when you talk about ML models. So let's, we'll have some understanding of these terms. and how they relate to these things called overfitting, underfitting, and what's the problem, all that. Then we'll talk about regularization in linear regression and what is regularization. We'll talk about that. Okay, and then we'll see two methods for regularization in linear regression, which is ridge regression and lasso regression. We'll quickly compare the two, and then we'll get into something called hyperparameter tuning. We will understand the difference between parameter and hyperparameter. Then a quick note on model selection, which will be more useful as we go ahead. Yes, logistic regression is a different topic, Jacob. It is related to linear regression in a mathematical sense. They are quite similar, but in terms of objective, they are different. Right? So, in fact, logistic regression name is a bit funny because it's used for classification, but we call it logistic regression. Okay. So, linear regression is used for regression, numerical values, to predict numerical values. Logistic regression is used for classification. But the math is quite similar. Okay, the math is quite similar, and that you will be doing next week, I think, logistic regression. So we'll quickly just talk about model selection. This will become more useful as you add more machine learning models to your arms, right? You'll have more tools in the sense more ML models to work with. That time model selection plays an important role. So for that you have to understand various models, then you can make judgment calls. Should I be using linear regression? Should I be using decision tree? All those kinds of things. And finally, we'll see a Python demo of linear regression, hyperparameter tuning. Let's get into this whole bias variance business, right? So if we remember, what we studied about ML, the aim of machine learning is essentially to impart the ability to learn to a digital computational system. Okay, we call it machine, computer, whatever, right? We want to impart ability to learn. That is the ultimate goal of machine learning. And we saw one of the methods or one of the ways in which we do that is called supervised learning. Right? How do we impart ability to learn? We need some protocol, right? One of those ways of thinking is supervised learning, in which if we all remember, right? So I hope everyone remembers this diagram. You have one feature which is output or target, and then you have all these input features, right? And given this data set, we would generally consider splitting into training and then some kind of testing data. And we'll understand what validation data is in further detail today. Okay. So generally this is what we do. We train it on the training data by giving it the relationship between the input and output, right? So here if you see, the model is able to see the input and the corresponding output. So this is why it is called supervised. Okay, because the learning is supervised by the truth, the true values, right? On the training data, and then you check the performance on the validation testing data. Okay, and then finally you use it on the new data to predict whatever you want to predict. So now comes the question. Okay, this is the way we are training it. How do you evaluate? I mean, we have seen ways of evaluating before. Let's formalize that. So basically, this is the data that you have, right? This is your historical data, right? It could be for everyone, it's going to be different data based on the domain that you're working in, right? It could be business data, it could be hospital data, whatever. This is the historical data that you have. Now, what we do is we split it into three things. One is training data, one is validation data, one is testing data. Now, generally for training testing, if you remember, we said go for 70-30, go for 60-40, 80-20, something like that. In this case, you could do something like 60-20-20. Okay, that's also fine. 60-20-20. Now, 60% of the data that you have, you will use that to fit your model, fit or train. The word you can use is fit or train. In Python, most commands will be .fit, all right, .fit, .fit. So you use this training data to fit the model. The purpose of the validation data is essentially for the model to see how it is performing and give a chance to improve itself. So we will understand what this means in further detail today. This improving business, right? We'll see what that means. Because last time I told you that once you have a linear regression model for a given set of input predictors, you don't change the line. It's a fixed line, right? The line is fixed, end of story. You have the coefficient values, you're not changing anything. So how's the model improving, right? So we'll see today methods that we use to regulate or improve the model. As you see, I'm using the word regulate, right? Regularization. Finally, testing data. The model did not see the data. You made sure that the model did not see the data, so that finally you can check the performance in a fair way before deploying. After deploying, the model has to now go and perform on the new and unseen data, right? So this is essentially the full evaluation, training to evaluation life cycle. Okay. There is this thing called ML model inference. It's essentially just the process of understanding how the model is performing after training. So there is usually two phases in machine learning training, right? One is training, one is inference. So you train the model, then you infer the model. How is it performing? Train, infer. Okay. So when you do the model inference, that's when you're doing, RMSE and all that, right? You're evaluating on the validation and testing data. And there are a lot of points that we need to keep in mind, right? When we do this, we might see bad result, we might see good result, and then we need to know why we are seeing bad result, good result. So some questions that we can think of is, did you expose the ML model to sufficient amount of training data, right? Do you have enough data to learn from? Then what type of training data have you used? Is it relevant training data? Are you using unnecessary kind of data? Did you choose the right ML model for the problem statement, right? Should it be a linear regression? Should it be a decision tree? Should it be a something else? And then the question also is that, did you use the right algorithm to train? Okay, so some models have different objective functions and algorithms you can train it with, right? So these are all questions we want to keep in mind when we talk about the goodness of a model, okay, in the end. Now, the main problems that generally machine learning models face can be classified in two parts. One is called underfitting, one is called overfitting. Now, underfitting happens when the model has not learned well enough from the training data. There can be many causes for this. One, maybe you don't have enough training data. Two, maybe you have irrelevant training data. Three, maybe your model is not the right model. So you see why I put all of these questions in the previous slide, right? So when you see that your model is not performing well, right, you shouldn't think, oh no, something is, we can't solve this, right? If you think in terms of these four questions, 4 or 5, of course there are many other similar questions which I can put in this list, but broadly this is what we are talking about, right? The data and the model, right? So underfitting happens when the model does not learn well enough. As I said, very less training data, nature of the model, there are many reasons why it could happen. Generally what happens, underfitting leads to poor performance on training and unseen data. Okay, so you'll have bad predictions on the training data and you'll have bad predictions on the new data also. What is overfitting? Overfitting is on the other end, right? So overfitting happens when the model learns too well. In fact, we can even replace the word learn with memorize. Okay. So there's a fine line between memorizing something and learning something, right? So we don't want the models to memorize, because if that happens, then it will work well for you in your instance. The moment you deploy it, it's not going to work well. So, what we need from good machine learning models is good generalization. Okay, we need the model to generalize well on any kind of new data, that it is able to learn some pattern from the historical data, use that knowledge to predict or classify from the new data. That you will say is a intelligent model, right? So overfitting, it will lead to bad generalization. It will perform well on the training data, but it will not perform well on the new data. Okay. So what we have understood, underfitting and overfitting, right? Underfitting, model did not learn well. It is anyway a bad model, so it's not going to be of any use. Overfitting, the model has learned too well from the training data that it doesn't know how to predict anything except the training data. So both of these you need to avoid. Okay. How to avoid? So as I said, increasing the amount of training data can help you with underfitting issues. Diversity of classes or values again can help you with underfitting issues and can help you with overfitting issues also. Class balance is very important when you're working with classification problems. Keep in mind all this. Don't need to go detailed right now because next few weeks you will be learning so many different models. All of these things will be mentioned and it will be like bread and butter, right? When you're discussing logistic regression, decision tree, you have to keep in mind all these things and it will keep coming up. So no need to memorize what's on the screen. Okay, just setting some context. You can improve class balance. Then one important thing is choosing the right type of model, choosing the kind of algorithm, tweaking hyperparameters, and so on. There are many things that we can do and should do to improve model performance. Okay. Now this brings me to a very interesting concept called bias and variance. And let me just put it simply that models with higher bias, essentially you can think of it as more restrictive models. That is, they are making more assumptions. So in a way you can say, you can compare it to something like a close-minded, right? Generally a higher bias leads to poorer learning from the training data, and generally typically it might lead to underfitting. Okay. That's bias. Bias just means that the model is making too many assumptions. You can say it is rigid. Okay. Bias means your ML model is rigid in its assumptions. It is not allowing for free learning from the data. Okay. That's one way to understand it. Model with higher variance is what, and the reason I'm talking about bias variance right now in this session is you might hear it again and again as you go through the various ML models and everything, and when you start exploring and when you read articles and look at anywhere else on the internet, right? These things will be mentioned, bias and variance. So it's important to have some idea what is bias and variance. So bias means what? The ML model is too restrictive, rigid, makes too many assumptions, does not allow for free learning from the data. Variance is the opposite, right? Higher variance models make less assumptions, and what they do is they allow for more variation in the learning, right? It's more flexible in a sense. So you can use the word flexibility. And what they generally do is they try to match the variation in the training data much better, right, than a moderate variance model, right? High variance model will try to match almost point to point. So that generally leads to more complexity and can lead to more overfitting. So generally higher variance leads to better learning from the training data, yes, but it leads to overfitting. Now these things will become more and more obvious when you understand different ML models. For now, I'll give you two examples. Okay. A high bias and low variance model example is linear regression. Why do I say that? So if you remember in our second session, we discussed a few slides in which we took the scatter plot and then we fit a line and then we fit a quadratic curve and then we fit a cubic curve. I hope everyone remembers this, right? We fit a line and then we fit a quadratic curve and then cubic curve. So you saw very clearly that the line has the maximum error. Okay, when you fit a line to random scatter plot data points, it will have more error. When you try to fit using a curve, you're going to have less error because you have more flexibility. So if you're using a higher polynomial to fit, you are allowing for more variance. Okay, but if you're using a linear model, you are not allowing for any such variance, right? It's a rigid model, only straight line, no up down curve, nothing like that, right? It's a single straight line. And that is why linear regression can be considered as a high bias model. It's assuming that your data is linearly related. Okay, it's and which may not be a correct assumption. If you see the world around us, I mean, a lot of things need not be linearly related, right? Even though there may be a correlation, does not mean it's a linear relation. Okay, so but the linear regression model is a simple model. which is why we are starting ML with simple model, right? Just y equal to mx plus c, full stop. Not y equal to mx minus m squared, mx square, whatever, right? That's a complex model. So linear regression, high bias. And it's a low variance model. It doesn't allow for variation in the learning. Okay. So that would be an example of high bias, low variance model. What about a low bias and high variance model? Now, many of you may not have encountered this model. You will be encountering it, I think, in some weeks from now, right? So first linear regression, then logistic, and I don't remember what's there in the program after that, but you will be studying decision tree sometime in the future in this program. So decision trees are almost opposite of linear regression. They make zero assumptions about the data actually. Okay, if in fact there's no formula also. The decision tree model does not have any understandable formula, let me say. Maybe there is a very complicated logic formula, okay, that we can create for decision tree, but there is no generic simple formula for decision tree. Okay, so it makes no assumptions about the data because there's no general formula also. It's a low bias model making less assumptions. Okay, and generally the decision tree actually very prone to overfitting. It is very prone to overfitting because of this, and it is a high variance model. Okay, high variance in the sense any changes in the training data, the decision tree can match that change also. So you can even get 99% accuracy on the training data and almost 5-10% accuracy on the testing data. It's that bad. Okay, decision trees. Okay, so that's what a low bias high variance model will look like. It is low bias because it does not make any assumptions about the data. It has no restrictions. It is able to train from the data very easily. And it's a high variance model for that reason, right? And an example is decision tree. Okay, I just want everyone to keep these concepts in mind. It's not the case that we should understand these concepts, in this session in these 10 minutes. Okay, absolutely not. This you have to think about on a day-to-day basis as you go through this program, as you study the various machine learning models. You must keep these in the back of your mind. Keep asking the questions. Am I looking at a high bias model? Am I looking at a high variance model, low variance model? Am I looking at a model which can overfit or potentially has the tendency to overfit? Am I looking at a model which is a tendency to underfit? Keep these questions open when you go through all the different ML models. Okay. All right. So generally, to improve model performance, on a model building level, what we really want to do, we want to decrease the bias, right? I told you, high bias means very restrictive and you're not able to train properly. Okay. And you want to increase the variance, right? Variance means again training properly from the training data. But generally speaking, there is no model which has perfectly zero bias and perfectly 100% variance. There's no such. It's a trade-off. Okay, it's always a balance between bias and variance. Okay, so generally that translates to, as I said, this bias variance stuff. You can think of it as the back end process of the machine learning model. You can think of it as nature or characteristic of the ML model, right? So if this is your ML model, right, then it will have characteristics called bias and variance. This can be translated to the performance. So when you do the testing and deployment, right, that time what is really important is performance. So in performance, this balance between bias and variance translates to what? It translates to the balance between underfitting and overfitting. Okay, so it's a very fine balance, and we will see this in full detail with the Python demo today. Okay, where underfitting is happening, why it's happening, how overfitting is happening, all that we will see. Okay, so I just want everyone to know and keep in mind that in the back end there is this notion of bias and variance, which has everything to do with the structure and the formula used in the ML models. Okay, and just to sum it up, linear regression, very 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 simple equation, obviously very restrictive and very high bias. Regularization in linear regression. Okay, so let's start with the general formula, and again, let's not worry about the algebra too much. It may look complicated, but it is simple if you box it out properly. Okay, so here is your predicted output. This is the formula that you will use to calculate your predicted output: beta naught plus beta 1 x1, so on, x1 x2. These are your predictors. This is an MLR model, obviously, and you can just use a sigma operator and make this look a bit smaller, the expression. So here you have I equal to 1 to n, which is nothing but your input features. So x1, x2, x3, so on, and the coefficients. So if you remember the linear regression sessions, we discussed that the learning actually happens in the coefficients, right? Of course, we discussed two things. One is the coefficient, one is the structure of the model itself. But structure, we cannot do anything right now because we are using linear regression. Okay, so we are stuck with this structure. Now, given this structure, then where is the learning happening, right? The learning is happening in the coefficients. So then it is a logical claim that bad and good learning also happens in the coefficients. Okay, whatever bad learning happened, blame the coefficients. Whatever good learning happened, credit the coefficients, right? So that's the main thing we have to focus on. What are the optimal coefficients? Now, just remember, for the theory part, as I said, we'll be using this small data set. I hope everyone remembers this. Let's just go through it once. This is my target that I want to predict. It's the amount of money spent on coffee. What you're looking at is a historical data. So this is last year's data. I have 10 customers here: Aarti, Darshan, Isha, and so on. And I have their some characteristics like gender, job, income, age, so on and so forth. Okay, and the objective is essentially to train linear regression model to predict how much a new person will spend on coffee. Okay, so let's consider the full model, so to speak, right? Let's full model in the sense we will use all the predictors. Okay, so explain amount as a linear combination of gender, job, income, and age. So you're using all the four to predict amount, right? So how many linear regression equations are there for this model? One only. There is only one linear regression equation. Okay. Now, before we get into regularization, there is one thing we need to understand, that is feature scaling. Now, many of you may have come across this, may not have. Still, let's sort of talk about it and understand why this is required. So, see, initially, if you look at your data, all the predictors are on the own scale. Like if you see gender, it's on a scale of binary, female, male, whatever. If you see income here, it's on a different scale. It's in many thousands, many tens of thousands of dollars. If you see age, it is in 20, 30, 40, 50, 60, things like that. Okay, so each predictor is in its own scale. Now, if we want to compare two predictors really fairly, if you want to compare fairly, then generally what you need to do is you need to make them of the same scale. Otherwise, how will you compare? Because if you see the equation of linear regression, each of these betas, if you see each of these betas, the beta is multiplied by the x. So in this case, suppose x is age and suppose this x is income. Now we just saw that age is on a scale of 10, 20, 30, 40, 50, right? And income is on a scale of tens of thousands. Then the coefficient will be on different scales accordingly. Why? Because both coefficients are predicting the same target. The target is the same. It has a common target, right? So what will happen? Wherever, so if you consider the income variable, which has a larger scale, the coefficient will be on a smaller scale. You might have noticed this if you look at the PDF from the previous sessions and things like that. Income coefficient was 0.026 something in the red model, right? But age coefficient will not be so small. Age will be on a bigger scale. The age coefficient will be on a bigger scale because age is on a smaller scale, right? And why these two are related? Because they are predicting the same target. Target is the same. So when you're doing the prediction, there is this difference in the scale of the coefficients because of the difference in the scale of the inputs. So if you want to fairly compare the different coefficients, then you need to have the same scale. Otherwise, there's no point in saying that age coefficient is 50 or 60 and income coefficient is 0.05. So income is not important. No, that is a wrong interpretation, obviously, right? So if you want to compare coefficients, that is essentially comparing the input features. For that, you have to make all the features same scale. After that, you can compare the coefficients and then you can decide what do I want to do with the weak one, strong one. We cannot say any feature is weak or strong without bringing all of them to the same scale. Okay. And how do you compare weak and strong? After bringing same scale, we can look at the beta, the coefficients. Before same scale, you cannot compare the beta. Okay. The only problem is that you will lose the interpretability, okay, of the coefficient. Of course, once you convert your data into same scale, 0 1 minus 1 1 whatever, right? Generally these are the things we do. Interpretability will be lost because they're on different scale now, right? So interpretability means what? If you remember, we said 1 unit change in this variable will cause beta unit change in the target. That kind of interpretability will be lost. But so what? When you are trying to build a model for prediction purposes, it's perfectly fine if interpretability of coefficient is lost. That is primarily important when you're doing core data analysis. When you're doing core machine learning, you are not really interested too much about interpreting coefficients, right? You're more interested in making a model which works for you. Okay. So this is essentially what feature scaling is. Now, there are some methods. Very common methods are these two: normalization, that is rescaling from 0 to 1, and standardization, rescaling minus 1 1. Standardization, normalization is also called min-max. If you have seen it anywhere before, so in Python we have min-max scaler, right? And standardization is also is the same as z-score. If you remember your z-score, it was what, x minus mu sigma something, right? So you are standardizing your feature. So for example, if you take the income feature, 64,000, 56,000, whatever, right? It essentially converts all of that to z-score and provides you, right? Which is why the scale is from -1 to 1. Okay. So these are some scaling methods that we can use. Now, before we scale it and then look at it, one thing we should remember is that transformations, before we convert our dummy data here, let's understand one thing. There is something called data leakage or information leakage, it's called sometimes, in machine learning. Very important concept. Basically, transformations of any kind should be designed using the training data only. In other words, if you split into training and testing, but then borrow information from the testing data to do the transformation, then that is essentially unfair. When I say borrow information, what do I mean? Suppose you're doing min-max scaling. Okay, look at this data set and look at the income. What is the maximum income I see? 81,293, I think. So suppose, for example, these three are used for testing. Forget Zishan for a moment. Okay. And suppose the top part, I've already marked it here, is used for training. Now, if I use min-max scaler and use 81,293 as maximum value to transform the values in the training data, that means information has leaked from the testing data to the training data. Of course, because the model is only supposed to see the training data. Now, if the model is seeing the training data, then what is the maximum it should use? If you're trying to do min-max scaler, what is the maximum value? It is Gayatri's salary, which is 72807. That is the maximum inside the training data. Okay. So min-max scaler, just for everyone's understanding, it takes maximum and minimum and gives the value 1 and 0 basically. And whatever is in between, it gives the appropriate value. So for example, here in the training data, 72807 will be given the value 1, and whatever the minimum is, you will get the value 0. And everything in between, you will get values between 0 and 1. Okay. But if the model knows that the maximum is 81,000, that is Trevor's salary or income, then that means information has gone from testing to training, and that is called data leakage. Okay, this is called data leakage. So basically you must design your transformation using only the training data, then you can transform the testing data. Don't design using testing data. Okay, so design means you just need the max value, min value in the case of normalization, and in the case of standardization you need to know where to center your mean and things like that, mean and standard deviation, right? Those are the things you need for this one, z-score, which is standardization. So that information you should only take from the training data. Okay, so otherwise information will leak, and this compromises the legitimacy of the model, right? It will not be accepted as a fair model. Okay. Great. So having understood all of these things, what we will do before we get into regularization is we need to prepare the data. So for that, categorical features, of course, you have to convert to dummy variables. And let us say, for example, we will normalize the data to 0, 1. Okay, you can standardize also, no problem. I have considered normalization here, which is min max scalar. For those who are interested, you can quickly, if you want, Google min max scalar. Okay, we'll anyway be using it today, I think. So this is the Python method. Okay, min max scalar for normalization. So what will your transform data look like? So you can see on your screen, now everything has been changed from 0 to 1. Okay, so here I am using all 10 data as training data. Okay, so from RT to Zishan, I have 10 data points, all are my training data. If you see, Zishan has an income of 0 and Trevor has an income of 1. Let's quickly confirm that with our data. So if you see the income column, please check which is the minimum income in the all 10. Zishan has the minimum income, right? 44987, and maximum income is Trevor 81293. So your scalar gave value of 0 to Zishan and 1 to Trevor. Every other value will be between 0 and 1. Same for age. So now you can check here age also, which is the minimum age. I am seeing Jasmine at 24. And maximum age I am seeing RT at 56, I think, right? So Jasmine and RT, let's check. Jasmine 0, RT 1. Okay, and everything else will be in between. Cool. So now all of these input features are in the range what? 0, 1. All the input features are in the range 0, 1. Now if I fit a linear regression model, now I can compare the coefficients and make claims which is more important feature, which is less important feature. Okay, that's the whole point of doing this. So if you look at the unregularized model, just a fancy way of saying basic linear regression model, MLR. Okay, this is your basic MLR model. So you're explaining amount as a combination of all the input features. Also notice one more thing, the what do you call, the categorical variables have to be converted to dummy variables. Okay, so you need the zeros and ones because now it's all numerical, correct? So you need the zeros and ones. All right. Great. So so that's that. And as you can see, where are the coefficients? Yeah, here are the coefficients. Okay, so you can see the coefficients of this unregularized model here. It has an intercept 1371. Okay, and it also has the coefficient for the gender variable, coefficient for job variable, and things like that. Now looking at these coefficients, you can make some claims that okay, the lowest coefficient seems to be income in terms of magnitude, lowest is income, so maybe it is the least important. Now of course I am using only 10 training data points, so so don't make any claims using 10 data points. I'm just showing this to demonstrate how to use these things. But more importantly, if you see down, here is the training RMSE and the testing RMSE. So if you see, the training RMSE is lower and the testing RMSE is higher. Similarly, the training MAPE is lower and the testing MAPE is higher. What does this mean? This means that the performance of the model on the training data is not bad, is good, but the performance on the testing is bad. So this is exactly what we call overfitting. Okay, this is exactly what we call overfitting. Testing performance is worse than the training performance. So if you compare 101 and 197, RMSE should be low, right? RMSE is nothing but the difference in the predictions. Difference should be less. It's less in the training, more in the testing, which means it learned well, but too well. Therefore, it is failing in the testing, right? So we say in this case, we say that model is not able to generalize well. Okay, it has learned from the training data quite well, but it's not generalizing on the unknown data. So in other words, you can say it has not learned, but more rather it has memorized or something like that. This is a bad thing. Okay, that brings us to the concept of regularization. Okay, so look at the screen and we'll understand this step by step. This is obviously your original linear regression model, correct? Y hat is the predicted value, and then this is your regression equation. Now, the basic regression equation loss function was only this much. It may look complicated, but this is nothing but SSE. If you check very carefully, this is nothing but the SSE, because whatever is this beta naught plus beta 1, whatever, this is nothing but y cap, right? This is nothing but the y cap value. So what you're looking at is yi, which is the true value, minus this whole thing inside the bracket, which is y cap, which is the predicted value. How are you predicting? It's nothing but beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth. So this part is your traditional SSE. Okay, so this is exactly what we used to find the linear regression model. But notice that now in regularization, what we will do is we will add this additional term to the loss. So already your SSE is there as your loss function, but on top of that we are adding a new term called the regularization term. Okay, that is here. If you notice very carefully, what it is nothing but absolute value of coefficient. It is raised to some power p, that is just a parameter which we can set, p equal to 1 2 3 4 whatever we can set, and alpha is kind of a control factor. Okay, alpha is basically some kind of control factor. So we'll go into this in detail bit by bit. For now, let us understand what we have seen in this slide. Okay, essentially we have added a regularization term to the loss function. The purpose, I will make it more obvious soon. We'll discuss this in more detail, why we did this. Alpha is a tuning parameter. Okay, alpha in this term, you can see it's a more of a control parameter. How powerful do you want your effect to be? That kind of thing. It's a power factor, you can say. P is the power of the coefficient terms in this summation. Okay, so it controls the type of regularization. And essentially how this works is that if you increase alpha, then beta must reduce to reduce the loss. Let's again look at the formula and understand that. So imagine you only had the SSE. Okay, imagine that you did not add the regularization term. So what's going to happen? The model is going to find out the beta values which reduces or minimizes the SSE. Now the only way for you to reduce or minimize the SSE is to have non-zero coefficients. Non-zero coefficients. Because if all your coefficients were zero, that means your prediction is zero. That means your loss is going to be very high. Just imagine yi minus 0 in each case. Now, how do you think you are going to reduce this amount? Of course, we cannot have 0 as my prediction. We have to have some prediction, correct? So for some prediction, we have to have some beta value. For better prediction, we need better beta value. This is exactly how linear regression works. It finds the optimal beta value to match the true values. In other words, the burden or the load is placed on the beta values. What if this is leading to overfitting in my model, right? That is the point. What if I am explaining too much? I am putting too much burden on my beta, right? Then you will get a very good training performance. But what if that is leading to overfitting? So the reason to add this additional regularization loss is so that the model is motivated not to increase beta too much. Because just imagine what is going to happen to this additional term if you keep increasing beta value, and notice there is an absolute value, so you're not considering minus, plus and all that, you are only taking magnitude. Okay, so suppose you have very high beta values, then of course you will be producing better predictions, no doubt about that. But if you have high beta values, then what is going to happen to this loss term? It is also going to increase. The regularization term loss is going to increase. That is going to contribute to the overall loss, correct? And that is how we optimize the model not to place too much burden on the betas. So you can think of it this way: if alpha is zero, then the linear regression model tries to explain all the target variance using the betas, right? So a target variable is coffee, and whatever variation is there, all that variation will be explained using these betas only. If alpha was zero, if alpha is not zero, then the model has to increase the beta to do the prediction. At the same time, the model cannot increase beta too much because you are counterbalancing the loss using this additional term. Okay, it's a positive quantity. Alpha is positive, and whatever beta is there, it's inside absolute value. So that loss is positive. Correct? So more beta will give you less SSE, but more beta will give you more regularization loss. Okay, I hope this made sense, right? So then you use alpha to control this effect. Basically, you use alpha to control the effect. If you put alpha as 0, it is your basic regression model, nothing else. If you start increasing alpha, then betas will be forced to limit. They cannot unnecessarily keep increasing in magnitude. Okay, I hope that is clear. Beta can be negative. Of course, beta can be negative. When I say increase, I mean magnitude. Okay, so you may have very large negative beta values and you may have very large positive beta values in the same model. All of these betas together are allowing you to do good predictions on the training data, which reduces the SSE. Good, very good. But that may lead to overfitting. Now what do? We added this additional regularization term, which is essentially sum of all the coefficients with absolute value. So now if you have large negative beta, large positive beta, then this loss will increase. So now the model is forced to find a very optimal linear regression, very optimal set of coefficients, which minimizes this new loss. Okay, so it is a way to control this unregulated expansion of the beta values. This is where the word regularization comes from. Okay, we need to regulate how much we are allowing beta to increase in magnitude. Okay, great. Now okay, I think I explained in this slide whatever I was explaining till now. So that's what I've kind of written here. So when the model is trained using this new loss function, it has to balance both components. This component on the right side increases with increase in beta. This component on left side decreases with increase in beta. This is your SSE, this is your regularization loss. SSE and regularization loss. Okay, so now you have to balance. How much power should we give regularization? Alpha. That is where you consider alpha. Okay, great. So what is the meaning of all this? In a sense, if you take the unregularized model and the regularized model, the unregularized model has stronger coefficients, no doubt, but that may lead to overfitting. The regularized model may be left with weaker coefficients, not the best training data predictors, but it might perform better on unseen data, and generally it does. Okay, generally it does. The only way for linear regression models to overfit is by increasing number of predictors. Other models overfit in other ways. Okay, but linear regression has only one way to overfit, which is increasing the number of predictors. So if you are in a situation where you are building a linear regression model and you need to use 10-20 predictors for whatever reason, then you have to regularize your model, otherwise you run the risk of overfitting. Okay, cool. We'll see all of this in action in the demo. Okay, and obviously the effect of scaling I've already mentioned to you before, correct? Already I said if you don't rescale your features to the same scale, then you can't compare coefficients. Now what is regularization doing anyway? It is comparing the betas, right? It is doing an automatic comparison basically, right? So think of it this way. Suppose x1 is in the order of hundreds, that is this feature. Suppose it is in the order of hundreds, and suppose x2 is in the order of thousands, this one. Then what will happen? Since y is common to both, then the beta 1 will be of a higher order than beta 2, because x2 is in order of thousands, therefore beta 2 will be smaller order, right? And since x1 is of a smaller order, beta 1 will be bigger order. But in the loss, you are applying the same alpha to both betas, correct? So let me just write it here. Beta 1 will be of a higher order and beta 2 will be of a lower order. In the loss, you are applying same alpha. Now the algorithm has to minimize the loss, right? That is, in the end, that's what we are doing. We are minimizing the loss. The beta with the lower order, that is beta 2, will be ignored, right? It will totally be ignored because it's a small value, right? And the effect of beta 1 will be more pronounced. Alpha has to worry about beta 1 more than it has to worry about beta 2. This is not fair, right? Alpha is worrying about beta 1. Why? Because beta 1 is much larger order, and since beta 2 is of smaller order, alpha doesn't care, right? Small change in alpha, right, will pronounce more effect in the case of the higher order coefficient. So again, this is not a fair way of training the model. It's not a fair way of treating your input predictors, right? So again, to show the importance of scaling the features before going ahead with regularization. All right. And as I said, in the unregularized case, you scale the features, you look at the model, linear regression model, then you can compare the coefficients and say, okay, this looks like age is less important or whatever income is more important. The only way you can make that claim is after you rescale all of it to same 0 1 0 1 0 1 or -1, whatever, whichever scale. That is manual. That is a manual comparison. Regularization is a kind of automatic comparison you can think of, right? It's a kind of automatic method, right? And we'll see more detail what it does to the coefficients. All right, having understood all of this, that brings me to parts 3 and 4, which is the two most common type of regularization. First is called ridge regression or L2 regression. For those who would like to know more about the math part of it, L2 refers to L2 norm. So this is obviously a vector concept. So if you're interested, you can refresh on that a little bit. So L2 regression, L2 norm. And obviously, okay, I've missed the squares. I guess nobody noticed here. If you see, I missed the square, I think. Yeah, here I'm missing the square. Okay. So in the loss, same way here as well, I have missed the square. So let me put that. Now it is your SSE. Okay. So in ridge regression, what are we doing? This is your SSE, sum of square errors, right? This is your SSE, and for this term we will choose p equal to 2, and if you choose p equal to 2, you will get square. So here you are adding square of the betas. Okay, that's all it is. So we understood what regularization is. Ridge regression is nothing but p equal to 2. In this formula, p equal to 2. So now you are going to train with this new loss function. I did this for the 10 data points, the coffee data set, you know, Arti, whatever Zishan, right? And immediately you can see the results. Please see the results. Unregularized model has 825 coefficient for gender. The ridge model has 29. I chose alpha equal to 25, by the way. Okay. So before training the model, I chose alpha equal to 25. Immediately you can see that the magnitudes of all the coefficients have gone down. Right. That is pretty much obvious. You can see it. Right. These are the coefficients, by the way. Right. Intercept, gender, job, these are. The intercept obviously increased, but all the other coefficients have gone down in magnitude. This is the effect of regularization. And you might be asking, okay, fine, what's going on with the model inference? Fine, let us look at it. So the unregularized model, if you see, it was overfitting, correct? So 101 RMSE in training data, 197 in training data, testing data. So bad performance in testing, good performance in training, that is overfitting. Great. What happened in the rich case? Well, in the rich case, very bad learning happened. The first thing you can see is bad learning, right? The training error itself is much higher, 293, right? And the training MAP is 12%, which is much higher. But even though bad learning has occurred, you can see that the testing results are almost the same as the training results. Okay, and this is called the concept of generalization. Generalization does not mean you perform bad in training, good in testing, or good in training, bad in testing, none of that. Generalization means you perform similarly in all the data sets. Your model performs similarly in all the data sets, but you should perform well. Okay, so there are two parts to generalization, right? Generalization includes, one, your model should perform well. Two, it should perform similarly in all the data sets, right? So training, validation, testing, you need to have similar values. So if you see, the ridge model has slightly more similar values, 12%, 10%, 12%, 10%. Okay, so this is how ridge model penalized my coefficients, but of course it led to bad learning. We said this could happen, right? A while ago in the quiz we said this could happen. It is happening, it does happen. Okay, so of course you need to control the alpha value. Okay, what is lasso regression? This is the other popular one. Okay, again let me put my squares. Yeah, let me put my squares. So in lasso regression, again you have your SSE. This is your sum of square errors, right? This is SSE. Instead of p equal to 2, you take p equal to 1. Okay, so as I've written here, p equal to 1. So now the new loss that you will be using is this. So this is your sum of square error plus this additional lasso term. And for those who want to read the math, L1 norm, right? So these are all vector concepts, right? L1 norm, L2 norm, all these things. It's kind of obvious though. L1 means p equal to 1, L2 means p equal to 2. Okay. Let's see the effect of the lasso model. Now in lasso also, I took alpha equal to 25. And very interesting thing I would like everyone to see is so many zeros in the coefficients. You can see, right? So many zeros in the coefficients. So I fit the lasso regression model with alpha equal to 25 to the coffee data. And this is what you get. There are many zeros in the coefficients. Essentially, lasso model offers you automatic feature selection or elimination, whatever you want to call it. Okay, automatic feature selection / elimination. If you remember in the MLR demo that we did recently, I might have said something like, we have to look at so many models, we have to analyze all the features, we have to do VIF, we have to do correlation, this, that. Now I think that is optional, right? To some extent it is optional. You do your correlation analysis, you do your VIF analysis, you do all that, but your ridge and lasso and regularization models are doing automatic feature elimination for you. So this again, I want to tell everyone the difference between the data analysis part of things and the machine learning part of things. In data analysis, no feature scaling, manually you have to interpret a lot of things, and all those things, right? Interventions from humans, right? I hope everyone remembers the first session, intro to ML, where we said data analysis involves a lot of intervention, human intervention and all of that. I hope everyone remembers that. And then we said machine learning is what? It is the attempt to remove all of these unnecessary, I wouldn't say unnecessary, but so many interventions, right? We want to let the machine do the job, right? So you can see it in action. Right now you can see it in action, right? So LASSO model is doing automatic feature selection, regularization is doing feature comparison for you, right? Using this, you can actually quickly compare, important features and things like that. I would then also finally like to point at the model inference. Okay, so now if you see, the learning is not good, not bad. I'll tell you that much. Learning is not good, not bad. Because see, unregularized model gave you 101 RMSE. The LASSO model is giving you 167. Who is performing better on the training data? Clearly, it is the one with the lower RMSE, correct? So 101. So the unregularized model is doing better on the training data. The LASSO model is doing worse on the training data. But immediately check the testing RMSE. Immediately check the testing RMSE. The unregularized model has much higher testing RMSE, 197, and the LASSO model has 160, which is less than 197. So your LASSO model has performed better on the testing data than your unregularized model. Point number one. Point number two, the values are similar. Look at it. 167, 160, almost similar value. This is what we call generalization. Values are now similar. So in this case, the performance also improved, point number one, and point number two, the performance on different data sets is similar. Now we can say that this model has generalized well. Okay, so this is how regularization works. Okay, so quick differences between Ridge and LASSO. Ridge p equal to 2, LASSO p equal to 1. Ridge does not have feature selection because you don't get 0. You can manually set threshold values and do if you want. What I'm saying is, see, Ridge does not have 0 coefficient for features. LASSO will end up having 0. So, immediately you can remove feature when it is 0. So Ridge does not have automatic, but LASSO has automatic feature selection. Generally speaking, Ridge does well if most predictors influence the response variable, in the sense that the target is explained, or the variation in the target is explained by many factors. Then Ridge is a nice model. If you are wondering, out of your say 10, 20 features, if you are wondering which is useful feature, which is not useful feature, and many of the features really are not that useful, that is what is written here. If many predictors do not influence the response variable, then LASSO will immediately eliminate many of those features with 0 coefficient. Okay, it will give coefficient 0 to that. Both of these allow for multicollinearity. This is another point that I would like to point out. So it's like this, right? Multicollinearity means what? We spoke about it in the previous session, I think. Yeah. And it just means that your predictors may be correlated to each other, right? Now, both Ridge and LASSO in their own way deal with it automatically. Okay. So what Ridge does is it equalizes coefficient values. It distributes the strength of the coefficient between predictors. And what LASSO does, LASSO removes unnecessary features. Correct. So as I said, this whole thing that we did last time, which is VIF, correlation, everything, all that stuff about multicollinearity, do it for the purpose of understanding your data, do it for the purpose of analyzing your data, perfectly fine, right? But it's not necessary. Once you invent these kinds of methods and techniques, many of those things become automatic, right? So feature selection became automatic, dealing with multicollinearity became automatic, right? It does all of this, Ridge and LASSO. Okay, great. So I think till now we have basically learned one thing, right? Within the past 1.5 hours, we have learned one thing. What we have learned is that we have added this new thing called regularization term to the loss, right? Which is essentially punishing the beta. That's all it is doing, right? It's essentially punishing the beta. right? And this, and we have seen this allows for better generalization. Okay, if you do not control the rate at which your beta optimizes to your training data, then you will get overfitting. Therefore, we want to control the rate at which the betas are optimized to the training data. Okay, and you've seen the results for yourself in the dummy data. We'll see the result in the cars data also. Okay, now let's get to this part about alpha. So if you saw in the previous cases, I used alpha equal to 25. Now that is an arbitrary number. Why should I choose alpha equal to 25? How should I know how much power to give the loss term? So if you saw in the ridge case, I gave alpha equal to 25, right? So in the ridge case, I gave alpha equal to 25, and the model did not learn anything. The model performed very bad on the training data. So it's a bad model, right? So how should I know? How should I understand what is a good alpha value for my case, right? So that is called hyperparameter tuning. Okay, and this alpha is called the hyperparameter. So quickly, to understand the difference between parameter and hyperparameter, if you see on the left side of your screen, you have the parameters of the model, which is beta 1, beta 2, beta n. Now see, I am not calculating these beta values. Okay, your model is calculating, right? So the question we are answering here is, what is the model learning? And this is estimated using the training algorithm, that is the objective function. And basically you're using the training data set to do this. Okay, we don't decide the beta values, right? The algorithm finds you the best beta value. This alpha is essentially a hyperparameter. Okay, there is no algorithm to find out alpha. Okay, and alpha, basically you're trying to answer the question of how is the model learning? Is it overfitting? Is it underfitting? Whatever. The parameter enables the model to make predictions. The hyperparameter enables the model to make better predictions. That's the difference. Okay, and generally these alpha values we find using searches. We basically search for alpha values. We basically search for hyperparameters. Now of course there are many methods where you can somewhat have an algorithm to find the value of alpha for hyperparameters. They tend to get a bit complex and very, what you say, situational. Generally speaking, if you want to implement your ML machine learning tasks in various domains, in various data sets, in various projects, then this is generally the way one would approach it. You search for alpha. How do you search for alpha? For loops, grid searches. There are many search heuristics that are there. Okay, and this is exactly where we will use the validation set. Okay, to choose a good alpha, we will use validation set. How we will use? Essentially, we will train our training data, train our model on the training data for different alpha values. Alpha equal to 1, alpha equal to 2, alpha equal to 3, whatever, right? And train the model, train the model, train the model. Just train model for each of the different alpha values on the training data. Check the performance of all of those trained models on the validation data. Out of all those validation performances, choose the best. Then you retrain your model and then you show it to the testing data. So this is the reason we split validation and testing separately. Okay, validation data is used to check which hyperparameter value is good for your model. So you're actually improving your model. You're looking at the performance on the validation data and going back and saying, no, alpha equal to 2 is not good. Let me use alpha equal to 3. Right? So training and validation, both of these data sets form training. The whole process of training requires both training and validation. Okay, this is the reason why we split that validation data. Now I have some graphs here. We'll see different graphs on the cars data today, but this is generally how you analyze. Okay, so here you have MAPE of the ridge model as a function of alpha. Basically on the x-axis you have the alpha values 1, 2, 3, 4, whatever till 50. Okay, just I have 0 to 50. You can take 0 to 100, whatever. Then you just run the for loops. You run the for loops, train the model for each alpha value, and check the performance. Okay, check the performance of that specific alpha value model for training and validation data. And that's what you're seeing here. The blue is the training MAP and the red is the validation. So what do you think will happen if alpha increases? What do you think will happen? We just saw, multiple examples as well as a quiz, right? If you have very big alpha, then you are penalizing the coefficients. That means you are going to do less learning, correct? If you're penalizing beta for existing, then of course there is going to be less learning. So as your alpha increases, you are actually blocking your model from learning too fast, which means it's going to have more error. And that's what you're seeing in the blue graph, the blue line, right? The error is increasing with increasing in alpha, right? Both MAP and RMSE, both are increasing with the increase in the alpha value in the training data. This is for the training data. This is true for the training data, correct? What happens in the validation data? This is exactly what I said might look surprising, but it is very normal. In the domain of machine learning, this is very normal. Initially, the validation error increased. Then it started decreasing. It will decrease till what? I don't know. You have to check for more values now. I have stopped my alpha value at 50. You can check for 100, whatever. It might decrease till a point, then it might increase again. So this is interesting behavior, isn't it? The error, which should be less, by the way, we are talking about MAP, RMSE. These are difference based errors. So we want less difference. So ideally we want less error. By increasing alpha, training error has to increase. Training error will increase because you are blocking the model from overfitting to the training data. So training error will increase. That is what you're seeing in the blue color. It is increasing, training error. But the red one increased and then decreased. And then if you check for more alpha values, it may start increasing again. Okay. So as I said, this may look surprising, but this is very normal. This is what you see generally when you spend time with ML models. Okay. So out of this, what I might think, okay, I should be using some alpha value around 50, 40, whatever. If you see, I have 10% validation error here. So then I will go back and I will use alpha equal to 40 to retrain my original model. And that is what we can say is improving our model, right? And this whole process is called hyperparameter tuning. And notice that I'm using the validation data to do this, okay? Which is not unfair because I still have separated testing data, okay? Which the model has not seen. Similarly, for LASSO regression also, you do the same, right? You build a LASSO model with a certain alpha value, then do for another alpha value, so on and so on and so on. And then you track the training performance, you track the testing, validation performance. So in this case, again, the training error has to increase. There's no other option, right? If alpha increases, then the training error will increase, okay? So the blue, you can see is increasing. But the red is doing all sorts of funny things. It's increasing, decreasing, increasing, then slope is increasing. Who knows what's going to happen after that? So you have to look at this and you have to come up with a acceptable answer. Like you should be satisfied and say, okay, in if you see the left side, the MAP, you have to look at this and say, I am happy with this value. What is this? Around 6.5% MAP, and alpha looks like around 18 or something. So you look at this and you say, okay, for me, alpha equal to 18 is working for my data. Let me build a model using alpha equal to 18, right? Hyperparameter tuning is done. Validation data has been used. Go back, train your data with alpha equal to 18. Now you are ready with your final model. Test it on the testing data, and that's all. That's the final thing, right? Okay. So how do you do the tuning? We use search heuristics. You can use for loop, grid search, randomized search. Things like grid search we will use later in the course, when we do other models. For linear regression, we'll use for loops to start to understand this better. Okay. Randomized search, once you understand grid search, I think you will be able to do randomized search yourself. So we won't do grid search today. We'll do it later in the course. For linear regression, we'll stick with for loops. Finally, I just want to make a few comments on model selection. So please recall this diagram, the machine learning pipeline. We said this is kind of where we are focusing, right? Defining the ML task, choosing the suitable ML models, build and train the model, evaluate the model. So what we saw till now is for one model. When you're talking about hyperparameter tuning, you are tuning for one model. Now let's build this little by little. Okay, so initially you had your unregularized model. Could you change anything in your unregularized model? No, absolutely nothing to change. Just take the training data and fit the SSE. The sum of square error should be minimum, end of story. In other words, you keep running that code 1,000 times, you will get the same coefficients, right? So in the unregularized model, there is nothing you can change. Then we went to regularization, in which we have one level of control, which is alpha. You can tune for a good alpha value. That is one thing we can do. But still, you cannot change the structure of the model, because still we are dealing with the same model. Okay. In the future, you now have to look at different models also, right? So if you are taking your linear regression, then you will be tuning alpha. If you are taking decision tree, you may be tuning something else, depth of the tree, criterion for splitting. There are many hyperparameters in decision tree. I'm just taking an example. Okay. So the decision tree is going to have its own hyperparameters. Linear regression has its own hyperparameters. So how do you compare between these two? Again, you want to check the performance on the validation data. Okay. So this is called model evaluation. But that's not the only thing. When you choose models, you also need domain expertise. Okay. Even you shouldn't only go by validation testing results, things like that. You should try out the different models. Okay. In fact, I think there was some Kaggle competition way back. It's not recent. I think it was way back. That was around Netflix something recommendation. I don't recall it in detail right now, but it was a movie recommendation or something, that kind of a problem statement. It was a Kaggle competition. Right, and many models people had tried: random forest model, neural network model, even linear regression or logistics, something they tried. A lot of people tried a lot of things, right? So many models came par to par actually, right? Some models were doing pretty well, but more complex. So for example, linear regression is a simple model. Decision tree is a slightly more complex model. So then you have to think about computational complexity and things like that. So if you use 10 data, 20 data, 200 data, you will not see the difference. Use thousands and 10,000s of data to compute and see. You will start seeing the difference. Time taken to compute. Okay. So all of these things come into play when you talk about model selection. Okay. So again, as I said, no need to understand all of these things immediately today, because over the next many weeks you will be learning all of these various different models, and by the end you yourself will be in a position to compare and understand many of these models, right? Okay. And just as an extension, the question you want to be asking is, what is the right model for my data, right? There are so many supervised learning models. So this is again the same data that we've been working with. So let's start with setup and data preparation, the usual packages. The only additional things I would like to direct your attention to is these things here, right? So I have something called the min-max scaler from Scikit-learn pre-processing. I also have LASSO and Ridge from linear model. Okay. So in addition to the linear regression model, method from the linear model package in Scikit-learn, right? Linear regression. In addition to that, I have LASSO and Ridge, and scalar because we need to scale our data. So these are the additional things that we will use. I'm just going ahead and running this cell. Let's look at the data and all of that, right? Converting to category. We've seen all of these things before, converting to category and things like that. So the data we're dealing with is car prices data, as you can see here. The price is our target variable, and we have many predictors: symboling, door number, car body, engine location, wheelbase, so on and so forth, right? We have spoken about and analyzed and fit linear regression models to many of these, using many of these predictors to predict price. And we'll continue with the same thing, convert symboling to category and all of these things, right? Drop the car name, so on and so forth. Now, for this demonstration, I want to use slightly more number of features. Okay, the first thing that you will notice is symboling, car body, car weight or curb weight, horsepower, city mpg. These features we have used before, correct? In addition to those features, I want to use wheelbase, engine size, bore ratio, stroke. Okay, I will use these 4 additional features. The reason is that when we are talking about regularization, as we discussed in the theory part, it only makes sense when your model is prone to overfitting. Now, a linear regression model, it cannot be prone to overfitting if you have less predictors. If you remember, in this session itself, we discussed and we said that the only way for a linear regression model to overfit is to have more predictors. Okay, so let's take more predictors, right? Which is what I've done. I've taken a few more predictors, wheelbase, bore ratio, things like that. And you can, of course, study these things. What are these values? As I said, I'm definitely not a car expert. So, those with some interest or expertise in this can study the data and understand more about these features, wheelbase and things like that, bore ratio, all of that. So these are the predictors that I'll be using. So the additional predictors. So let's go ahead and retain that. So this is the data that it looks like for me right now, right? I have price, I have the car ID here, 1, 2, 3, 4, 5, and so on. And I have these predictor features, symboling, car body, all of these. Now out of these symboling, car body, so if you notice engine location, we saw last time that it has a very high imbalance, so we did not take that feature. So I didn't select the feature here itself. Okay, so all the features, final features that I will be using in the demonstration, they are in front of you. Symboling, car body, wheelbase, car weight, engine size, bore ratio, stroke, horsepower, city mpg. These ones I will use to predict price. Okay, so essentially I have 205 records. That is observations or rows, you can say, and I have 10 features including price. Okay, and you can check that there are no missing data, and you can also check the type of the data. Okay, so yeah, that's that. Now this is again something that we generally do, right, when we fit machine learning models. Especially using Scikit-learn, we have to split it into 2 things, X and Y, input and output. So X is everything except price. So from this data frame, other than price, everything else is going to be my X. All of these features together is going to be my X, and the price is going to be my Y. So you can quickly just look at it, right? X is all of these features. So I have car ID 1 to 205, and I have all these features and the values. Similarly, Y, car ID 1 to 205, these are the prices of the cars. Okay. So finally, in the last session, we split the data into training and testing, right? We used train test split command, this command only once. But since we are going to do hyperparameter tuning, which we have seen, we need the validation data. Again, validation data is just a fancy way of saying testing only, but we will not use the validation data as the final, because we are using it to improve our model. That leaves us with a gap in the end. We need some kind of final score, you can say, right, for the model. And we cannot use validation for that, because we are using the validation data to get good alpha values. Then of course, if I use good alpha value, it will do good in the validation data. That's not a fair test. So we need validation separately, we need test separately, correct? So now we need to split the data into training, validation, and testing. Okay, that you can do by using the train test split command 2 times. Very simple. So in the first command, you can see here I have written x train, x temporary, y train, y temp, and here I'm putting x and y as the input, and test size as 0.4. 0.4 means 40% test size, which means these x temp and y temp will have 40% of the original data, and 60% will go into training. Okay, now in the next command, in the next train test split command, use x temp and y temp as the input. So the 40% that you did not use for training, that you use as the input for the command, train test split command. And here I am using test size 0.5, which means whichever 40% you retained from the first command, you are now splitting into 50-50 basically. So 60% you kept as training, whatever remaining you kept as input for the next command, and there you are splitting into 50-50. So here X validation, Y validation, you will get 50% of the data of the remaining data, that is 40% of the original. So 50% of 40% of original, correct? We can calculate these and see the size. Okay, and X test and Y test also will have 50% of the 40% that you kept aside. So in 205 is my original number of records, correct? So 60% of 205 is 120 something, I don't know, but we can check the length using the len command. So you can quickly check the number of observations in your 3 data sets. Okay, so you can just use the len command to do that. So the training data has 123 cars observations, the validation data has 41 cars, and the testing data has 41 cars. Okay, so this is the split that we'll be going ahead with. Now the next thing we said, if you want to actually do regularization, that is automatic feature elimination, automatic feature comparison, and you want to skip all this VIF and all of that, this is a necessity. You need to rescale your data to the same scale. Correct? Now, since your categorical variables are already within 0-1 range, therefore it makes very very much sense to use a min-max scaler here, right? So min-max scaler will rescale your features to 0-1. So before we do that, we will just see an example. So if I just say extrain head and I just want to see 2 inputs, 2 records. So before the scaling, if you see wheelbase is on a different scale, 93.7, 107, all of that. Curb weight is in another scale, 2000 pounds, I guess. Car weight we discussed was measured in pounds or something in this data set. So I don't know, we need to check, but last time I remember someone said pounds. So this is 2000, 3000 pounds. Engine size, I'm guessing this is some kind of volume metric, so it has its own scale. Bore ratio is a ratio, so it has its own scale. So all of these different features are on different scales. Okay, now remember also that I said there is the concept of data leakage. Okay, you should not train your scaler, that is, you should not design your scaler using all the data. You should only design it using the testing training data. So generally what you do, these are the few steps. First, you initialize a scaler. Okay, so scaler equal to min-max scaler. The scaler is initialized. Then you need to fit the scaler. Basically, initialize and fit. There are 2 things. Okay, initialize and then fit. So you initialize the scaler and then fit the scaler. So this is the initialization. Now I obviously want to fit it only for the numerical columns, right? So I will select the data. So this command gives me the column names. Okay, so numerical columns equal to df.select dtypes. You've seen this command before, and I'm including int64 float64. Where is this coming from? How do I know this? You go to df-info. In df-info, I can see my numeric data. These are in either int64 or float64. Okay, so I will select those columns int64, float64, and if you see here, I have ignored the last entry, that is the last column. Why have I done that? So let's quickly understand that also. So if I just do this df select columns int and whatnot, it gives me price also. Now see, you can scale price, but it doesn't make any sense at all because it's not affected in any way, right? Price is what you are predicting, right? This price is what you're predicting. The data leakage issue and the coefficient comparison issue, all of these issues are issues of the predictors, not of the target variable. So there is no need to scale the target at all. Okay, target you can directly calculate. Okay, no problem. So I want to exclude the target, which is why I have used slicing, list slicing here, and I have put -1, which means it will ignore the price. So you can check that here. If I just do like this, as you can see, it has removed price from the list. Okay, so now I have all the numerical columns here, which is wheelbase, car weight, engine size, all of this, and price is not there, right? So in fact, I could even direct, instead of df, I can directly use xtrain also, no problem. So if I do, for example, if I take this command, right, the select d types, and instead of df, which is my original data frame, I can directly use xtrain also. This should give me the same list. As you can see, it is giving me the same list: wheelbase, car weight, whatever, and it has no price. Why it doesn't have price? Because x, obviously input data, does not have price, right? So you can even obtain the numerical columns using this command also, no problem, right? So instead of this, you can do this, no issues. Okay, so now what you do, you select those columns in your training data, and then you use the scaler to do two things. You are fitting and you're transforming. Okay, so fit means what? You are getting the maximum value, minimum value, all of those things required to convert to 0-1 range, right? Those values you are obtaining only from the training data. That is what fit does. That is obtaining the maximum and minimum. Then using the maximum minimum to change your values, that is called transform. So the scalar object has a command called fit transform. It does both. It is the same as doing fit and then transform. That also you can do. You can do scalar fit and then you can do scalar transform. You can do separately also, same effect, right? Scalar fit, scalar transform, like this you can do, or you can do directly scalar fit transform on the training data. Now on the validation and the testing data, we should not fit. That is the whole point. We should not fit. Whatever scalar has been fit, right? Whichever minimum maximum value you got from xtrain. So car weight maybe minimum is 2191, maybe maximum is 3197, right? So if you got this from the training data, that same value you will use as a formula to convert the other values in the validation and the testing data. Okay, so the formula, I don't quickly remember it, but it is a very simple algebraic transformation, right? It's a new value equal to I think max minus old divide by min something. There is a very simple formula. I don't remember immediately. You can just Google and check the formula for min max. It's very simple. But for that formula to work, you need the min and max. Okay, and that you should only get from the training data, which is why I'm using fit transform here. Okay, and then for validation and testing, whatever formula you got, min max formula, same formula you have to use here. You cannot fit again. Okay, so let's go ahead and do the fitting. Now let's see what happened to my xtrain. So I'll take the same command and I'll just see here. Now you can see all of these things have been transformed. Okay, everything has been transformed from 0 to 1, right? And in fact, another way to check is let's say xtrain, say you take wheelbase, okay, and I'll say max. Definitely you will get the maximum value 1 somewhere in the training data. You will get. Why? Because the min-max scalar maximum value also came from the training data. So that maximum value exists in the training data. So 100% xtrain will have somewhere you will get 1, the maximum value. But is it going to be the same for xtest and xval? I don't think so. As you can see in the screen in front of you, the maximum transformed value in validation for wheelbase is 0.74, not 1. So now I hope it is becoming clear. Your 0 and 1 came from the training data, right? You cannot again do a new fit on the validation and say validation has maximum 1, so there also 0 and 1, there you'll fit a new scalar. No, that is called data leakage. That is problem of data leakage, right? Similarly, X test maximum is 0.84. Again, the value 1 is not there. Why? Because the value 1 came from the training data. Okay. So this is kind of the preparation that we need to do. Now we have scaled all our numerical columns. We need to now get dummies. Now if you see the X train or anything, right? X train, let's say I just see 2 values. These things are still need to be converted to dummies, right? So symboling here it says 1 and 0, but we know very well it has -1, 3 other values also are there. It's a categorical variable. So we need to get dummies for this, get dummies for car body. Okay. So we need to get dummies for each of the data, X train, X well, X test. And again, you're just going to use pandas get dummies, choose your data, choose your columns, and drop the first dummy variable in each case, because you don't need you know 2 dummy variables for 2 levels. We understood that in categorical, right? So if you have male and female, you only need male. You need just 1 column. If you have 3 levels, you need 2 columns, things like that. So we are dropping the first one in each case. So this is done. This is all I need to do for preparing the data. So now if I see X train dummies, I should be having a very large, yeah. So these are all the numerical ones, and then if you see this side, you have all the categorical ones, right? So if you see car body, hard top, hatchback, sedan, wagon, and if you see original DF car body, there is one category which we have taken for reference, which is that convertible. So if you see car body convertible, it is not there here because I dropped first. Okay, I did drop first equal to 2. You can keep it if you want, but it's of no use. As I said, the information in that is exactly like complement of the information in the other 4 columns. So if you know the information of these 4 columns, that is 100% equal to knowing the information in that 1 column. So when you have 5 levels, so here you see convertible, hatchback, sedan, wagon, hardtop, 5 levels. You don't need 5 dummy variables, you need 4. Okay, to completely define the data, you only need 4. So anyway, this is what my data looks like right now, and we are ready to build the models, right? So first, we can do, predict price using all the predictors in my data. Okay, all the predictors means all of these: wheelbase, bore ratio, car body symboling, all of that, right? So we can of course do an analysis using stats models. So if you see here, I'm using the full data frame before. So in stats models, you don't need to do XY split and all of that. And we did not, when you're doing analysis, you don't necessarily need to split into training, validation, and all of that. This is just for looking at the model, just to recall the model. Okay, so we are fitting the complete model. So it is using all the predictors to predict price. Okay, so smf.ols fit and then summary. Now, if you see the R square and adjusted R square, these things are pretty good. Yes, 85%, 84%. That's a good sign. Maybe it's too good also. Okay, so that you cannot judge from here, right? So when I say too good, I'm talking about overfitting. Now that I have increased the number of predictors, there is a larger chance of overfitting, and we will see how to judge that. So just by looking at this R square value, I cannot say whether it is overfitting or underfitting. I cannot say that. I can say it's a good fit for the training data, but I cannot say whether it's going to do well on the testing data. So before we continue for Scikit-learn, if you see, one small thing is in stats model, you can directly give the categorical variable as a single name, symboling, and automatically the stats model package is going to split it into the levels, right? So symboling will be split into -1, 0, 1, 2, 3. Default is -2. Same way, car body, you only give the name car body here, but stats model will automatically split it into the required dummy levels, right? That's an advantage, you can say, with stats models. But with Scikit-learn, that doesn't work. You have to give the feature name correctly. So if you see here, I've written features considered equal to this. In fact, all of these names you can actually directly get from the dummies, right? If I just say extend dummies dot columns, I'm going to get all of these, right? So directly you can just say features considered equal to extend dummy columns. I've just written it out here to show you that all these features we have to split it in this way, right? This is the exact same list. Okay, symboling -1 0 1 2 3, same thing here, -1 1 2 3 0 and so on. Okay, so we'll store this list of input features for Scikit-learn in this variable features considered, okay, for easy reference. Now let us use Scikit-learn, let us use Scikit-learn to fit a linear regression model using all the predictors to predict price. Now this time we will only use the training data because now we are getting into proper model building with Scikit-learn. So we'll only use the training data. So what is the command for that? You give a name for your model, LR model 1, instantiate the model, linear regression. This is the method from Scikit-learn, and then you fit. So LR model 1 dot fit. This is your input, that is extrain dummies and all the features considered, right? Extrain dummies, all the features considered, and white train. Now I've put it this way mainly because if we want to reduce features and things like that, then we can change this list. Okay, now of course in my analysis I'm using all the features, so I don't necessarily need to do this. I can directly just delete this because I'm using all the features. But if we wish to, maybe when we rerun the notebook, if you want to remove a feature or something, then you can do that. But the necessity is not there, right? In this case, extrain dummies is the same as extrain dummies with all the features considered. This I've written here just to show, okay, I'm using all of these. Okay, so let's go ahead and fit. In fact, if you want, we can not even use that and just use extrain dummies as it is, and you can fit the model. So now your model has been fit, and you can take a look at the coefficients. Now look at the coefficients. Okay, now there are so many coefficients, and you need to match this with these, right? So whatever order, now here I did not give this order, correct? So if you see extrain dummies, originally what is there in extrain dummies, we have to see, right, the order of the columns. So it is starting with wheelbase, car weight, so on and so forth, right? So if I just say dot columns, right? So this coefficient, first is the first coefficient here, that is wheelbase. So you have that one here. Then you have 7617. This is the coefficient for car weight. Then you have 13115 coefficient for engine size, so on and so forth, right? But if you want to reorder that, then we can of course reorder the columns using the referencing, data frame referencing, right? So you can specify the list here, and you should get a different list this time. That is, these values should come up before. Let us see. Yeah, so you can see here the values which related to symboling, now they will come here because I have given in that order, right? So I've given the column names in this order. You will get the the coefficients in the same order. Let's check again. Okay, so if I just want to show you, I can just do this, and I will not use this list here. I'll directly just use extrain dummies, right? And let me print the coefficients here. So as you can see, these values 2036, 2416, 2495, these are the coefficients of what? For that you have to check the columns of extrain. Where was that? Extrain dummies dot. So yeah, you can see these 5 values here, 2036, 2416, 2495. That relates to these 5 features here. Okay, that is in the original extend dummies. Okay, here I have not specified any order for the input features. If I do specify the order, or if I do take a subset of the input features, I can specify the order. What is the specify order? It is there in this variable features considered. So you have symboling -1, 0, 1, whatever, right? So these 5. So ideally what should happen? These values 2036, 2416, it should come first. And that's exactly what is happening here, as you can see. Okay, so this is kind of important. That's kind of the reason why I did this, right? Because when I do ML model analysis and things like that, generally the original extrained data, columns, somehow they just get messed up as you do all your EDA and dummies and all of that. It gets a little messed up. So when you are doing your ML analysis, you may be interested to reorder the columns. Okay, like what do you want to see first? Categorical first and this first, whatever, right? That's one thing with Scikit-learn that you need to keep in mind. Okay, keep in mind that it's not going to give you names. Okay, like stats model will always give you names, name, coefficient value, all those values are here. It will give you the names and all. Scikit-learn is not going to give you the names. It will give you the coefficient in a list. All right, cool. Now that that is out of the way, we know that these are symboling coefficients. This is car body, and these are all my wheelbase and all of those things. Okay. This we have seen before already how to do. Just take the model, use the predict command, and here I want to actually repredict the training. So here I want to look at the training performance. I want to look at the validation performance, right? For this model. And in this model, if you notice, we did not do any regularization. And this code you've already seen before, mean square error, MAP, all of those things. So use the prediction on the training data to get the training predictions, use it on the validation data to get the validation predictions, and then print the, calculate the values accordingly. So you can see that the unregularized model has a training MAP of 15%, but validation of 21. What would you call this? Please remember what we discussed in this session. Training error is less and validation error is more. What is the meaning of this? This is overfitting. Very, very clear case of overfitting. Training performance is good, that is less error. Validation performance is worse, that is more error. Okay, you can compare the same with the RMSE also. 2800, and if you remember last time we said we want to try to get it to $2,000, $3,000, right? The price was around the mark of what, $11,000, $12,000 median, something like that. The prices are around $11,000, $12,000. So at least I want to try to get, on my unseen data, not training data. Training data, of course, we want around 2,000 something, the error in the price, but for validation and testing also I should get around that. That's not happening. As you can see in this case, it's not happening, right? So there's much more error in the validation data when you do the predictions. So this is case of overfitting. Now let's look at the ridge model. Okay, so almost all the commands are exactly the same. Instead of linear regression method, you use ridge method. So if you see this command here, ridge, this I'll just go back and show you. From Scikit-learn linear model, linear regression, this is the basic model that we've been studying. And again, from Scikit-learn linear model, we have LASSO, we have ridge. So instead of linear regression, you just use LASSO or ridge. Okay. So in ridge, I will start with alpha equal to 1 because I don't know which alpha is correct. Okay. So I have to start with some alpha. In fact, I guess there must be some default. Yeah, the default alpha is 1.0. Okay, and everything else, if you see, looks like linear regression because it is linear regression. It just has a name, ridge regression. Okay, so ridge, start with alpha equal to 1 or anything, and follow the same steps. Fit the model on the training data. Okay? And now you can compare the coefficients. So here, coefficients of the unregularized model, as you can see, these were the coefficients of symboling and wheelbase, all of those things are here. And this set, it is the coefficients of the ridge model. Already you can see that the coefficients have been damped down, right? 2036 became 799, 2416 became 656, 3465 became 1823. So already there is the coefficients are getting penalized. This is what we mean. when we talk about regularization. All the coefficients will get penalized. We will not allow the coefficients to try to overfit the target variable. So then your next question is going to be, okay, how do I actually, so okay, now your question is fine, the coefficients have been penalized, but what about the model inference? How is it performing? Did this help me? For that, go ahead and do the same thing. Predict on the training data, predict on the validation data. If you remember the slides also, the analysis of the overfitting, underfitting, you're doing by comparing training and validation performance, right? So use your ridge model, LR model to predict on training, predict on validation, and get the results. Now you can see here, okay? So first thing what you notice is that the training error increases. You go back to your unregularized model, the training error is 15.74%. In the regularized model with ridge, your training error is almost 17. So training error increases. But second thing you should notice is validation error decreases. So here it is 21.73 in the unregularized model, the basic model. In the ridge model, it has decreased to 20. As I said, it might look surprising, but it is very normal when you deal with ML models. So that is, as you can see, it is already trying to deal with the problem of overfitting. Okay, already it is trying to deal with the problem of overfitting. So that's ridge. What do you do for lasso? Exact same thing. Instead of ridge or linear regression, just use the lasso command. Okay, here also the alpha default must be 1. Default is 1. So there's no need to specify this also. I've just written it here. So just do the same thing. Do lasso, instantiate it, fit it to the training data, and you can also compare the coefficients if you want. So here, this is the unregularized model 2036. The ridge model, it became 799, the coefficient. In lasso, it became 1730. It's still been penalized. Okay, 1730 is less than 2036. Okay, so definitely penalizing happened, but the strength of penalizing is different in both cases. Why? Because of alpha. Okay, how alpha treats these models depends on the value of alpha for that specific model. So yes, coefficient has been penalized, but now the question is how much should I penalize? Right? So we'll get into that soon. You can again check the performance of the model. So I'm guessing that training error must have gone up from the regular, gone up or almost the same, 15.74, and I'm seeing 15.7 almost here. And validation is almost the same, 21.73, 21.51. Validation actually went down. Okay. Okay, so this is how you fit ridge and ridge and lasso linear regression models using Scikit-learn, and this is how you start analyzing the notion of model performance. Okay, when you're dealing with predictions, training and validation, this is what you need to track. So now comes the question of what should be my alpha value, correct? So for that, we have to do something called hyperparameter tuning, and we discussed this before. Basically, we need to fit models for various alpha values and track the training and the validation performance for all those alpha values. Now, what kind of range of alpha values should you use? There are guidelines. Definitely, you can sort of read textbooks, articles to get some idea of the guidelines. What sort of number should I be looking for? Because as I told you, hyperparameter tuning, generally we do it using searching heuristics, for loop, grid search, whatever. So I should know what I'm searching for, right? How do I know it should be 050? So np.arange 051, what does this give you? This gives you a list from 0 to 49, I believe. Yeah. So 0, 1, 2, 3, 4 till 49 in steps of 1. So how should I know? Why am I only checking for these alpha values? Good question. So you will understand this as you spend more time with these models, and as you spend more time with various kinds of data, you will start to understand what kind of hyperparameter values are or the range that you should be looking for. So for linear regression, your hyperparameter is alpha. For decision tree, you will get other hyperparameters, right? So for each model, as you keep understanding how it works, you will develop an idea of what kind of things you should be looking for. So we'll just start out here 0 to 49. Okay, so these are the alpha values for the ridge model that I want to tune, and all of this is just basic Python stuff to finally create my performance graph. But what we are doing is, for every single alpha value in the list, 0, 1, 2, 3 till 49, fit the specific ridge model. So choose alpha equal to current alpha value. So it will run through all the different alpha values, fit the model, do the predictions, get the training performance, predict on validation, get the training validation performance, and then just put it in a list. Okay, and I'm storing my performance values in these lists. So these are the 4 lists. Okay, after the for loop, I have the performance of my 50 models, 0 to 49, 50 models, right? So I have each of those models, I have the training and validation metrics. Directly you can use line plot or something to look at it. So if you run this is the kind of graph that I am getting. So we already discussed that blue cannot decrease, right? This is the training RMSE, which is the blue line or blue curve. Here also you can see the training MAP blue. So blue can never decrease. That is never going to happen. Okay, because why? You are penalizing the coefficients on the training data. You are not allowing it to overfit to the training data. So error will increase the more you increase the strength of the alpha. Definitely. So blue will always increase. When I say increase, the error is increasing. So if you're using some other metric, you might see a down graph. Depends on the kind of metric. These metrics, RMSE, MAP, they are directly proportional to the difference between the true and the predicted. So more means more error. Okay, so they will increase. But if you see the red graph, very interesting. Here it goes down actually, and then it starts to increase. Right here also it's going down, and then it's starting to increase. So definitely there is some regularization happening here. But still, what you might see is that generally the validation error is above the training error. So by looking at these two graphs, I am already thinking that maybe ridge is not the right model for this data. Okay, because the red line, even though it is decreasing and increasing, it is perfectly above the blue line. So there is no case in which they will perform similarly, so to speak. Similar means they have to almost be close. For some alpha value, they have to cross actually, right? That is not happening in the ridge case. So by looking at this, I can say even if I get a best alpha value out of this, the validation performance may not be what I'm expecting, right? Anyway, you can go ahead and still find the best alpha. So best ridge alpha, what you have to do, you essentially need that alpha value for which the validation error is least. So I am using MAP to get. You can use the RMSE list, or you can use the MAP list, or whatever else. So in the validation MAPE, find the index of the one with the minimum MAP and give me that alpha value. So apparently the best ridge alpha value is 1 for this model, right? Similarly, you can do a hyperparameter tuning for the LASSO model. So what do? Again, you just choose alphas. Instead of ridge, you are fitting LASSO each time. Okay, and you fit one LASSO model for each alpha value, get the predictions, get the errors, put it all together in a list, create a graph, all of that, right? Now, if you see here, I am tuning from range 0 to 499 instead of 0 to 49, 0 to 499. There are a few reasons why I did that. One, the ridge model has a square term. If you remember the loss, it is beta square in ridge. In LASSO, it's not a square. So the effect of alpha will be much more pronounced in the ridge case. Okay, so I can still look for between 0 to 50, 0 to 25, something like that in the ridge case, because the beta is being squared. In the LASSO case, it's a modulus of beta, not square. Power is 1. So I might need stronger alpha values, right? For that reason, I am searching for a larger range. Okay, so this and many other reasons. As I said, you can try out different things, right? You can even try 0, 1000 and go in steps of 5. No problem. sorry, 1000. Yeah, 0, 1000. Go in steps of 5. You can sort of try out different values. Essentially, at the end of the day, as I told you, it's a search. It's a search for the right hyperparameter value. Okay. At the end of the day, it's a search. So through more experience with ML models and understanding how these things behave, right, you will come up with sooner or later you'll start understanding what is a good range and what is a bad range to search for. Okay, these things come with a bit more practice and experience. Anyway, so I just need to do the same thing again. Okay, it's a very big cell, but it's all very simple stuff. So let's run it. Let's see what happens. Okay, quite interesting. I would say this is quite interesting. All right. So what's happening here now? Similarly, the blue line generally. By the way, there is a small decrease here. You shouldn't count that because 0 means unregularized. Okay, so I am including 0 in my list. Okay, and what did alpha equal to 0 mean? Alpha equal to 0 means unregularized. So you're comparing unregularized model with a regularized model. So this comparison is not valid. So here it's going down or it can go up, doesn't matter. Okay, but generally the trend is that it has to go up. So as you can see, this error is going up. And another reason, I think this is MAP. Yeah, MAP is not an absolute metric. So there might be some cases where it flattens out and things like that. But generally the trend you can see is that it is increasing, the training error. Okay. What about the validation? Now, interestingly enough, there is a minimum here and then there is going up here. If you remember, I told you, right, that we don't know what's going to happen in the validation case. We have to actually search and see what's happening in the validation data. We can't predict what's happening in the validation. So in this case, as you can see, it's going down, it's going up, it's going down here, it has a slope here, all sorts of things are happening. And it's getting really close around somewhere here, right? Around this 250, 300 mark. In terms of percentages, it's getting pretty close, right? Okay, again, we can do the same thing. Now, by looking at this, again, I would say that I am not hopeful because I need my validation and training errors at least to cross or at least to touch or at least to be really close. By looking at these graphs, I'm not getting so much confidence, but we will really not know until we do the final test. Okay, but this is generally not good enough is what I would say, right? This is not good enough. We might want to explore using more predictors, things like that, collecting more data. As I told you, the data is pretty less. For training we are using 120 data points. That is as good as a small data set, correct? So there are many reasons, but by looking at this, I would say maybe I need to collect more data, maybe I need to use more predictors, so that I get better result when I'm trying to compare the training and the validation performance. Regardless, you can do the same thing again. Choose the alpha value for which you get minimum error. So here there's a very stark minimum somewhere here. So I can go ahead and so apparently the best LASSO alpha is 247 somewhere here, right? To around 250 for LASSO. So now that we have our optimum alpha values by looking at the validation data, we should go back and train the final models. Okay, so the final optimal models. Unregularized model, already it is trained, so I don't need to train it again. These are the coefficients, just keeping it for reference. And now we will predict on the test data and see the testing results. Because after all of this, what I'm saying is, I'm done with my training, I'm done with my validation, I'm done with my tuning, and I am ready to declare my model on the testing data, right? So let's go ahead and predict on the testing data as well this time. Okay, so LR model 1, yeah. So here these are the predictions, and let's just go ahead and do that. So here if you see, these values should be similar, right? This is exactly the same metrics that we saw in the unregularized model, which is somewhere here. Yeah, 15.74% error on the training, 21.73 on the validation. Okay. So on the testing, what was it? 19%. Okay. So 15% on the training, 21% on validation, 19% on testing. This is the model inference for the unregularized model, right? Now for the ridge model, what do you do? Again, you just use the ridge command, choose the best ridge alpha, which you got from, the hyperparameter tuning, and then you fit the model. You can, of course, again confirm that the coefficients are being penalized. So, these coefficients are being penalized here, right? And then you can again go ahead and predict on the training, validation, and testing data. Now, if you see here, the optimum ridge model is point number 1, performing worse in training, that is expected, performing slightly better in validation. So 20.35% here, 21% in the unregularized case. So validation is slightly better, not much better, only slightly. And testing, of course, we cannot predict. Okay, and clearly the ridge model, even after optimizing, has not performed that well. Okay, so then as compared to the unregularized model, right? So then you fit the LASSO model. Again, you get the best LASSO alpha from the tuning, fit the LASSO model, check the coefficients. This is the interesting part, right? This is the very interesting part. Notice how LASSO model completely, negates some of the coefficients, right? It basically says, I don't want these features. All of these features have been eliminated. So this is the interesting thing about LASSO. It eliminates many features, right? Automatic feature selection. So clearly features have been penalized here, right? Then again, you can go ahead and predict on the training, validation, testing using this model and then see its performance. This, I think, is such a classic case of generalization. Just look at the values. Just look at the values. Yeah, 17.5, 19.7, 17.3. So close to each other and good, right? So if you remember, what did we say? It should be consistent across data sets. That is one thing, and it should be good, right? So if you see the unregularized model, it is not consistent. The unregularized model is doing well on the training data, doing very bad on the validation data, and we don't know how it's going to do on the test data. And this time it did bad, right? Consistency is not there, and generally performance is bad. Okay. And if you see the ridge also, it's kind of bad in the training, very bad in the validation and testing, and it's not consistent also, 16, 20, right? But if you see these values, this is the best testing SME we have got by far. This is the best validation MAP we have got by far. And if you see all the 3 values, they are very consistent. This is the indicator that your model is starting to generalize. This is the meaning of generalizability or generalization. Able to perform similarly given whatever kind of data. Correct? This means you are best prepared for your board exam. Right? We will say, right, whatever paper comes, I'm going to do well. Right? That is the generalizability that you are able to see in the LASSO model for this data set. Okay. So I think let me take a pause here because that's kind of the end of this session.